span many different time zones, and we have tried as best as we can to make sure that this is not an awkward time for anyone. So thanks again for joining. So today's just to give you a little bit of an introduction, I'm sure all of you know about the importance and the many recent works that have been happening in the security and reliability aspects of machine learning. And machine learning has a long history of being applied for different security and safety sensitive tasks. And these days, with the huge success of neural networks, as we all know, they're increasingly being used in different critical domains like autonomous driving or medical equipments or security or surveillance systems, right? And of course, in these domains, it's very important, as we all know, for these models or for these methods to be to some extent secure and reliable, right? And there is a long line of work demonstrating that even the state-of-the-art models that achieve state-of-the-art performance or even beat human performance in certain tasks, they tend to be very easily fooled, right? I'm sure you have seen some of these pictures. For example, here a stop sign was tampered so that it looks like a speed limit sign to a model, right? Or a high-risk category disease, right? The image of the disease location can be, under some normal, very regular transformations might be categorized as low risk, right? So this, demonstrates some of the dangers of the current lack of security or robustness in these models. And again, the aspect of security and robustness of machine learning have been explored over the past, many decades, right? But the latest set of work have mostly been motivated with this example of adversarial examples, right? Which I'm sure, again, most of you are probably familiar with. Essentially, around 6 or 7 years ago, it was shown that even though neural networks were, very accurate at predicting certain classes or doing certain tasks, there are these certain targeted perturbations that, once added to an image or to any input for that matter, can cause the model to mispredict almost consistently. So that was kind of the main driver behind this new set of work about focusing on security and reliability of machine learning. And in practice, often this adversarial example finding takes the form of adversarial attacks. In the sense, you want to constrain the type of adversarial example you are trying to find. For example, you might say, well, what is the minimum perturbation needed from a given input to make it mispredict, right? This is just an example. There can be many other kind of constraints, right? So that's the main kind of threat model, among many other stuff, of course, that had been a major driver of this line of work. And this has resulted in a really wide interest, a very exciting set of work from a lot of researchers, some of whom you will hear in today's workshop. Different ML tasks, different threat models, different kind of bounds, different kind of constraints, as I said, different types of robustness. Certain robustness guarantees are empirical. Certain stuff can be verified with proofs. So there's a very wide range of work that people have been doing. And again, as I said, you'll hear some of them in today's later sessions. So in terms of agenda, we have 2 sessions. In the first session, we have 1 keynote and 5 20-minute talks, and then we have a panel discussion. And in the second session, very similar, 1 keynote, 5 20-minute talk, and another panel discussion. So this is our agenda for today. And we have our website set up, so please visit that for further information. And with this, I think I would like to introduce today's first keynote speaker. David, are you all set from your end?
I sure am.
All right, thank you. So it's my great pleasure to introduce Professor David Wagner from UC Berkeley. Who's going to deliver today's first keynote. It's going to be on defense against adversarial examples. And Professor Wagner is a professor of computer science at the University of California at Berkeley. And he's known for discovering security vulnerabilities in cellular networks, 802.11 wireless networks, electronic voting systems, and many other widely deployed systems. And he currently studies the security of machine learning. So David, it's all yours now. Let me stop sharing.
Great. Good morning, everyone. All right. It's great to see you all. Thank you. Please feel free to interrupt me at any point with questions, or I'm glad to take questions and discussion at the end. So what I wanted to do today was to show you a few ideas about security and machine learning. I'll show you a few ideas from my group and a few problems maybe that some of you all will have some ideas on. So I want to start by talking a little bit about adversarial examples. And here is an example motivating scenario where attackers might be able to use adversarial examples to manipulate systems that use machine learning for decision making. And in this example, this is work from Sato et al., where they're looking at autonomous driving. And they identify patch attack where by putting a bit of covering up part of the road surface with a specially designed pattern, they can cause autonomous driving algorithms in their experiments to veer out of the lane. So when the road looks as normal as shown on the left, then the lane keeping algorithm keeps you right in the center of the lane. But then they showed in their attacks that when they apply this special road surface onto the road, then it fools the machine learning algorithm and causes the lane keeping algorithm to swerve out of the lane. All right, so this is an instance of a more general problem whenever we're using machine learning in a broader system to make decisions that may be safety or security critical. So I wanted to talk you through some defenses to adversarial examples and show you one idea from my group. So existing defenses, I have three favorites. The first defense is called adversarial training, and we defend against adversarial examples. Think of it like a biological analogy, that the way you prevent yourself from getting COVID is by getting vaccinated. In other words, we expose your immune system to synthetic attacks that hopefully are close enough to the real attacks that your immune system learns how to defend against the synthetic attacks, and therefore also protects you against real attacks. So at training time, we generate attacks in advance, and then we train on these attacked examples. A second direction is using generative models. I think this is a potentially promising direction in the long run, but in the short run, one challenge is that our generative models are not as good as our discriminative models. But the idea is, if you have an image, you check, can the generative model generate an image like this? And if not, then that's a sign that it might have been attacked. And finally, thirdly, is randomized smoothing is a third defense, where we add some random noise before we classify, and that turns out to smooth out the decision boundary to have less sharp corners. Okay, so I wanted to show you an idea that we looked at earlier this year that I call propose and verify. And it's motivated by ideas that we've seen in the security literature before. For instance, the P versus NP problem. When people believe that P is not equal to NP, one of the intuitions there is that we think that checking a proof is often easier than finding the mathematical proof in the first place. Or in the security world, proof carrying code is based on the intuition that checking, if someone gives you a proof that the code is safe, checking that proof is maybe easier or simpler than making code safe in the first place. Okay, so we're trying to apply this same idea to machine learning classifiers, and we were looking specifically at lane marker detection. Okay, so standard algorithms will take an image and they'll find the lane markers on the image, but they're not robust against attack. So they can be attacked. There are adversarial examples that will easily fool them. And so the scheme we're looking at called propose, then verify, because in our scheme, there's two stages. The first stage is that we use an ordinary machine learning model to come up with a proposal. This proposal is not trusted. So the machine learning model is not necessarily trustworthy. It will tell us where it thinks the lanes might be. Of course, it could have been fooled because it might be vulnerable to adversarial examples. So that's why we need the second stage. The second stage is a verifier to check whether the proposal appears to be correct. Okay, so the proposal identifies, I think this curve in the image indicates where the lane is. We then need to verify, does that appear to be correct? And for lane marker detection has the nice property that once you found the lanes, the appearance of a lane is relatively uniform. So to verify it, how do we verify? Well, we use another machine learning model, which sounds like it doesn't help. We've just fallen back to, again, needing a robust machine learning model. But the trick here is that if I point to on the image where I think a lane is, we can then crop that area out and straighten it into a line and put it into a canonical pose. And then that makes correctly identified lanes look pretty much like each other. And so then the problem of recognizing them becomes much simpler. So the verifier, that model, can actually be made fairly robust with adversarial training. Okay, so this is the propose and verify idea. And in the context of lane marker detection, let me show you how well it works. If you take an undefended neural network, it's completely attackable. Our scheme, when we evaluate against patched attacks, was able to detect 97% of the attacks. So less than 3% of the time is it possible to attack this without being detected by the verifier. But the cost is a false alarm rate of 4.5%. So 4.5% of the time, this will falsely say, I don't know what's going on. I can't verify the output of the machine learning classifier. So maybe not completely there for practical deployment yet, but this trade-off between false alarm rate and detection can be tuned. Okay, so challenge to all of you is, can we apply propose and verify in other contexts? Is it easier to check the output of a machine learning model if it gives us some evidence to justify its decision? I want to show you another idea from our group. Departing a little bit from adversarial examples, we've been looking at the use of machine learning classifiers in security classification. So trying to detect attacks on enterprise networks. And we've been looking at traditional anomaly detection. So in classical anomaly detection, like you might find in textbooks, the way we detect attacks on a computer network is that we come up with some model for the distribution of benign data. So maybe we train some machine learning model on historical data, which is assumed to be benign. And then given an event, given like a login attempt or something like that, we compute the probability, the likelihood of this under the distribution of the benign data. And if that likelihood is too low, if it's too anomalous for the distribution of benign data, then we raise an alert. Okay, super intuitive approach, I hope. Let me show you one of the shortcomings of this traditional anomaly detection. Let's suppose that the feature we're looking at is a single value only, just a single feature, just to simplify, that we're seeing an attempted login from some IP address. And what we do is we figure out number of past logins by across the entire enterprise of people trying to log in from this IP address. And then that number is our feature value. So it's you would sort of expect that this might be helpful for detecting attacks, that most people log in from machines that they've logged in from many other times before. So typically that feature value will be fairly high. And an attacker might be attacking from an entirely new IP address that's never been used to try to log into this network, so might have a low feature value. So you might imagine this feature would be discriminative. If we now use traditional anomaly detection, let me just show you some examples of how it would handle different values of this feature. So if you have the feature has a intermediate value, like, oh, there's been 20 past logins from this IP address, then that is not anomalous. On this PDF, that's a completely ordinary value. The probability of getting a feature value of 20 is fairly high, so the traditional techniques would not generate an alert. On the other hand, if you observe a feature value like 1, this is the first time anyone's logged in from this IP address, based on this distribution, that's very anomalous. That's very low likelihood. And so traditional schemes would alert because that's anomalous feature value, which is good. That's what we would like a scheme to do. It makes sense for a scheme to alert for this kind of rare event. But let me show one more example. Suppose you get a feature value that's very large, logging in from an IP address where it's been seen 500 times in the past. Well, according to this probability distribution, that is also anomalous. It's a very low likelihood that you'll see 500. And so traditional anomaly detection schemes will raise an alert because it's anomalous. Yet, from our eyes, that looks kind of silly, because if someone's logged in from that IP address 500 times before, that's not suspicious at all. That's just a really commonly used IP. So it's anomalous, but not suspicious. Okay, so what went wrong here is that the alert rule for traditional anomaly detection only looks at the likelihood according to the benign data distribution, but doesn't say anything about the distribution for attacks. And if you look at the theory for Bayesian decision making or Neyman Pearson lemma or any of these kind of standard methods, they tell you should actually be looking at the ratio of these likelihoods. And if that ratio is too small, then you should raise an alert. But the problem is we can estimate the distribution for benign data. We have lots of historical data, but it's not clear how to estimate the distribution for malicious data. I don't know what might that look like because I might be dealing with novel attacks that I've never seen before. So I don't know how to estimate that. So traditional anomaly detection says, oh, well, I don't know how to estimate it. I'm just going to assume it's constant. I'm going to ignore it and just throw it out of the equation, which theory says is wrong, but that's what we do to make a pragmatic scheme. And the cost of that, making a pragmatic scheme, is that it raises too many alerts. It raises alerts on events that are anomalous, but not suspicious from a security perspective. So I wanted to show you our solution that we used with a lot of success in recent work, called it DAS. And this idea, and this is based on the idea that in some contexts, I don't know how to characterize what feature values might arise from attacks, but what I do know is that smaller values are more suspicious and larger values are less suspicious, monotonically so. So the larger the value of this feature, the less likely that it comes from an attacker. The more logins I've seen from an IP address, the less likely that's to come from an attacker. So I can't tell you what the distribution is, but I can tell you it's monotonically decreasing. And under that assumption, it's then possible to come up with a reasonable scheme. And the scheme basically amounts to, instead of computing the probability of that specific value, you compute a tail probability, you compute an integral of all the values in the tail that are at least as suspicious as the observed value. Okay, so this then gives anomaly detection a measure of what is suspicious. So if I see a feature value given by the star here in the middle, like 20, then what DAS does is it computes this tail probability, the area of the yellow. That's a fairly large area. And so it would say no alert. If it sees a value of the feature that's very low, like 1, it computes the tail probability to the left of that. That's a tiny, tiny area. So it would say alert, which is good. We want it to alert on small feature values. Those are anomalous and suspicious. That's what we want it to alert on. And if we observe a feature value that's very large, like 500, then it will compute the tail probability of everything to the left. And that tail probability is like very close to 1. So it's very large. So it will not alert. And that's also good. That's what we want, because this is anomalous, but not suspicious, not indicative of an attack. Okay, so this is an idea I thought I would show you to improve anomaly detection in security settings. In the special case where you can characterize what attacks look like by a monotonic property on one of the feature values. And so my challenge to all of you is to invite you to think about, can we generalize this? Often human security experts have domain knowledge about what kinds of events are suspicious. In other words, would tend to make you think that you might be under attack. And it's not always as simple as something monotonic, that smaller values are more suspicious or larger values are more suspicious. So I think there's a challenge here for the field. How could we extract that information from human experts and build schemes that are aware of that information to improve how we do anomaly detection? Another challenge in this space is dealing with distribution shift or concept drift. And there's been some recent work that shows that this is a major challenge for anomaly detection, that there are a number of common causes of distribution shift, where I may be working with an ML model that has modeled the distribution, this straight line, based on past data. But in the past few weeks, something changed, and now the actual distribution, unbeknownst to me, looks like the dotted line. And now I'm using an incorrect model. And so this can cause a huge number of false alerts. And this is a major problem for systems in the wild as well. And so a challenge for the field to think about is how to deal with this kind of distribution shift. All right. I thought I would show you a potpourri of other ideas and problems. I'd love to get your thoughts and your discussion at the end of the talk. Here's another challenge that I don't know a solution to, but I wanted to show you not work from my group, but from others that I really admired and appreciate. Let's take autonomous driving. And let's say we want to use a machine learning model, but we want it to be sure that it's safe. It won't cause the car to crash. One of the challenges we've run into when we want to certify the safety of something using a machine learning model is that even if we achieve 99% accuracy, it's often very challenging, and even if we achieve perfect robustness against adversarial examples, which we don't know how to do today, even then, that's probably still not good enough, because it could potentially be unsafe the remaining 1% of the time. And techniques from the security world of certified robustness or formally verification of robustness don't help either, because they at best give us perfect robustness, but you still have models that are not 100% accurate. So some fraction of the time they'll be wrong, which means they might be unsafe. As a field, I'm not sure we really have any good solutions for dealing with this in terms of the machine learning model. Okay, so that's the first challenge. Second challenge is, it's actually worse than that. We need a lot better than 99% accuracy. If you look at an application like autonomous driving, then to do better than human drivers, we need a failure rate of less than something like 1 in 10 to the 8 hours of driving, which means something like less than 1 in 10 to the 12 frames of images or decisions, because you're probably making thousands or 10,000 decisions per hour. So that means you need, if you're going to use machine learning classifier, you need accuracy above 1 minus 10 to the minus 12. You need an error rate below 10 to the minus 12. How do you test that? How do you measure that? How do you certify that? How do you convince a regulator of that? How do you convince yourself of that? This seems almost incredibly intractable. I mean, the machine learning answer for measuring accuracy is we get ourselves a validation set, a labeled validation set. But if we want to try to measure accuracy to this level, we're going to need a validation set with more than 10 to the 12 examples. That's a lot of field data, and they all need to be labeled. Ouch. So that seems pretty infeasible or expensive, super expensive. Maybe you're thinking, well, we could use a simulator. We could use fuzz testing. We could use some kind of automatic test case generation. But now you have the challenge of how do you validate your simulator? Maybe there are rare cases that come up in the real world with probability 10 to the minus 6, but that your simulator is unable to generate because your simulator doesn't have perfect fidelity. And then you could be doing perfectly on the simulated data, but still not meet the accuracy goals. So this is another challenge that as a field, I feel like we don't really know how to meet. So what are we going to do about this? Well, let me show you one idea that I've read about in the literature. One idea suggests that we use 2 independent subsystems. Okay, so if we're thinking of autonomous driving perception, then maybe you've got one system that's using a camera and a vision model, and another that's using LiDAR and some kind of LiDAR model. Or if you're thinking about autonomous driving path planning and steering control, maybe you've got 2 independently designed algorithms and independently implemented, pieces of code. And then maybe a plausible approach is you try to validate that the error rate of each is less than 10 to the minus 6. So now that's maybe plausible that I can have a validation set that has 10 to the 6 examples and check each one to make sure it doesn't make any errors on that validation set. And now I believe that the error rate of each is below 10 to the minus 6. And then if the probability of failure of each of these 2 subsystems is independent, then that means the probability that they both fail is at most 1 in 10 to the 12th. So I can do some kind of a voting system on those 2. Or maybe I need 3 independent subsystems and I take a majority vote. Okay, so then I could plausibly get to a 10 to the minus 12 error rate if I could ensure that the failure events was independent. But unfortunately, this assumption that errors are independent is a really, really strong assumption, and it's probably pretty dubious in practice. There are probably scenarios that have an increased likelihood that cause both your camera and your LiDAR to fail. Or there may be, we know from past work on software reliability that you give the same task to 2 programmers and they independently solve it. And there are some kind of bugs that's really easy for people to make that might end up in both implementations. So I think this is kind of a lie. So we don't really have a good approach. I wanted to show you one work from the safety and formal verification community that I haven't figured out how to apply here in the machine learning world, but I wanted to show it to you to see if maybe one of you can come up with either a solution to this challenge or a way to apply some ideas from the safety community that I really like. So there's a beautiful line of work from Bev Littlewood and Rushby that suggests a way to come up with a variant of this 2 independent subsystems that actually works and is kind of reasonable assumptions. And the idea they have is that we're going to have 2 subsystems. One of them might occasionally make errors. So maybe it's using machine learning. And the other one, we're going to design that we hope it's perfect. And we're going to try to make it perfect and verify that it's perfect using, for instance, software verification. And then we're going to do some voting between the two, like only take an action if both of them agree or something like that. And they prove a theorem that says, if you can validate, like using testing and field data, that the first subsystem has an error rate of less than 1 in 10 to the 6th. And the second, this one we're hoping is perfect, has a probability of being not perfect of less than 1 in 10 to the 6th. Then you can actually reasonably obtain a 1 in 10 to the 12th failure probability for the whole system. So this is still fairly challenging. It's fairly challenging to build a machine learning model that has an error rate of less than 1 in 10 to the 6th. We don't really know how to do that for most tasks, but it's plausible that we could, at least if we achieve that, validate that with a validation set of 10 to the 6th examples. That sounds within our reach. And it's very challenging to build a software system that that we think is perfect with a probability that there is any bug whatsoever is less than 1 in a million. That's very challenging, but it's sort of almost plausible that it might be within reach, that we come up with a formal specification of what it means to correctly, I don't know, path plan for lane keeping, and algorithms that we can formally verify correct, and then apply software verification to verify that we have a correct implementation of those algorithms. And then what does this probability mean? It means we need, for instance, the probability that there's a bug in our software verification tools has to be less than 1 in a million. That's really challenging, but maybe it's plausibly achievable. Okay, so if we could come up with a way to formulate our tasks so that we might be able to come up with something that's plausibly perfect and can apply formal verification techniques to, then we might be able to kind of use a voting between two subsystems to plausibly achieve a 10 to the minus 12 error rate. Now, I don't know exactly how to apply that to any realistic scenario. For instance, for perception, detecting lane markers or road signs or pedestrians, I don't know how we would get a plausibly perfect subsystem. But maybe for some simple cases like lane keeping, the path planning part of that, maybe we could apply these techniques. You might, if you enjoy this thing, you might also enjoy reading papers on responsibility sensitive safety from Intel and Mobileye. I'll show you another direction we looked at in our group and had only modest success with, and maybe you'll have some ideas how to take this further. So I've been very interested in patch attacks. I think patch attacks are an important problem for the community of adversarial machine learning, folks working on adversarial examples. They're an attack that I think is important because it's plausibly physically realizable. It's pretty plausible that you might be able to attack a machine learning classifier by placing a sticker on something. If you were to drive around, you'll see people putting stickers on road signs, okay? And there's been past work showing that that's enough to fool a machine learning classifier. You put a sticker on a road sign, you can make the classifier think that stop sign, make it think it's a speed limit 55 sign. Put a sticker on an object, you can fool the object detection into not realizing this is the person and getting confused, thinking that rifle is actually a harmless turtle and so on. Okay, so patch attacks are, I think, are an important, well-motivated threat model and to work on figuring out how to make our models robust against. And one of the things that, if you've been paying attention to computer vision and machine learning over the past year or two, you've probably heard about vision transformers. It's an exciting new direction, improving on our models for handling images. ResNet was once the best. Now the models to beat are vision transformers, which apply techniques from natural language processing to vision, and they're achieving state-of-the-art accuracy, better than any other models on many vision tasks. The way they work it's kind of embarrassingly simple. They divide up an image into 16 by 16 patches, and then they treat the image as a sequence of patches, and then they do some kind of sequential processing on that, same way that we do natural language processing of sequence of words, and now it's a sequence of patches. Okay. Well, you might be noticing that that's patch-based processing, which got me thinking, can we use that somehow? Patch attacks are attacking one patch. This is processing each patch one at a time and then combining them somehow. So here's how vision transformers, the architecture of vision transformers look, stolen from seminal paper on this. Basically, they split the image up into small patches. They then, for each patch, use some model, some neural network to analyze the patch and output a vector that's a representation of that patch. So they feed the patch through a neural network. And then they do this transformer operation, which basically does this processing on each patch and then combines them in some way using this self-attention mechanism. And you can think the self-attention mechanism is it figures out for each patch which other patches are most important, and then does some kind of like a weighted sum or weighted average of values from the other patches that it thinks are relevant or important. Now, as you think about this doing a weighted average, for those of you who are familiar with robust statistics, you know that an average is an example of an aggregation mechanism that is not robust against outliers. So a single faulty outlier, single faulty value can arbitrarily skew your average, which sounds like a bad thing in the context of robustness of this model. A single maliciously attacked patch in the input image could cause a single value here to be messed up. So after the first stage of this processing, it actually looks like robustness, we might have a hope for robustness because one bad patch in the image could only mess up one of these intermediate values. But then when we do the attention, that one bad value could arbitrarily affect all the averages and really skew them off enormously. So what we propose, we looked at a scheme for trying to build robust self-attention, where instead of using the average, intuitively, we try to use some kind of a aggregation that is robust against outliers. And specifically, the particular scheme that we've experimented with that's done the best in our experiments is that we try to detect outliers among these values, look for, is there one outlier, and then throw away outliers and do the aggregation on the remaining ones. And the intuition is if there's one patch, one of these patches that has had a sticker, it's been corrupted, then there's one of these intermediate values that will be bad, but then that will be an outlier and so be ignored by the robust self-attention and shouldn't affect the output too much. So does it work? I'll show you experiments. Some, it works a little bit, it helps a little bit, but not a ton, not a ton. So one of the state-of-the-art methods for defense against patch attacks is a clipped bagnet, which uses an architecture that's specifically designed to be robust against patch attacks. And here we did an evaluation on ImageNet, 100 class subset of ImageNet with 10 by 10 pixel patches, so a fairly small patch attack. If you are familiar with accuracy numbers for ImageNet, you'll notice a clipped bagnet has a clean accuracy on unattacked images that's quite a bit lower than undefended networks. But it does get a robust accuracy of about a little over 50%. So that's something. If you take a ResNet and then you do adversarial training, it turns out adversarial training is a remarkably good, surprisingly good baseline for defense against patch attacks in our experiments on ImageNet. In fact, it even improved the clean accuracy compared to an undefended network a little bit. And with a ResNet, we get almost 75% robust accuracy and a very good clean accuracy, 91%. So that's pretty good. And with the vision transformer, you can get a little bit better clean accuracy, but for some reason we had a hard time successfully adversarially training. It was not as good as a ResNet. I think maybe we don't have the best training procedures yet for vision transformers or something. So there's a first challenge for you. Figure out if we can have better ways to engineer adversarial training with vision transformers. And then when we applied our robust aggregation mechanism, we found that we paid a little bit of a price in clean accuracy, but we got a significant boost in adversarial accuracy, robust accuracy, when there is a small patch present. So this is at least a plausibility argument that it might be possible to use something about this patch-based architecture of vision transformers to improve our robustness against patch attacks. And I'll challenge you all to see if you can come up with a better mechanism. It felt like maybe it'll be possible to do even better, but we couldn't figure out how to do better. We've been looking at generative classifiers for better security, and I think I'm just going to skip past all this. If you're interested in it, you can look at a PhD thesis of my student Anju, where he was found some interesting work on using generative models to try to improve security against adversarial examples. Lastly, I'll mention just some stuff we've looked at with randomized smoothing. Standard randomized smoothing adds Gaussian noise, IID Gaussian noise to every pixel, and then classifies on this noised up image, which sounds a little crazy. You make the image worse before you classify, but then you can prove that this helps improve adversarial robustness intuitively, because the classifier can't have super sharp curves in its decision boundary. It kind of smooths out the decision boundary. So what we experimented with is, well, Gaussian noise is just one form of noise you could add to image. What if we add other kinds of noise that we expect could occur in practice? So like blur or color jitter or random cropping, and then classify. Okay, so in fact, we're not the first to suggest this. There's a previous paper called BART that proposed something like this. And what we found is that if you do this, this does seem to help improve adversarial robustness compared to having no noise. First of all, we found that BART, a previous paper that had proposed something like this, was much less secure than the authors had thought because they didn't have the best attacks. But if you come up with better attacks, then we think that this has maybe some potential. The line you could compare would be comparing this to adversarial training, where you can see that with this random, noising up the image using many random transformations, the robustness that we obtained on a 10 class ImageNet subset was not as good as achievable with adversarial training, but it gave a significantly better clean accuracy. So in the trade-off between clean accuracy and robust accuracy, clean accuracy is more important to you, then maybe the scheme might have something like this might be worth exploring more. We've also looked at another direction in randomized smoothing. If you're familiar with randomized smoothing, and then here's a visual model of how randomized smoothing works. Suppose the decision boundary is this sharp isthmus, as shown here, this peninsula here. So we have two classes, the green class and the blue class. Then a classifier with this shape of decision boundary is vulnerable to adversarial examples. If you have a data point X at the black dot there, then it will be classified as blue, but a very small change to X can cause it to be classified as green. Thus, adversarial examples exist for this classifier. What randomized smoothing does to deal with this problem is it adds random noise to X. So it's like randomly choosing points within this disk shown by the dotted line here then classifying those random points. And if you do that for many random points, you'll find that more of them are classified as green than as blue. And then if you take a majority vote, then the classifier will classify that as green. So actually, an ordinary classifier would classify X as blue, but the randomized smoothing one would classify it as green. And you can see that small changes to X shift the disk only a little bit, so they don't change the majority. The majority is still green, so the smoothed one is secure against adversarial examples. That's the intuition behind randomized smoothing. So a direction a problem with randomized smoothing is that it requires this majority vote of many samples. You take 1,000 noised up versions of X, you classify all of them, and then you take a majority vote. So your classifier just got 1,000 times slower. So a direction we've looked at is to use variational methods from variational autoencoders and combine that with randomized smoothing. So the idea is that we imagine making a small change to X. So we consider an experiment where we allow a small change to X to try to maximize how much this is classified as blue. And then we separately make a small change to X to maximize how much this is classified as green. This is trying to rectify it under one hypothesis that maybe this was an attacked version of some blue sample, and the other hypothesis is an attacked version of some green sample. And we see how strongly each of those get classified as blue or as green. And in this case, a small shift can make this be classified as 100% green. The small shift in the blue direction can only make it classified as like 30% blue. So this is a much stronger green, and so you should classify this as green. So then you can use variational methods, the elbow, lower bound, and some gradient descent to try to find what direction to go. And if you're interested in this, you can look at Anju's thesis. Does it work? It's interesting it's unclear whether it gives you any advantage on large perturbations, but on very small perturbations, we found that this gave better empirical robustness than ordinary randomized smoothing. So I don't know whether this is effective or a good idea, but at least some early indications that maybe there's some interesting opportunities to apply ideas from variational methods to improve randomized smoothing. Okay, so thanks so much for listening. I wanted to show you just a random assortment of ideas and hopefully things to get you thinking. And I very much appreciate your time and would welcome any discussion or questions if we have time for that.
Okay. So thank you, David, for giving us this great talk. So this is very nice talk and very inspiring. So I'm Huan, and I will be hosting the rest of the morning session. So let me first ask if there are any questions from the audience. So if you have a question, because there are many participants, can you use the raise your hand feature of Zoom, and I can ask you to unmute, so we won't complete. So you can, there's a reactions button on the bottom of Zoom. You can click that and you have raise a hand feature. And I can see you raising your hand. So okay, I'm seeing a question here from Suman. So Suman, maybe you can ask your question now.
Sure, yeah, I want to ask one quick thing about the automotive examples that David gave. So one thing I was wondering about, David, is there have been several works, right, who talk about basically using multimodality of the driving inputs, right? For example, imagine you have more sensors, right? I mean, LiDAR and camera, the examples you were giving are two, right? But then imagine we change the road, we add more stuff, right? So I was wondering that, 10 raised to minus 12 number that you gave, right? And you're absolutely right. It seems like an almost impossible task to achieve. I was wondering about your thoughts of like, can that at least make the problem a bit more tractable?
I don't feel qualified to answer that. I don't feel like I know enough about it. It seems promising, and the biggest worry that I have is this independence assumption, the risk of common mode failure, and I don't know how to assess that. So I'm hoping maybe others will have more insight onto that, how much I should worry about it.
And just to follow up, I mean, I completely agree with the the futility, or rather the risk of making the independence assumption, right? Especially at the presence of attacker, it seems even worse, right? If I understand it correctly, right? Because if it's natural, maybe we can at least isolate, we can do something, right? I mean, do you think that makes sense?
Yeah. Yeah, I think it's interesting to imagine, though, it might be interesting, multimodality might be interesting to look at attacks. For instance, if we think about specific attacks like the sticker attack, where an attacker puts a sticker on an object or sticks a sign on the side of the road or something like that, those stickers are probably going to be flat. And if we had good enough depth sensing, maybe we're not there yet, but maybe in the future, if you have fine enough resolution depth sensing, maybe it could detect that this part is flat. And if the model was, thinking that this is, a car, it should have some depth to it. It's not flat. But then if the depth thing says it's flat, then that might be a basis for suspicion of, oh, I'm under attack. The shape that I'm inferring from the visual doesn't match the depth sensing that I'm getting from the depth sensors. So at least against some kinds of attacks, I think multimodality might be really, really interesting as a possible defense.
Thank you.
Any other questions from the audience? So I have a question for David. So David has studied many practical systems like cellular networks and wireless network, and also electronic voting systems. But as you mentioned in your talk, like for machine learning, like the failure is really hard to get even below 1% failure rate. But for building a really robust system, for example, if we are building an aircraft, we probably want a very low failure rate. And we know that people are building those aircraft today, and people can build this actually very highly reliable system. So do you think like today's machine learning are still not good enough for those tasks? Because it's really hard even to get maybe 1% error rate compared to maybe using some other traditional method where you can actually build very reliable systems like aircraft. Do you think we still have like a really large gap here for machine learning?
It does seem like we have a gap, but I would be interested to hear perspectives from those in industry, because maybe they're further along than I realize. One thing that I found that's interesting and powerful from the electronic voting world and other parts of safety is the notion of having a fail-safe interlock, or two kinds of subsystems. You've got one subsystem that you believe gives you the best reactor control or the most comfort in your driving. And then you have a second one that understands the safety envelope and is constantly monitoring to see if you've exited the safety envelope. And it's a very simple subsystem that's not going to give you optimal control, but will ensure you stay within the safety envelope. So for instance, in electronic voting, one version of that is we have the complex electronic voting system, but then as a fail-safe, we have a paper trail that can be compared against the electronic. And that has it's a fairly safe mechanism. It's not, amenable to hacking. You can't, once the votes are printed on paper and stored, there's no hack that's going to change all those printed records. So yeah. I think it's interesting to look for those kinds of system level defenses in this context.
Yeah, I think from that perspective, so unlike other existing system like electronic voting system, machine learning is usually much more complicated, and it's usually just like a black box. and it's really to study the behavior of the system, and it's really sometimes hard to propose some fail-safe mechanism that can be helpful, especially if you fail-safe system is also a machine learning system. That system can fail as well. So I think it's definitely a quite challenging problem we have here. Yeah, so thank you for answering my question. Are there any new questions from the participants? Okay, I'm seeing a question from Chen Hong. Chen Hong, can you unmute and ask your question?
So can you hear me now?
Yeah, we can hear you.
Okay, so very good. So thanks for this very nice talk. So in terms of this 10 to the minus 12 or 10 to the minus 6, so just have this, I think that one thing that comes to my mind is about the definition of accuracy, because accuracy doesn't really imply safety, right? Because for example, actually, if we think about safety, the most important thing is that the bounding box actually surrounds the guy. And then in that sense, you don't really need the accuracy. So I think that one thing that bothers me is a little bit is the way how people talk about. I think that when we talk about safety, for example, we actually have a much more relaxed way, just like how we drive. Actually, we don't really exactly position the other people's in a very, for example, X meters in front of it or something like the bounding box to be extremely tight. And so I think the one thing that, for example, when we're talking about all these kind of safety aspects, I would say that the way how we define the metrics, they should be sort of like influenced by safety, but not really, for example, governed by the way how ML people directly value it. And I just want to know a little bit about your thoughts on this. Thank you.
Thank you. I was hoping to come here and learn from other folks, so I appreciate maybe you could teach me more about that. Thank you.
Yeah, I think it's a very interesting question. So yeah, so it partly kind of depends on the application. Like for autonomous driving, maybe yeah. So some like for example in autonomous driving, if you because the system is always taking images from a video or something like that. So you're processing the things for every frame. So you're really just making a mistake after you're making a mistake for a few frames that can actually trigger a bad action. For example, if you segmentation or whatever is just wrong for one frame, maybe that's just gonna be okay because it's not gonna affect the outcome of the system. But if you're making something, if you're for example, if you're driving towards something, if you're not seeing an obstacle for one frame, maybe that's okay. But if you're not seeing it for many frames, maybe that's causing a trouble thing. So the error rate of making error rate and the failure rate is definitely two different things here in this system. That's definitely a very good point. But I think it quite depends on the application and the specific problem people are looking at. So yeah, it's hard to have a definitive answer here. So other people having opinions on this question? Or any people have more questions for David? Yeah, maybe I can ask another question. So David, you mentioned that you can define the patch attack on vision transformers by inspired by the special structure of the vision transformers, because they also work in a similar manner as the patch attack. They also divide the image into patches and classify the image based on the patches, so you can actually fix the self-attention module for this architecture. So do you think it is more promising to design a machine learning model from the perspective of attacks or security by changing its architecture or whatever, just like what you did for the vision transformer? It's to use an architecture that is more suitable for so for defending this kind of attacks. Do you think that's a promising direction?
I don't know. I think it's interesting to explore. There's been some real advances in defending against patch attacks. By improving the architecture, and so some beautiful papers from the Princeton group, for instance. I'm unsure. There's so much engineering on neural network architectures from the machine learning community that it would be really nice if we could just use their existing architectures and then apply adversarial training. And so far, what we found is that it's hard to beat adversarial training, and that we weren't able to do that much better. So one possible lesson you could take from our experiment is adjusting the architecture based on the threat model might be promising, but another possible takeaway is just use adversarial training. That will let you borrow the state-of-the-art architectures, and maybe it's pretty close to the best, or maybe it's even better because you take advantage of all the engineering that others have done. So I don't know the answer. I think it's worth exploring more because it's intriguing that we have this convergence where model architectures that seem to be the best for state-of-the-art clean accuracy also might give us an opportunity for design security by design against patch attacks, but I don't know what's going to turn out to be the best in the long run.
Yeah, I think I also saw papers that were proposing like certified defense for patch attack, and some of them I think already mentioned in your talk, like the backnet. There's a kind of design the network with just each like using an ensemble network, and each one only looking at a small patch of image, and you can actually do some certification in that sense by assuming the attacker can only change at most one features or something like that. I think it's definitely a promising direction for people to further look at. Okay, cool. Any other questions from the audience? We still have maybe time for one or two more questions. Okay, there's a question from Eric. Eric, you can unmute yourself and ask a question.
Hi, David. That was a nice talk. I just had a question about one of the challenges that you brought up, which is the 1% error rate. Right, and this seems like sort of a fundamental challenge for sort of not just like security and verification, but just like machine learning in general. And so, maybe it's not possible at all for machine learning in general to ever achieve less than 1% error rates. And so, if this is almost something that we virtually never see in machine learning models. And so if we assume that we can't ever get this 1% error rates, what would you think is maybe the second best option?
I kind of came here hoping that maybe someone here would have some idea what to do about that, because I'm kind of at a loss. I mean, one natural thing one could say would be to somehow design your system so that you're not relying on the ML for safety. But I don't know how to do that. So I wish I had an answer for you. I kind of came here selfishly hoping that someone else would have some ideas. It's a great question. Thank you so much for raising this.
Yeah, for me, I'm thinking like using independent systems, like David mentioned, is definitely a promising direction. But the challenge in machine learning models is, they are often not that independent. Like we saw many papers on using like ensemble models to tackle the adversarial defense problem, like training a few models. I want to increase the diversity of the models, and I hope the models are independent and so on. But usually people found that if you attack the models using a stronger attacks and more fancy attacks, all this method will simply break down and really doesn't doesn't work here. So I can see, like, if you're using an ensemble, maybe it increases the robustness by a little bit. Maybe you increase the PD accuracy by a few %, but it's definitely not gonna solve this problem. So I think definitely it's a challenging open problem. So Eric, what do you think?
Yeah, well, I think maybe David's kind of right. We all sort of maybe are coming here, maybe looking,
Yeah.
hoping that somebody else has some kind of insight or answer to this question. But I think probably something that David brought up is probably also very key here, which is that we probably do need to maybe connect more with some industry people to see what is really the second best option, because maybe machine learning really isn't the end all sort of answer here.
Yeah. Cool. So we will have a panel discussion. We'll have actually two panels today. So one in the morning and one in the afternoon. And David will also be joining the afternoon session. So if you want to see more opinions from more people, you can join our panel discussion session in the afternoon. And we hope we have invited several experts from different fields, and we hope we can hear different opinions from more people. Okay, so any more questions?
Oh, I have a quick comment about the topic we discussed before.
Cool.
So I feel like maybe, yeah, as David mentioned before, like maybe you can have two independent perfect models that works really well, so that we can cut down the error rates that's required to make the whole system perform well. So if that means that we can actually split the whole task into many different small tasks, like each is a very simple tasks, so that we can combine with some engineering logic, so that we can make sure that each of very small tasks, the model is working really well, and we can combine them together, so that overall, we can make the whole system works much better and verified as a whole. So is that the correct direction that you think maybe you can go, or we can still investigate to make the model more powerful for fit for each task?
Yeah, that's a great opinion. I think when people are building very complicated systems like aircraft, they do build each part separately and make sure each part are highly reliable to make sure the entire system is.
So yeah, if we want to make the model to have less than 1% of the error rate, maybe it's because the task is too difficult for the model. If the task is simple enough, so that the model can totally handle, then maybe 100% accuracy is also possible, right?
Yeah. Yeah. Okay. David, do you have more comments on this?
That's really interesting. I hope we'll be able to continue this discussion.
Okay. Yeah, cool. I think we can continue the discussion during the panel session this afternoon. And thank you, David, for giving this great talk. And really appreciate the talk, and it's really inspiring and stimulate a lot of our discussions. So thank you so much, David. And we'll now move to the next speaker. So let me share my screen with speaker information. Okay, so we're now moving to the first short talk this morning from Patrick Henriksen from Imperial College London. So Patrick is a PhD student in the verification of autonomous systems group at Imperial College London. His research revolves around formal verification of neural networks. Patrick's proposed a new novel method for verification of neural networks and created the VeriNet toolkit. The toolkit won second place in the verification of neural network computation 2021. His current research focuses on further developing the VeriNet toolkit and related topics such as repair of neural networks. So today, Patrick will introduce the VeriNet toolkit and the algorithms used inside the toolkit for neural network verification in our workshops. So let's welcome Patrick. So Patrick, you can start sharing your screen now.
Yes, thank you for the introduction. Let's see if I can get my screen up. Can everyone see my screen?
Yeah, I can see your screen.
Yeah, okay. Yeah, so I'm Patrick, and I'll be presenting our work on VeriNet, which is a symbolic interval propagation-based approach for formal verification of neural networks. And the work from this presentation is done by me and my supervisor, Alessio Lemoscio, and we're both based at the Verification of Autonomous Systems group at Imperial College London. So the VeriNet algorithm is a complete verification algorithm for neural networks. And the implementation won second place at the second International Verification of Neural Networks competition. VeriNet supports most common feed-forward network operations and architectures, including ReLU sigmoid 10H activation functions, fully connected convolutional batch normalization, pooling, reshape, transpose, and more layer types, and also residual connections. And relevant papers are these two, so deep split and efficient splitting method for neural network verification via indirect effect analysis, and efficient neural network verification via adaptive refinement and adversarial search. Before we go into the algorithm, I'll just present or formalize the verification problem a little bit. And what we consider here is a problem comprised of three inputs, so a feed-forward neural network, a set of box constraints on a network's input, and a set of linear constraints on a network's output. And given these three inputs, the verification problem is to determine whether the output of the network satisfies the output constraints for all inputs satisfying the input constraints. Let's start by giving a high-level overview of the algorithm. And in the first step, we create an abstraction of the neural network. And we do this using two versions of symbolic interval propagation, namely error-based symbolic interval propagation and reversed symbolic interval propagation. And as part of this symbolic interval, as part of this abstraction, we have also derived optimal linear relaxations for sigmoidal activation functions. After creating the abstraction, we pass this to a verification phase, where we encode the verification problem and the abstraction into a LP solver. And then we try to determine whether the network is robust or not robust for the given verification theory by solving the related LP problem. However, due to the overestimation of the abstraction, this part may fail, and we may get what we call a spurious counterexample. So a counterexample with respect to the abstraction, but not with respect to the underlying network. And whenever we get that, we use a novel adversarial search in an attempt to locate real counterexamples. I'll also talk a little bit later about the LP encodings we use here. If the verification phase still fails, then we proceed to a refinement phase, where we split the input to a node in the network and thus create two new, stronger constrained subproblems. And both of these problems are then restarted from the abstraction phase. In order to determine which node to split, we use a analysis we call direct and indirect effect analysis. So I'll talk about more all of this in more detail now. So first, we'll start with the abstraction and cover a little more details here. And as I mentioned, we use symbolic interpropagation. This is illustrated on the top left here. I won't cover all the details on that because there is a lot of literature on it. But the main idea is that you start with some bounds on the input of the neural network and then propagate these lower and upper bounds for each node throughout the network to get some bounds on the output of the network. This is quite straightforward for normal layers, for fully connected or convolutional layers. However, for nonlinearities, and in particular activation functions, we need a linear relaxation. For the ReLU node, this is illustrated on the top right. So instead of propagating bounds through the ReLU activation itself, we propagate the upper bound through the upper relaxation illustrated in red here, and the lower bound through the lower relaxation illustrated in blue. Now, there exists a lot of variants of this symbolic interpropagation, and we use a combination of two of them. First, we use error-based symbolic interpropagation, which propagates all equations, all bounds through the lower relaxation always, and upper relaxations, or the impact of upper relaxations, are tracked via concrete error values. So we get one of these error values for each node in the network. We also use reverse symbolic interpropagation, which introduces bounding equations in the final layer and substitute the variables of these equations layer by layer until we reach the input layer. Typically, RSIP, so the reverse symbolic interpropagation, is more precise than the error-based one. However, the error values from ESIP are particularly well suited for analysis, as we'll see later. We first perform a pass of RSIP, and then the bounds from RSIP are used to augment the ESIP phase. This produces precise relaxations that are also suitable for the LP encodings and effect analysis, which we'll cover in more detail later. Before we proceed, I want to say a few words on how to relax sigmoids. ReLUs are covered a lot in literature already, but sigmoids a little less. And as part of our work, we derived what we call optimal relaxations for sigmoid and 10H activation functions. And they're optimal in the sense that they minimize the area between the relaxation and the actual activation function. And basically, we've done this by identifying three possibilities, depending on the input bounds to the sigmoid. In the figures, they're marked as ZL and ZU, so the lower and upper bound. The first case is when the line intercepting both endpoints is a valid relaxation. We've shown that this is also the optimal relaxation. For the second case, we've determined an analytical expression for a ZT such that if the tangent at ZT is a valid relaxation, then it is the optimal one. And in the third case, we determined that if neither of the two previous ones are optimal, then the optimal one is a tangent at some ZT star, which we can't find analytically, but we have proposed an efficient method for approximating this ZT star. So having covered a little bit about the abstraction of the network, we now proceed to how we actually do the verification part. And to do the verification, the bounds from the symbolic interpropagation and the negated verification problem are encoded into an LP cell. Since we encode the negated verification problem, we know that if the LP call is unsatisfiable, then the verification problem is robust. Otherwise, the assignment from the LP call is a potential counterexample. Succinct LP encodings usually lead to efficient resolutions of the problem, and of particular importance are the encodings of node splits, which we will come back to a little bit later. If the LP solver returns an assignment, this may be a counterexample, but it may also be a spurious counterexample. Whenever we get a spurious counterexample, we use this in an adversarial search. So the search is gradient-based, and it's quite similar to a PGD attack. However, the difference here is that it's initialized at spurious counterexamples. And back when we introduced this in our first paper, we measured speedups of several orders of magnitude for not robust cases when compared to state-of-the-art approaches for verification at the time. But these days, most state-of-the-art verification algorithms have something similar themselves. So the next step is when further verification fails. So when this verification phase does not find a counterexample and also can prove robustness, we proceed to refining the abstraction. And refinement is on a high level performed by creating two new branches and splitting a node into two subdomains, one subdomain in each branch. The splitting, of course, introduces an exponential complexity since we are creating two new branches every time we split. Thus, it's important to find nodes to split that have a significant impact on the abstraction. To do so, we use a node splitting score function to evaluate the effect of splitting a particular node. We also use a new LP encoding for splits that's more succinct than previous encodings. We'll start by discussing the splitting score a little bit. And we calculate or estimate the effect of splitting a node via we assume that it has two separate effects that we estimate. First of all, we have the direct effect, which is the impact on the network's output bounds from splitting the node, given that everything else stays equal. And with everything else, we in particular mean that the relaxations of all the nodes stay equal. Secondly, we have the indirect effect, which is the effect that when we split a node early in the network, the bounds of all succeeding nodes also change during symbolic interpolation, and thus their relaxations change. So we define the splitting score to be the sum of these two effects. So the question is, how do we calculate or how do we estimate this splitting score? And this is where the error values we mentioned earlier from Hsieh come in. For each node in the network, Hsieh produces a linear equation Q of x and errors epsilon n, where n is an enumeration of all the nodes in the network. So each node produces one error value. Q of x is the pre-activation value at a given node, given that all activation functions in the network have been replaced by the lower relaxation. Remember, in Hsieh, we propagated all the bounds through the lower relaxations. Epsilon of n indicates how much Q of x changes if the lower relaxation at node n is substituted by its upper relaxation. Thus, we actually see that epsilon n is a very good measurement of, in some sense, the sensitivity of the bounds to the relaxation of a node. And we use this directly to estimate the direct effect. And then we can recursively estimate the indirect effect for a node I as the sum of the direct effects node I has on other nodes in the network, multiplied by their corresponding total effect on the output of or the bounds at the output of the network. Finally, the node with the largest score is selected for splitting, as we have estimated that this has the largest effect on the output bounds of the network. The split constraints also make use of the error values from Hsieh, and we encode a split as Q of x plus the sum of some sigma n multiplied by the epsilon n's. And here, sigma n is constrained to be in 0, 1. And remember, adding epsilon n was thus, can be interpreted as changing from the lower relaxation to the upper relaxation at node n. Thus, when sigma n is 0, we can interpret it as the node n operating at its lower relaxation. And when it's 1, we can interpret it as it's operating at its upper relaxation. Now, by sharing these sigma n's among all constraints in the LP problem, we capture the dependencies that each node should operate at its either lower or upper relaxation in all constraints. This is in contrast to previous encodings, which could technically mix lower and upper relaxations for the same node in different constraints. So in summary, we start by creating an abstraction of the network. And here we use ESIP and RSIP. And we also introduced optimal sigmoid relaxations. The abstraction is passed to the verification phase, which attempts to solve the problem, and it uses, among other things, adversarial search and succinct IP encodings. And whenever the verification phase fails, we go to the refinement phase, where we split the input of a node into two and restart both the new problems from the abstraction phase. So very quickly about some experimental results. As we already mentioned, Raghunathan won the second place in the VNNCon, and it was also the only toolkit in top 4 that did not use GPUs. And it has been tested and shown to work on networks with at least hundreds of thousands of nodes, and in some special cases, we run it on networks with a few million nodes. That was all I had. Thank you for having me. Any questions?
Thank you, Patrick, for the great talk. So now we have time to take 2 questions from the audience. So you can raise your hand on Zoom if you have questions. So before people have a question, I have a question for Patrick. So what is the most important factor for the success of VeriNet? Is that because you introduced a few things like optimal relaxation for like sigmoid, and also you mentioned you have a better splitting score considering the direct and indirect impact of splitting. So what do you think is the most important factor that lead to the success of VeriNet compared to other existing verifiers?
So VeriNet is comprised of 2 papers. In the first paper, what set us apart was this adversarial search, which led to a huge speed up. In the second paper, which is newer, I would say that what sets us mostly apart is the splitting, estimating the splitting score, so determine the right node to split. And I think in general, focusing on the refinement phase and focusing on more succinct relaxations will lead to the biggest results, because we're kind of reducing the problem of the exponential complexity by focusing on those.
Yeah, so do you think the refinement or the splitting phase is the most important thing for verification for most models?
So I think a refinement, a good refinement phase and a good abstraction is kind of 2 different sides of the same problem, because obviously with a good abstraction, you may not even need a refinement phase. So I think both of those 2 are important for scalability of the verification.
Yeah, because they're like there's kind of a trade-off here. Like you can use a stronger method for computing the bounds, and you can also spend more time on doing the splitting and using the cheaper method to compute the bounds. So there's kind of trade-off here, right? So
yeah, there absolutely is.
Yeah. So do you think like how to balance between the 2 things here?
Yeah. So I think in the future, I would be interested in seeing more methods that try to use stronger abstractions, such as, for example, MIL or semi-definite programming on subsets of the network. Maybe identify some parts of the network that are more important to relax succinctly.
Yeah, that's a very promising direction. Yeah, thank you for answering my questions. Are there any other questions from the audience? Okay, there's a question from Han. So you can.
So about the relaxation phase, I saw, so for instance, for the ReLU relaxation, you had that parallelogram. And I saw some other papers using something where they try to minimize the area in that phase instead. So the lower bound is sometimes, so yeah, so in this phase, like some papers try to minimize the area by having choosing different slopes for the lower bound. And is that something that you could have changed and had better results? Or
yeah, So actually, the ESIP algorithm requires parallel realizations. However, the RSIP algorithm does not. So we do actually use different realizations in the RSIP part, and that's also one of the main reasons that it produces more succinct bounds. If you run ESIP and RSIP both with parallel bounds, they're very similar in the results they produce. I think they may even be mathematically equivalent, but I'm not sure on that one. So yes, that's a very good point. This is not necessarily the optimal Rayleigh realization. We use others too in the end.
Okay. Okay. So you said the AC phase requires it to be parallelogram, right?
Yeah.
Okay. Okay. Thank you.
Okay, cool. Thank you for all the questions, and let's thank the speaker again. Thank you, Patrick, for giving this great talk, and we'll move to the next speaker. So the next speaker is Maksym Andrichenko. Maksym is a third-year PhD student in computer science at EPFL in Switzerland. His research mainly focused on how to make machine learning algorithms adversarially robust and improve their reliability. And his interest in improving robustness evaluation standards and understanding the effect of adversarial robustness on other tasks as well. Maksym has co-authored 7 papers at major machine learning and computer vision conferences, which has been cited more than 900 times. Today, Maksym is going to introduce RobustBench, a standardized adversarial robustness benchmark in our workshop. So Maksym, you can start sharing your screen now.
Okay, thanks a lot. I will share my screen now. Okay, can you see it?
Yes.
Okay, perfect. Okay, so hello everyone. My name is Maksym, and I'm going to present our work, which is called RobustBench, Standardized Adversarial Robustness Benchmark, which has been recently published at this year NAIRIP's Datasets and Benchmarks track. And this is joint work with Francesco Croce, Vikash Sevak, Eduardo De Benedetti, Nicolas Flammarion, Moon Chan, Pratik Mittal, and Matthias Hein. So basically, first of all, the question like about motivation, right? So why do we need an adversarial robustness benchmark? And I think the most important point is that now it is really difficult to keep track of the best performing defenses, right? So basically there is this motivating figure, which is taken from Nicolas Carlini's personal website, where basically he automatically counts the number of papers about adversarial robustness. And by now there are more than 4,000 papers. And among them, I suppose around maybe 2,000 of them or 3,000 of them are defenses against adversarial examples. So it's really hard to understand which ones work better and essentially how to rank them between each other. Okay, so the second point is that evaluating adversarial robustness is actually error prone, and actual robustness is often overestimated. So basically, we know that there have been a lot of different papers on how to evaluate robustness, right? So there have been pointed out a lot of problems with robustness evaluation, such as obfuscated gradients. There have been some guidelines about how to perform, for example, adaptive attacks on defenses against adversarial examples. So there have been a lot of papers in this direction. So it's not a trivial task. And basically the third reason why we need a benchmark like RobustBench is that essentially, okay, so one solution is to run adaptive attacks, right? Although it's not always clear how to run them properly, right? Because adaptive attacks are basically attacks that are run specifically for particular defenses that somehow leverage the structure of a particular model such that we can, for example, break it, right? However, okay, so the guidelines are only approximate, right? So it's not always immediately clear how to basically how to properly come up with a good adaptive attack. And second is that by definition, these adaptive attacks are incomparable between different models, right? So because we need to customize the attack for a particular model, and we don't, I mean, the numbers that we get, let's say robust accuracies that we get, they are essentially incomparable, right? So, and that's why we essentially propose robust bench. So basically, okay, so what are the main ideas? If you want to summarize in just single sentence, right? So we want to track systematically progress in adversarial robust models under some set of restrictions, which I will mention, in a standardized way, so that we are able to perform kind of side-by-side comparison within, let's say, single leaderboard of many models that have been proposed in the literature, and we do it using an ensemble of strong attacks. And now we use auto attack for this evaluation, which is a recently proposed method for which is essentially an ensemble of multiple attacks. And this is how our like one of our leaderboards look like. So essentially, okay, so it's publicly available on this website, okay, so we have multiple leaderboards, first of all, right? So it's in different threat models, but I think this like perhaps the most important, at least for the community, is I think the leaderboard on Cypher 10 for the L infinity threat model. And essentially one thing that I would like to highlight in particular is that, for example, okay, so by now we know that adversarial training works well, so it's a very reasonable defense. And if you avoid some pitfalls like catastrophic overfitting and so on, then you by now we know how to train robust models using adversarial training. And still, adversarial training in the way it has been proposed in essentially in the paper of Madri and collaborators at ICLR 2018, it achieves 44% robust accuracy, and the best model currently in the leaderboard achieves 67, right? So kind of the gap between robust accuracy and standard accuracy is kind of not completely closed, but it is reduced by almost by a factor of 2, right? And I think that there's something very important is that we really want to be able to track some fine-grained differences between different models. So something on the order of maybe several percents, right? And essentially the best model in this leaderboard kind of accumulates a lot of small improvements on top of the essentially adversarial training baseline. Another thing that I want to mention is that okay, we do rely a lot on auto attack in our evaluation, right? So this is the main method that we use for evaluation of robustness, but we also welcome adaptive attacks. So we have a column that basically says best known robust accuracy. So in case you have some adaptive evaluation that you want essentially to be represented on robust bench, we would be happy to essentially to show it. Okay, so there are 3 contributions, right? So the first one is essentially this leaderboard, right? So currently it contains more than 120 evaluations. So it's kind of quite large scale effort to collect these evaluations. The second one is a model zoo, which gives unified access to the most robust models. And currently there are more than 80 models in different threat models. And the third contribution is that based on the leaderboard, so based on the collected evaluations and collected models, we analyze various aspects of robust models, such as, for example, just general trends or essentially influence or the effect of robustness on calibration, fairness, privacy, and other interesting metrics of the model performance. Okay, and okay, so I think reasonable question is, okay, so why is this talk essentially given here at the verification workshop, right? And I think, okay, so first of all, okay, robust bench is not about verification, right? But I think it still can be useful for the verification community in the following ways. So the first point is probably the most obvious, is that the benchmark summarizes the latest developments in empirical robustness, which I think can be valuable on its own. The second one is that the model zoo provides easy access to robust models, which ideally should be formally verified, right? Although most of them are too large for the existing verification methods. And the third point is that we also accept verifiably robust models to our benchmark, although it seems that currently they are not competitive with the top entries of the leaderboard. So apparently there is some room for improvement. And okay, so just to highlight this, so the first entry has essentially 66% robust accuracy, and okay, so currently we have just one model which is verifiably robust, and it has twice less robust accuracy and also twice less standard accuracy, right? So there is quite a large gap. Maybe this model is not state of the art at the moment. At least it was state of the art at ICLR 20. So in case you have some better model which is verifiably robust, we would be also happy to show it on Robust Bench. Okay, and now I will talk more specifically about the three main parts of Robust Bench, starting from the leaderboard. Okay, so first of all, the threat models. There are currently three threat models. So first, it's L-infinity and L2 bounded perturbations. So this is the most well-studied setting. And the second one is common corruptions. Essentially, common corruptions are a set of kind of naturally occurring corruptions. So it's kind of essentially it's just a set of synthetic corruptions which aim to resemble the naturally occurring ones, such as, for example, different types of blur, some weather artifacts, or some other digital distortions potentially. So, and for L-infinity and L2 threat models, we use auto attack, which is an ensemble of white and black box adversarial attacks. And we also have an option to extend the evaluation with some adaptive attacks. So we welcome contributions in this area. Okay, and for common corruptions, evaluation is easy. So essentially, just compute the average accuracy on a fixed test set over all the 15 corruption types and 5 severity levels. And this is the essentially table that says basically how many models we have in different for different data sets and different threat models. And as we can see, for example, L-infinity Cypher 10 is the most popular setting, where we have 63 entries in the leaderboard. And essentially, it just reflects the kind of the attention in the community that this particular pair of data set and threat model achieved. And we also have models on ImageNet. Okay, now about restrictions. Okay, so basically, this is, I think, very important part of this of the whole benchmarking effort. Essentially, that basically we want to somehow rule out methods which make standard attacks fail without improving adversarial robustness. And motivated by this goal, we only accept models that, first of all, have in general non-zero gradients with respect to the inputs. So, for example, something like quantization of inputs, which would make the input gradients be zero, right? This is not allowed. The second thing is that we require models to have deterministic forward pass, which means that we don't allow randomized defenses, which can, okay, so it does rule out some kind of trivial defenses, but it also, of course, introduces certain limitations, right? And the third one is that we do not accept models that have optimization loop in the forward pass, right? So, and essentially it rules out many test time defenses, and also something like GAN-based iterative projection on the data manifold, right? So, yeah, so we currently do not support evaluation of this kind of defenses. And okay, I will come back later to discussion on these limitations. Okay, and we also introduced flags for L-Infinity and L2 models. Essentially, we flag models for which auto attack evaluation may be unreliable. So basically, the condition for this is if the black box square attack, which is part of auto attack, sufficiently reduces the robust accuracy compared to the white box attacks in the auto attacks ensemble, right? And this is essentially serves as an indication that adaptive attacks may be needed for such models. And currently we have only one such model, which is Shao et al. From ICLR 20. And so this is currently entry 58 on the leaderboard. So basically we can see that essentially auto attack shows 18.5% robust accuracy, which is kind of already quite low, but we know that it is possible to reduce the robust accuracy of this model at least to 7.4% if we run essentially also auto attack, but we increase the number of iterations and restarts of the square attack, right? The next thing that I want to discuss is the model zoo. So essentially, okay, so since we anyway have benchmarked quite a lot of models, we thought that it would be fruitful if we can provide simple access to these models. And in particular, one can install the library in just one line and import the corresponding function and basically load the model in just one line, and one just needs to know the identifier of a certain model, and it will be automatically downloaded. So it should be quite convenient. So currently we have more than 80 models in the model zoo, right? And again, this table shows how many models we have for each threat model and data set. So essentially all data sets and threat models are covered. And also I want to highlight that the most robust models are included in the model zoo. So for example, these top entries of the leaderboard, they're also available in the model zoo. Yeah. And the third part is about analysis. So essentially, first of all, we analyze the different trends based on the collected evaluations. For example, we can ask questions like which conferences, let's say, are more selective in terms of defenses accepted there, right? And is there some improvement over time, right? So we can have some plot like this, right? So on the x-axis we have different conferences. On the y-axis we have robust accuracy of auto attack, right? And we can see that essentially over time there is an increasing trend, right? So it's essentially this first point at ICLR 18 is the paper of Madri and collaborators, and there has been quite significant improvement since then. Although there are some, let's say, negative outliers, right? So essentially defenses that are less robust than claimed, or that are maybe not robust at all, right? So and we can kind of see which conferences essentially more selective in terms of the accepted defenses. We can also ask how much auto attack evaluation improves the evaluations which are reported in the original papers, right? So basically on the x-axis we have robust accuracy which has been reported, and on the y-axis we have robust accuracy of auto attack, and we can essentially see that there is a kind of sublinear trend in the sense that robustness evaluation from auto attack is at so it's basically either the same or better than what was reported in the original papers, which gives kind of a lot of I mean, which justifies the choice of auto attack for this benchmark. Okay, I think I have only 3 minutes, so maybe I will quickly go through the rest of the slides. So first of all, I'd like to know that basically all these evaluation results are in JSONs, so they are all open source. So one could analyze them and basically derive. You can derive your own trends and so on, right? So this is all available on our GitHub page. And then we have also included different points of analysis in our paper, such as, for example, how robustness can influence calibration. And kind of short conclusion is that most models, most robust models are completely miscalibrated. And that's why post-hoc calibration is especially important for them. Another conclusion is that when we looked at the amount of privacy leakage for robust models, we actually didn't observe any clear trend that essentially that robust models leak more, deteriorate the privacy leakage. And okay, so I think I have just 1 minute just to summarize everything. Okay, so we believe that accurate standardized robustness evaluation is possible if we introduce the restrictions on the models that we consider. And of course, these restrictions do introduce some limitations, right? And we don't want to discourage research on models that do not satisfy them. And also, just I want to highlight again that we have a lot of different evaluations which can be useful for different kinds of meta-analysis. We have a lot of models which can be useful for also for meta-analysis and for fine-tuning or building upon them, setting up as baselines and so on. And only a few models are formally verified, so there's also room for improvement in this direction. And we also introduce auto-attack flags, which kind of point out to the models that have to that should be evaluated adaptively, and essentially we basically view standardized and adaptive attacks as complementary, and we welcome contributions on the side of better evaluations if there is any. Okay, so Robust Bench is an open source project, and contributions from the research community are very welcome. So thanks a lot for your attention, and I'd be glad to answer your questions if there's some time.
Yeah, thank you, Maksym, for the great task. So Robust Bench is, I think it's a very important work in this field because a standardized and well-maintained benchmark and leaderboard is very important for the development of this field. So we can take one quick questions. Is there any quick questions from the audience?
Okay, may I have one question?
Sure.
So I think the one thing I think is not maybe fair enough is that if the two defense methods are evaluated on two different models, then it's hard to compare them directly. So do you have a plan to like design a matrix to evaluate such things together, like the nature accuracy, robust accuracy, and also the model parameters?
I see. Yeah, I mean, that's okay. That's true that basically we do rank particular models and not defenses, right? So, and then, okay, so I think this is something that we basically leave up to the user of the benchmark to kind of to try to understand which method works better, let's say on average, if we average over some set of data sets, right? For example, I don't know, let's say if one is curious whether traits is better than standard adversarial training loss, right? So then one can try to figure out from our benchmark, but then it would be more like some meta-analysis, right? So, and okay, we decided not to go in that way and to rank essentially just particular models without judging which defense is kind of robustly better over multiple data sets or multiple threat models.
Okay, thank you. Because, but I just think because the architecture will become, more and more diversity. So maybe that will lead make your leaderboard become a little bit fragment.
Yeah, I think there are some trade-offs, right? So there is no clear solution for this, right? So, and basically, okay, so we decided that we would just reflect whatever models there are in the literature, right? And we would provide some functions on the website, like for example, filtering according to architectures or according to some keywords, right? And then it's kind of up to the user to draw the final the final conclusions, right, about like which method is better, which architecture is better, and to really do kind of some meaningful comparison, right? So that was kind of our design decision. Yeah.
Thank you.
Thank you for the great talk. Thank you, Maksym. Now we'll start the next talk from Alexandro Di Palma from University of Oxford. So Alexandro holds a master's degree in computer science from ETH Zurich and is currently a PhD student at the University of Oxford, advised by Professor M. Pawan Kumar. His research focus has been on neural net verification and is more generally interested in optimization for deep learning and AI safety. Today, Alexandro will discuss how to improve branch and bound for neural network verification. So let's welcome Alexandro. And Alexandro, you can start sharing the screen.
So hi, everyone. I hope you can actually see my slides.
Yeah.
As Huan introduced me, I'll be presenting our most recent work on improving branch and bound for neural network verification. Just want to thank Huan and the other organizers again for having me, and also my co-authors across DeepMind and Oxford. So I guess I don't need to motivate neural network verification here. So I'll just present from the high level what it means as a problem. So we're given a network along with an input and some specifications for the allowed inputs, and just we want to verify that a given property holds for all the outputs associated to this set. So in practice, implicitly or explicitly, this means just propagating through the network some bounds so that we compute the set of allowed activations per layer until we get to the very end of the network, so that we have a set of allowed outputs, and we just check that the given property, for instance, whether they're all correctly classified, holds. So in this case, this is true. In order to solve this, we cast this as an optimization problem. So notation-wise, we have this calligraphic C, so the input domain, the affine functions. They're creating so-called pre-activation variables. These are then passed through the activations, sigma, usually nonlinear, like values. And we just pull everything together as an optimization problem. We just want to minimize this thing, which if it's if the network is properly formalized, in order to verify the property, we just need to check the sign basically. So if the sign of the minimum is positive, then the property holds and it's verified. Of course, the problem is non-convex due to the nonlinearity of sigma. So we cannot just run gradient descent and land on a local minimum. We need guarantees. So we need to solve this non-convex problem provably. And in order to do that, we rely on branch and bound. So just a brief introduction to branch and bound. There's probably some repetition with respect to what Patrick said. But the first component is bounding. So we have, again, the same specification, but now we kind of replace every set of activations with a convex outer approximation until, again, we get to the very end of the network. Of course, we'll only be able to verify a subset of the properties, as if all the points of the over approximation satisfy the property, that's good. The original property is verified as well. But if it's not the case, then we can actually draw no conclusions. So we need to do something more to have a complete verifier, and that's branching basically. As in this case, you cannot even verify the given property. So branching means basically splitting or dividing the domain of the optimization problem. In this case, we have this dashed yellow line that splits the domain of layer 1 in 2. And then we basically compute the over approximations separately for the splits. So we have subproblems, and for each subproblems, we compute the over approximation and we carry it forward until the very end. It is guaranteed that, like, at least for piecewise linear activations, the any property can be verified in finite time just by iteratively splitting and bounding the resultant subproblems. In this case, a single split is fine, so we can verify the property. So that's like a very rough overview of branch and bound. And as we said, I'm going to be presenting some potential improvements on both bounding and branching. We're going to be starting by bounding. So mathematically, bounding means replacing the minimum with a lower bound on the minimum. The most like commonly employed way to do that is just like to replace the activation function with its convex cell. For ReLU activations, this is called the Planet relaxation. It's like so popular that it's been referred to as the convex barrier to neural network verification. And there's a bunch of very effective bounding algorithms that tackle this relaxation or something looser. We argue that this is actually not tight enough for harder problems. So if we plot this in 3D with respect to the activations before the ReLU, we can actually see that the Planet relaxation is clearly not the convex cell in 3D. In fact, it's quite loose, and Anderson and colleagues have recently proposed a tighter relaxation that is able to represent not the convex cell of the activation function alone, but the convex cell of the composition of the affine function and the activation function. This is much tighter, but comes at a cost of like having exponentially many constraints. So this cannot be solved as it is. Luckily, though, the authors point out that, like, given any point in the feasible region, the most valid constraint at that point can be found in linear time. So a so-called cutting plane algorithm is possible and quite effective. This means iteratively calling an LP solver to land on the vertex of the current feasible region, and then adding the most valid constraint, again found in linear time, at that vertex to the relaxation. Hopefully, actually, just a couple of cutting planes suffice to recover most of the tightness from the exponentially sized relaxation. So potentially, you could just directly apply this for neural network verification. The problem, though, is that LP solvers are actually known to be scaling quite poorly with network sizes, even in just loose relaxations like Planet. So we kind of look for a customized solver that just tackles this relaxation more efficiently. We argue that we need the bounds to be valid at any time. This is actually very easy to achieve, just suffices to go to a dual space. So we kind of push all the complexity of the relaxation to a dual space. So the primal feasible region is now just hyperrectangles, but we have a problem that the dual variables are now exponentially many. So we cannot just directly tackle this dual. We actually need to restrict the variables to a smaller set so that we can afford to store this in memory. We call the small set an active set, but then if this is only like constant sized as opposed to like exponentially sized, we were facing the problem of choosing the variables that go into the active set. Of course, like the idea here is to preserve the tightness of the original relaxation. And we argue that this can be done by kind of mimicking the cutting plane algorithm in a dual space. So we start from the Planet relaxation. We start from a dual of the Planet relaxation and take a number of supergain steps to tackle this dual, and then minimize the Lagrangian so that we land on a vertex of the hyperrectangle and add to the active set the Lagrangian multiplier corresponding to the most valid constraint at this vertex. So this is effectively a simplification of the primal cutting plane in a dual space that hopefully allows us to get better bounds in the same time. We call the resulting algorithm active set, and let's evaluate its performance a bit. Let's compare it with a previous tool algorithm called BDD Plus that just solves the Planet relaxation in dual space, and with a primal cutting plane algorithm implemented in Gurobi. We just benchmark on computing upper bounds on the margin by which an SGD trained network is robust to adversarial perturbations on CIFAR 10. So here I'm just like plotting the the runtime as box plots and the variant plots where higher is better are the improvements in terms of bounds with respect to Gurobi. So starting from left, we can see that BD Plus is very, very cheap compared to Gurobi. It's like 2 orders of magnitude faster, but it yields quite loose bounds. In the same time, though, by tackling the tighter relaxation, we can get tighter bounds than the blunt relaxation, thus overcoming the so-called convex barrier. And we're still like 2 orders of magnitudes faster than Gurobi. If we just run the algorithm for longer, we can match the tightness of the bounds by Gurobi in still like a fraction of the time. And just adding more compute, we can actually improve on Gurobi bounds in like a 10th of the time. So we argue that these results kind of call for a redefinition of the convex barrier. We presented this paper in ICR last year, and we kind of extended this work with a new solver that doesn't need to store these active sets of variables so that the memory footprint is smaller. So that's the idea for bounding, just tackling tighter relaxation with Planet. What about branching then? Well, first, let me just explain what branching means usually. Usually one just takes the domain of the activations and splits it in half. For ReLUs, this is like super easy. It just suffices to split at 0 to get 2 linear functions. So in this case, for this particular neuron, the over approximation is the function itself due to the linearity. So it's pretty good. But we have a problem. We have a problem of selecting at any step in branch and bound which ReLU to split on. This is done with a branching strategy. A very popular one introduced roughly 2 years ago is called SR. It relies on very, very cheap bounds introduced by Wong and Kolter in 2018. So this is the shape of the over approximation. You can see this like much looser even on the planet, but it allows to estimate the contribution of a given split to the final bounds with a single backward pass for all the neurons in the network. So this is super cheap. We call these estimates S scores, and basically like SR branching just takes the largest score across the network and splits on that. If this failed, as a fallback strategy, an estimation of the size of the over approximation and its contribution to a dual is instead employed. These are like, we call them T-scores. That's fine, it's very cheap and quite effective, but it has been noted that by learning the branching strategy, one can actually greatly improve on these verification times. Learning-based algorithms are somewhat attractive, but they're quite problematic in verification as they require retraining once you just change a detail of the branch bound framework, if you change data set. So ideally, we'd like to kind of perform on par with a learning-based strategy, just via heuristics. So the first point to note on the SR branching strategy is the fact that like it's estimating the best bounds across the 2 splits. So this is like very greedy and optimistic. And we actually look for a more balanced branch and bound tree, as like we want to get to the leaves faster, hopefully. In order to do that, we replace the max by the mean. So again, to have a more balanced tree. And we also point out that the best possible branching strategy, at least from a greedy perspective, is to evaluate all the possible splits and to compute bounds for them, and just to take like the best possible bounds across the splits. This is called strong branching, and it's of course like super expensive. But at least using these scores from SR and our small correction on that, we can actually filter out the most promising in our branching decisions and perform some type of strong branching on this filtered set. In order to do strong branching, we actually employ a slightly cheaper bounding algorithm with respect to what we would do in branch and bound, and we use Crown, which is actually a very effective empirical trade-off between just cost, which is like a single backward pass, and tightness. All right, so we evaluate this branching strategy called FSB, so filtered strong branching, against SR, the heuristic I mentioned, and the GNN, so the learning-based algorithm. And so like these tables are plotting the average runtime on this data set, the number of tackled subproblems, and the percentage of timeouts. So the properties that cannot be verified in an hour. So we can see that like for 3 networks, the FSB strategy significantly cuts both the subproblems and the average runtime with respect to the heuristic. That was quite easy, but also with respect to the GNN. Especially like on a deeper network, you get almost a factor 3 improvement with even just cheaper, with like virtually no cost, just a backward pass, a constant number of backward passes. So these improvements, along with other engineering improvements to our branch-bound framework, are part of another extended paper that we have in archive. To pull these things together, we'll present the final leaderboard for VNN Comp, where like our entry oval is employing both FSB and active set. We arrived joint third with Iran from ETH, and we're like really glad that the best performing entry, Alpha Beta Crown, is actually at least partly relying on our branching strategy. So I think this kind of testifies the advantages of our latest research. In particular, actually on a harder data set than the average, where the perturbation ready have been kind of tuned on the single difficulty of each image, we can actually see that the tighter bounds from the Anderson relaxation pay off. And on this specific data set, this allows us to be actually the best performing entry. So that's a kind of what I want to say about like the technicalities of this. And I think I'm just going to conclude just by pointing out potential improvements. I think like the technical part of bench and bound, at least for like piecewise linear networks, has been kind of covered. For instance, Alpha Beta Crown performs quite well across a variety of benchmarks. But what is missing at this point is like support for a larger variety of specifications. It's like we have been focusing on robustness, but perhaps fairness or other safety-based specifications could be taken into account. And as a like closing remark, I think none of these algorithms is able to scale to the size of the networks commonly employed, like computer vision. And we believe that like a completely different approach would be needed to scale up branch and bound on those networks. So yeah, with that, I just thank again the organizers and leave it to any question.
Thank you, Alexander, for the great talk. I think the active set relaxation is quite important achievement for doing neural network verification, and the branching heuristic you developed are also very effective. So now let's take questions from the audience. We have some time for maybe 1 question. So if there are no questions, maybe I can ask 1 question. So like as you mentioned, like when you're using a stronger convex relaxation, like the active set relaxation, it seems you have to run a lot of optimization steps to get a much tighter bound compared to the cheaper method, right? I remember you have a figure where if you run the method 1,000 steps, it's actually gonna be much tighter than running 50 steps, right? 80 steps. So how like when you are solving a real verification problem, how do you decide like how many steps to run? Because if you run too many steps on a single splitting subdomain, you're probably wasting too much time. So you'd rather just do more splitting to improve the bounds instead. So how do you balance the two?
Yeah, thanks, Huang, for the question. Of course, like this is like a very hard problem. Like there's no like ground truth. There's no like theoretically correct way to approach this. In practice, like in our paper about the branch-bound framework, we point out that the number of iterations can be dynamically adjusted as you go down the branch-bound tree. It's basically you can estimate the size of you would need to get to the leaves, so to verify the property. And if you if like your estimate gets worse as you move on in branch and bound, that's probably the time to use tighter bounds. So in this fashion, by keeping like some exponential moving average on the statistics of the branch and bound tree, we just dynamically add more iterations and hopefully avoid wasting too much time on bounding near the root. But again, like there's like ideally one could learn this with a GNN perhaps.
Yeah.
But that'd be problematic for other reasons. So I mean, I think there's no real solution at present.
I see. So do you think like I know in your paper, like you actually show that FSB is actually faster than the GN-based splitting. So do you think it's still possible to further improve the learning-based splitting to make it even stronger?
Yeah, I think it would be nice like to incorporate more active learning, like online learning components into the branching. It's like the GNN paper mostly relies on like offline training, and this does not generalize very well. It's like the training is done on so data set that we benchmarked on is like composed of 3 different networks. The training is done on the smaller of the 3. And that's why like most of the performance improvement is on that network. It's like there are some minor generalization problems. But I think that like perhaps changing the way that the learning problem is formalized with more active learning, you could be able to adapt to newer architectures. But again, it's a very painful process to be able to, you know, beat on these heuristics, which are like fairly easy to implement. And this won't be the case for a learning-based algorithm.
Okay, cool. Thank you. That's a good perspective. Okay, so thank you, Alexander, for the great talk. And we'll move to the next speaker. So the next talk is given by DG Zhang. DG is a staff research scientist at DeepMind. His research interests include developing formal techniques to reason about behavior of complex systems with a particular focus on systems built using deep learning. So today, DG will give us a talk on probabilistic and global robustness verification. So let's welcome DG. DG, can you start sharing your screen right now? Okay, nice. I can see your screen. Are you muted? We can't hear you talking.
Can you hear me now?
Yeah, I can hear you now.
Can you still see my slides?
No, not really. I'm not seeing
sorry.
you.
One second, I had to reload because my.
Yeah, we can see it now. Cool. DJ can get started. Oh, we can't hear you again. Are you muted?
Can you hear me now?
Yeah, we can hear you now. Yeah.
And can you still see the slides?
Yes, I can see the slides.
Yeah, sorry. If for some reason, whenever I was sharing, it was stopping. It was muting me. I don't know why.
Yeah.
Anyway, hopefully it's resolved now.
Yeah.
So thanks, Juan, and thanks to all the organizers for putting together this wonderful workshop. Happy to be here, and I'm going to talk about some verification problems that go beyond the specification that we're most familiar with, which is robustness to perturbations constrained by LP norms. It's joint work with a number of collaborators from DeepMind and Oxford. So I'm going to motivate the types of specifications I'll talk about to start with. So on the probabilistic side, think about a vision system or a component of a vision system for a self-driving agent that's trying to recognize stop signs from video or images. So you can probably, many self-driving car companies have like extensive data sets of these traffic signs, and you can probably train pretty accurate neural networks for recognizing these. But what happens if you have some kind of sensor failure that leads to some kind of corrupted image? Many of these networks will actually make an incorrect prediction, but still be very confident about it. And so this is not even necessarily an adversarial example. It could just be some out of distribution example that the model just somehow recognizes very confidently as something different, because it's not, the weights are not trained to respond correctly to this kind of input. So this is something that can probably arise in practice quite often, where maybe you have foggy conditions that change the visibility or illumination of the traffic signs. I already talked about the sensor noise that can corrupt some of the pixels, and maybe you have other conditions like rain that occlude the cameras in some ways, or like add these kinds of water droplets to the surface of the camera. And you can imagine that each of these types of situations creates a different distribution of inputs depending on the conditions that are applied. And so one of the criteria that we might want in this situation is that when you're trying to make classification decisions in terms of recognizing these stop signs, and you're encountered with these kinds of out of distribution inputs, you may want to refrain from making confident predictions, right? So those kinds of specifications can abstractly be seen as follows. So you have a set of distributions on the inputs to a neural network. This could be the distributions that arise from each of these conditions in terms of the ambient conditions that a self-driving car is operating in. Then you have some kind of neural network which probably can be stochastic itself, because many times when dealing with predictions in uncertain environments, it's helpful to make the network itself stochastic, for example, use a Bayesian neural network. And then if you take a distribution over the inputs and you pass it through a stochastic network, you're of course going to get a probabilistic output. So you're going to get a distribution over outputs. And corresponding to each input distribution, you will get a different output distribution. So if you have a set of input distributions, you would get a set of output distributions. And then you want to make some statement of the form when the set of input distributions satisfies some constraint, then the output distribution also satisfies the constraint. Right?
So sorry, DJ, we can't see you moving the slides. We can only see the first page of your slides for some reason.
Oh, sorry. I'm really sorry. I don't understand what's happening. Okay. Let me try this again. Can you see this now?
Yeah, we can see this now. It's much better now.
Okay. Okay, sorry.
Yeah, thank you.
Yeah. So you have a set of distributions over the input, and you propagate it through the stochastic network, you get a set of distributions over the output. And then we're interested in a specification of the form, for example, that the average confidence of the network, say, measured by the softmax prediction, is going to be below some threshold tau, right? So you want to say something like, you want to reliably avoid confident mistakes when you have distribution shift. So formally, this corresponds to saying that for every distribution over the inputs which lies within a given set, if you apply your neural network to input sample from that distribution, then on average, the output distribution will satisfy some constraint. The other type of specification that comes up in some applications is global robustness. So this is kind of a robustness characteristic that is regardless of what values some set of features take. So you can imagine that, let's say you're trying to classify the topic that a YouTube video corresponds to. And you can imagine such classifiers exist at YouTube. And so you could imagine making this prediction purely based on the video, and you can train a network to predict the category that the video belongs to. For example, in this case, it's a sports video. But oftentimes, if you look at the comments that come on the video, that could also be an additional useful signal and help you improve the accuracy of the classification. But of course, the comments are probably much more vulnerable to changes as compared to the video itself. And you can imagine that, by changing if you have a network that is sensitive to the comments themselves, you could imagine that, the prediction could change when the comments are kind of perturbed in an adversarial fashion. So the question here is that, can we use multimodal features to boost accuracy in the absence of adversaries, but still somehow control the sensitivity we have to these vulnerable features, which are much easier to change? And we want to make this kind of guarantee regardless of how you change the vulnerable features. So in some sense, even under like arbitrary changes to the text features, can you still make some guarantees about the prediction? So I hope that's kind of motivated the types of specifications I'm thinking about. And now I'll jump to describing some of the ways we go about verifying these. So as is often done in verification, we turn the verification problem into an optimization problem, which is essentially the search for a counterexample. So we are interested in showing that for every input distribution within a certain set, the specification is satisfied, or the specification is below 0. And then you can construct an optimization problem that tries to find the worst case input distribution that maximizes the value of the specification. And if the optimal value is smaller than 0, or you can prove an upper bound on the optimal value that's smaller than 0, then you have verified the specification. So it turns out that we can actually do this in using kind of an extension of the Lagrangian duality framework. So essentially what we do is we construct a class of Lagrange multipliers, but as opposed to the standard case where these Lagrange multipliers are either scalars or vectors, in this case, they actually would be functions, right? And you can think of them implicitly as functions that enforce a penalty that kicks in when we don't respect the constraints between layers of a network, right? And so you design these penalty functions. In our framework, you can choose them to be any arbitrary function. And it turns out that if you choose these penalty functions carefully, this generalized dual problem, or what we call the functional dual problem, actually can give you an upper bound even for these probabilistic specifications. So if you compare standard Lagrangian duality to what we have, the standard Lagrangian duality deals with an input constraint, which is a set of points. In our case, the input constraint is a set of distributions over points. The standard Lagrangian duality requires that the network itself is deterministic. We allow stochastic networks. And you can think of the standard Lagrangian duality as the special case where these dual functions are chosen to be linear functions. But in our case, we allow nonlinear functions as well. And it turns out that we can prove this theorem that if you choose the lambda k, the dual functions appropriately, then the dual value exactly equals the value of the opt, which is basically the worst case value of the specification. But of course, that leads to an intractable computational problem. And in practice, we use a tractable upper bound based on restricting the type of function lambda k is allowed to be, for example, linear or quadratic. The verification algorithm for the global robustness is also kind of neat. So what we do is that we make the following assumption on the architecture that the text input goes through an embedding layer, which computes some kind of vector embedding of the text. And then that's the thing that's ultimately fed to the neural network. This embedding layer in practice mostly is either some kind of bag of words model, or it could be a transformer-based model. But in both cases, it turns out that the output of the embedding layer can be proven to be within the convex hull of a set of predefined embeddings. So in the case of the bag of words, it's just going to be in the convex hull of the vocabulary of all possible words of all possible words in the vocabulary. And in the transformer case, it's going to be the convex hull of the value vectors corresponding to the final self-attention layer that you produce. And it turns out that this convex hull constraint actually has some very nice properties when you combine it with piecewise linear networks like ReLU-based networks. So if you take a convex hull-like constraint, which in general is going to be a simplex, and you pass it through a linear map, and then you pass it through a ReLU, you get some potentially non-convex set. But the convex hull of this non-convex set can be characterized by just using 3 linear inequalities per neuron. So it's a description that has exactly the same complexity as the standard planet relaxation, but it's exactly as compact, and it's significantly more powerful, because the planet relaxation would not give you the convex hull. It would give you something weaker. And it turns out that mathematically, this is exactly an adaptation of the work by Anderson et al. That Alessandro mentioned in the previous talk, to the case where the input has this simplex constraint. So exploiting this simplex constraint allows us to get like really tight convex relaxations. I'm gonna go on to some experimental results. So for the probabilistic specification, we kind of made up a slightly contrived example, but I think it's still reflective of the kinds of specifications we would actually be involved in practice. So the idea is that you take a classifier for MNIST and you add a noise to this to the inputs, and you want to essentially get some kind of bound on the expected softmax output of the network. So you want to see what is the maximum confidence that the model can have across some distribution of inputs. And we don't fix the distribution, but we say that the distribution has 2 sets of constraints, that the support of the distribution is bounded, and that the distribution itself is sub-Gaussian. So it has lower tails than a Gaussian distribution. And it turns out that, like, yeah, to evaluate this, then you can kind of think about applying a threshold on the bound, and then you can essentially construct something that looks like a robust ROC curve. This is all pretty standard. But it turns out that if you compare our method, which is in orange, to the baseline, which does not exploit this information about the constraint on the distribution, it only uses the bounds that the distribution has to live within, then you can actually improve a lot. And it turns out that as you make the functional multipliers, the lambda k functions, more general, so you go from linear to exponential, you can actually get significantly better results. Again, I'm skipping over a lot of details here, but hopefully this will motivate you to go and read the paper. On the global robustness specification, we compared our method to the LERPA method from Huan et al., from Huan, Kaidi, and others. It turns out that for this particular data set that we looked at, which has essentially images of food and the corresponding recipe, so you want to do a multimodal classifier that categorizes the food based on an image of the food as well as a recipe, you can get significantly better verified accuracy numbers in exactly the same amount of time, because essentially the complexity of the relaxation is exactly the same as the planet relaxation, which is the basis for the LERPA method. I think I'll kind of end it there and just kind of leave you with this, that we should all be thinking about specifications that go beyond LP non-robustness and thinking about algorithms and benchmarks for the same. I think a lot of interesting work remains to be done here. As far as our work is concerned, our code mostly will be up at the DeepMind JAX Verify code base pretty soon. And the papers corresponding to the work I talked about will appear at NeurIPS this year. So please look out for those. I know that I covered a lot of items and it was probably a bit quick. So feel free to ask questions either now or reach out to me over email later on. Thanks.
Thank you, DJ, for the great talk on probabilistic verification and also global robustness. Is there any questions from the audience? So if you
yeah,
wanna,
sure. I had a question.
Sure.
Yeah, sure. So one of my questions was, how are you choosing these probabilities, like distributions in the first place? Like, what's the best way to choose those? Are those fully hand engineered, or is there a way to like choose those to best match your goal?
No, so that's basically a definition of the specification, right? So for example, in the self-driving example, it would come from an understanding of the sources of noise, for example, in your sensors. And basically it would be a characterization of the noise characteristics of your sensors. Right?
Okay, so they're fully hand chosen.
It's hand chosen as in it's basically a way to model the problem at hand, right? So you're essentially saying that the inputs to your network could be corrupted by certain kinds of noise. And maybe you don't know exactly the distribution of the noise, but you know some information about the distribution.
Got it. Thank you.
Yeah, I think that's a very good question though. So I think for like the global robustness and the probabilistic specifications, so there is, as you mentioned, there is no standard benchmark on these. So people usually don't know how to choose them, and it has to depend on a specific task, and it's hard to develop like a standard benchmark on this.
Right, but I think that like, you know, you could start with like very common examples, right? So for example, like sensor noise characteristics are pretty well known for many types of applications. So we could kind of like choose the constraints on the distribution that way. Of course, like, yeah, the self-driving example that I gave is much trickier because like, yeah, modeling things like fog and stuff will require a lot of modeling effort to like model the noise characteristics in that situation. But another example actually could be certain types of population shift, right? So if you imagine that, you know, you have a population on which you collect data, maybe like patients from a certain country or a certain region, and then you're kind of shifting to a new type of population which has a different mix of demographics. You can imagine that the different distributions come from like different mixture weights associated with the different subpopulations. And so, so I think there's lots of interesting examples where we can come up with like concrete suggestions for what these should be.
Yeah, thank you, DJ, for the great talk. I think these are very important for applying verification-based techniques to real problems because they are usually much more complicated than just using a LP norm threat model. Okay, thank you for the great talk, and we'll move to the next speaker. So the next speaker is Aditi Raghunathan. Aditi is currently a postdoc at UC Berkeley and an incoming assistant professor at CMU. She recently received her PhD from Stanford University, advised by Professor Percy Liang. She is interested in building robust machine learning systems with guarantees for trustworthy real-world deployment. She is a recipient of the Google PhD Fellowship in Machine Learning and the Open Philanthropy AI Fellowship. Today, Aditi will give us a talk on formal verification and also the real-world robust learning problems. Let's welcome Aditi. And Aditi, you can start sharing your screen now.
Okay. Do you see the right mode of the slides?
Yes, I can see it.
I haven't figured out. Okay, cool. Thanks for inviting me to this workshop. And yeah, so today, like Huan was saying, I kind of just wrapped up my PhD like a few weeks ago. And as I was writing my thesis, I took some time to reflect on how my view about robustness has changed over the years and kind of what kind of problems people are looking at. And I thought I'd take this opportunity to share a little bit of those reflections and my perspective, and in the process also give some details about some of the techniques that we worked on. I'm sure we all know this, like, when I started doing my PhD, like machine learning was a big deal. We had all these different examples of ML being very successful, but also it was a time when ML was widely used in all these different real world applications as well. And naturally, people started wondering kind of how good is ML in these real world applications. And these were the kind of articles that would pop up at that time. For example, in 2015, like perhaps a lot of you are familiar with this example, I was seeing that facial recognition systems built on machine learning do not work very well on certain demographics. It's been a while since then, and you'd hope that things are better now. But in 2020, we see similar examples of failures of machine learning based facial recognition. So I remember in 2015, I looked at, what did they do to address this issue? And turns out that what they did was to remove the word gorilla from their captioning lexicon. So I guess it's no longer that surprising that, these systems make errors because we haven't really fixed them in any fundamental way. And self-driving cars are again a very buzzword, been around for a while now. And you can look at how good self-driving cars are. And again, the answer is they're not that great. And here, a woman was tragically killed, where among other issues, a machine learning model failed to recognize a pedestrian who was jaywalking because it was only trained to recognize pedestrians at crosswalks when it was being trained. So I don't want to start this talk on a very dark note. So there are also funny errors that happen, like, a game can be ruined because the camera follows a referee's bald head rather than the football. It's something that we all acknowledge and knew is that current machine learning is brittle. And as we try to use ML in all these real world applications more and more, we were thinking about how do we make machine learning systems more robust. So taking a step back at the, looking at the machine learning pipeline, which is a lot of what we do today, is that, you collect a data set of examples from some distribution, and then we split this into train and test, or nearly into IID train and test. We train on the training data and we evaluate on this held out test set. So we're only typically evaluating on examples from the same distribution P that the training data was obtained from. And most of the benchmarks as well as theory, we're studying this setting, and this is no way solved. There are a lot of interesting questions in this space, but this is insufficient when you think about real world deployment, because you care about, for example, not just pedestrians at crosswalk, but pedestrians who could be jaywalking. And this is really a wide set of examples that the model could encounter that we need to think about. In particular, examples that are outside this data set distribution that the training data was obtained from. This kind of goal of robustness is generally thinking about getting good performance outside examples from just the training distribution, makes sense. But kind of the obvious question to think about here is, what is this set of examples that we, should care about? And, of course, this picture is misleading, probably the real world set of examples. In some sense, is this really complicated set of things that the model could encounter that may be really difficult to characterize exactly, and we don't know that a priori. And so given this kind of difficult question of robustness where we don't even know exactly what, how to capture what we want, and we have this intuitive notion that we want to be robust to a large range of examples, how do we start making progress towards this question? So kind of when I started off, I came from a little bit more of a theory background, and so it was very appealing to me to think about threat models because they're very useful abstractions when we try to think about building robust models. So the way I viewed this initially was that we can think of these different threat models as building blocks, right? And so we reduce the problem to first specifying what are the kind of building blocks and then trying to put them together. And so we can't be perfect. I guess DJ was taking some questions about how do we model this threat model. We can't be perfect, but incrementally we kind of build and add what are the different things a model could encounter and slowly build towards this general robust model. And in each step, we use the fact that we have some notion of a threat model and we can solve that properly. So this was kind of my kind of goal, or the path that I saw forward for robust ML when I first started thinking about this problem. And turns out that even if you had this threat model, actually achieving robustness is a hard problem. And we've worked with very simple threat models for the past few years as a community, but it's not like we've solved any of these questions to the level that we're happy with. So there are definitely a lot of challenges, even with a simple threat model. And then this is, of course, challenge, how do you capture certain complex shifts, like fog, or you could have even more weather changes and things like that. And now there have been some ideas floating around about using generative models to try to capture these threat models. But of course, the obvious question is we need to be aware that we might not even be able to characterize things we want via simple threat models. And then there's another question that even if we had a way to represent everything in sort of using generative models, how do we even get supervision on what exactly the shifts are? So if you knew that you wanted to model fog, then maybe you can write it as a generative model, but how do we even know what the shifts we want? Right, and sort of one approach that I had in mind, or what I thought could be useful, is to use a lot of unlabeled data. But getting labels is expensive, but maybe if we could just collect a lot of unlabeled data, we can get some supervision on what the shifts are. But like, of course, like all these you can see are like major challenges towards thinking about how do we get generally robust models. And we've barely kind of made progress on the first challenge and perhaps a little bit on the second. So I wanted to go into a little bit more about the first setting of threat models, which are simple, and these are things that perhaps a lot of people here are familiar with, and that's usually what we work on when we think about robust machine learning. So in general, the broad framework that is convenient to think about these kind of settings is this robust optimization framework. So you have this training set P, training distribution or underlying distribution P. And instead of just looking at performance on this distribution P, you can define a set of perturbations or like a set of different distributions around this underlying distribution P and try to get good performance on all these. So this B of P, or this kind of ball of distributions, captures kind of the notion of robustness you want in a precise fashion. Right, so this could include instance-wise perturbations, like adversarial examples that were pretty popular. This could be subpopulation shifts where there are changes in demographics. This could be a way to capture tail performance, in that if you have a very heavy tail distribution, you want to do well even on the tails. So there are a lot of interesting objectives that you can actually abstract out as this set of things around the training distribution. And this is kind of what a lot of robustness has looked at. And given this robust optimization framework, which is very appealing and abstract, the issues that come up here now are that evaluating this maximum, because now we're not evaluating on one distribution where you can just collect test data and look at the average error. We're actually doing a max over some probability distributions. And in many cases, it can actually be intractable. And perhaps a lot of the talks today around verification have kind of touched around this aspect. There's also the statistical question that even if you could evaluate this objective completely, what could happen is that actually achieving a low robust objective might require much more data than we use to get average accuracy. Because now this could be a strictly harder statistical question, because you want to do well, you want to really precisely get theta, because even small changes to theta could make your error on some other perturbation within the ball really high. And so this could just require more data. And in fact, this is something that we see in practice for really simple specifications as well. And another challenge that comes up is that even if we could collect more data and achieve good, robust accuracy, which is kind of what we have done to some extent, what we find is that there are trade-offs between robustness and accuracy. So when we do try to make models more robust, they tend to become less accurate on this distribution P, because they're trying to compensate by doing well on all these other set of distributions. And there sometimes can be trade-offs. And this is very annoying to deal with, because in practice, a lot of your examples are from their underlying distribution. So you don't want to compromise on that just because there could be some example that the model could fail on. And so these are all challenges that come up, and we've only solved them to some extent, even in the simplest kind of thing we can think about in this robust optimization framework. So just because I want to give some details in this talk, I'll very briefly talk about verification, since it could be of interest to most people here. So the framework of adversarial examples that perhaps a lot of you are familiar with is to defend against attacks that perturb inputs. And so this could be something like a stop sign by adding stickers, making it a speed limit sign, or you have some sentence, you have typos, and then you can break the model. So there are all these attacks that can perturb inputs, and at an abstract level, you have this set of perturbations. You allow an adversary to perturb, and you want to kind of make sure they get the same label. This could be typos or stickers and so on. And kind of, the simplest thing that a lot of people have looked at is these L-infinity perturbations, where let's say you have an image that's a lakeshore that, you can take an ImageNet model today and it would correctly say it's a lakeshore, but you can perturb and change each pixel by a really small amount to get this image at the bottom. That would now be called a completely different class. So this is kind of a nice starting point, because it's simple, very easy to think about, but also so striking because it's imperceptible. And kind of this is why a lot of people looked at this question. And unfortunately, we still don't have a complete solution to even this question. Right, and I think, I just want to very briefly go that one of the issues with the evaluation was that there was this kind of an arms race, or people proposed a lot of different ideas to defend, but the issue was not that we didn't have ideas, but sort of they kept getting broken, and it was hard to know whether the defense was actually robust. So this issue of intractability was really a problem, and it's not just a theory question in the sense that we weren't able to make progress on the question because we didn't know how to evaluate robustness. And just at a very high level, kind of what is needed to break this cat and mouse game is you want to be robust to the worst case attack, which means that you don't want to just evaluate on a few heuristic points that you can search. You really want to make sure that everything in your ball is robust. And you can write this out as an optimization objective. And the core challenge here is that this optimization that is over all these perturbations, when this loss function comes to a neural network, is like you can use that to calculate the exact robust error, but this is a computational problem that is intractable. So what we see is that when we try to be robust and have these kind of maximum, when you try to have an objective that doesn't evaluate on just one distribution, but rather a set of different points, the issue we quickly run into is that when you have this maximization over a large deep network like the ones we use in practice today, then we have to deal with an intractable optimization problem. And this intractability rises from the fact that there are nonlinearities as the input goes to the output. So from each layer to another, perhaps a lot of you are familiar with neural networks, the kind of issue that happens is you have a matrix multiplication, but there's a nonlinearity that you have to deal with. For example, the ReLU. So exact verification, unfortunately, turned out to be intractable, and you could use SMT solvers at the point when we started looking at this problem. They only scaled to about 100 nodes. So this was something that we couldn't use in practice, and this has been scaled up to some extent using MILP solvers. But when we first looked at this question, they still didn't scale very well, in contrast to modern deep networks that have hundreds of thousands of nodes. So how do we bridge this gap? And when we looked at this question, kind of the key insight is that you don't need to compute the upper bound exactly if you need guarantees, but you don't need to compute the maximum exactly. You can just compute a tractable upper bound, and that will also give you a valid kind of guarantee on the robustness. So I'm going a little fast because I think a lot of this is familiar to everyone, but I just wanted to talk about our mindset as to how we work through all these problems. So the one idea that we had was that, okay, the issue with evaluation was computation and tractability. Let's remove that by now doing tractable verification, right? And so the idea is that we compute some upper bound that maybe if that is 0, then we can at least prove that it's robust on that point. For example, if this is what the objective looked like, whenever the loss is 0, so we can compute an upper bound like this. And whenever the upper bound is 0, we know that even the true loss is 0, and that allows us to give you a guarantee or a certificate. But of course, since you're using something tractable, we could be missing out on some points, for example, here, but actually the point is robust, but you're kind of loose. And so we miss out on those points. But this is at least a starting point to try to understand how do we work with getting some guarantee when we have an intractable objective. And so this led us to think about certified error, where we can use some upper bound to calculate this, and then look at what are the fraction of points where the upper bound is 0, and say that at least on those points, we are sure no attack can break your network, but maybe things could happen at other points. We don't know. It depends on the quality of the upper bound. And so this, this is nice because now you can at least get a guarantee. At least you have some notion of what is going on with the intractable objective. So we did this. We had some kind of a simple upper bound to try to compute this. And the idea is to use convex relaxation. So you have a non-convex objective. You have a way to write it as a convex set. This makes optimization easy, but also gives you a guarantee because you're strictly covering everything that you actually care about. So we tried to use convex relaxations to do this. And so this simple idea that we had on convex relaxation, we tried it out. And one annoying thing that we found was that if you take an unbroken defense like adversarial training and compute the certified error, what we find is that it gave you something vacuous. So it said that 100% of the points could actually be broken. And this is, of course, we observed empirically this wasn't the case. So this was a little disappointing for us because we thought we had some way to get a sense on the objective, but really it was basically vacuous. But at least one nice thing that came out is that maybe we couldn't verify adversarial trained networks, but let's train specific networks that allow you to get certified error, which is reasonable. At least as a proof of concept that there exists some networks that we can prove some kind of robustness. So that led us to this kind of certified defense idea where you take this upper bound, but you explicitly minimize it, trying to find a network where the bound is tight. And so maybe that is meaningful. And this actually gave something reasonable. So like when you try to do this, like this is not great, but as a starting point, you've got a network with some kind of a guarantee on the robustness that no attack can get more than 35% error. So this is sort of how like we started thinking about certified defenses. We initially wanted to verify adversarial training, but we failed because the bound was too loose. And so we're like, okay, might as well just try and to train and see if we can at least find a network where the bound is tight. And so the key takeaway from this line of work is that maybe upper bounds are vacuous in some networks, but you can actually use them by making them non-vacuous by explicitly minimizing while training. So this was kind of the framework of certified defenses that a lot of people have worked on, come up with a lot of different upper bounds and scale things up. And this is a very incomplete list, but it seems like at least, this was something that gave us guarantees on robustness. So just as a brief timeline, so this was, adversarial training in 2015 or sorry, 2016 or so seemed successful, but we had no guarantees. SMT solvers were not able to work. And then instead of that, we came up with certified defenses as kind of a way that maybe we couldn't say anything about adversarial training, but we can get new networks where things could be, you can say something with guarantees. But this kind of question about what happened to adversarial training, can we say something about whether that's actually robust, was still open, right? And so that led us to think about this semi-definite programming where we went back to see, can we get tighter upper bounds so that even if we don't explicitly train, where you're just given a network that someone has used in practice, can we say something more reasonable? And can we go back to that original question of addressing the actual intractability without sidestepping and training new networks? And so here's a very brief description of what we found was a promising avenue using semi-definite programming. So we look at this ReLU unit, which is a nonlinearity. You see that there are kind of, this max, which is exactly what is shown here. And the nice thing is we can rewrite this in terms of quadratic constraints as follows. So this is an exact relaxation. So you have these two constraints, the linear constraints, which say that the output has to be greater than both these linear parts. And you have this other quadratic constraint that says it has to be exactly one of them. So this is basically writing the ReLU unit in terms of quadratic constraints. So we haven't changed the problem at all here. But why the quadratic constraints are interesting is that now we can relax this to a semi-definite program, which is a convex problem. And this is something that we have a lot of work on that we can build up. So this SDP relaxations of quadratic constraints have been studied quite extensively in both like the optimization as well as the TCS theoretical computer science community, and for example, the max cut relaxation. And so there's a lot of work that we could actually build upon. And so maybe the fact that we can write our neural network optimization as a quadratic program is quite promising because we can use these techniques. And in fact, we found that that is so. So like, we went back and looked at the same adversarial training network that we still had no answers on whether it's actually robust or not. And most previous certifiers were almost like completely vacuous. But when we tried to use an SDP solver, we got something pretty reasonable. And that now we could say that no attack can get more than 18% error on this adversarially trained network. And so we don't have to worry about it being broken, at least more than 18%. And this was kind of close to the lower bound in terms of actually finding attacks. So it felt like, yes, maybe there is some promise in using these quadratic relaxations. And we just went back and made sure that it is not just the adversarial training network, but really a bunch of different, robust networks trained by different methods were still being able to be certified by the SDP. So kind of the takeaway we found was, at least on small networks, these kind of quadratic constraints relaxed to SDPs were quite promising, and they can verify a variety of different networks. And you didn't have that original, like the certified defense issue of explicitly training to make them verifiable. But anyone who's worked with SDPs is probably thinking about like how scalable are the SDPs? Like, the whole issue with formal verification was it's intractable, though it was like tight. And so is the SDP any better? And turns out that off-the-shelf solvers are actually not that scalable. So the previous results were using like an off-the-shelf solver, and we could not scale it beyond more than 100 nodes, beyond 1,000 nodes. So there was some improvement, but not great. So working with people at DeepMind, DJ and others, and people at Google Brain, what we tried to show is that SDPs are still convex problems, so there is still a lot of scope that we can do in optimizing. And sure, we could build a custom SDP solver that only uses forward and backward passes through the network. So the nice thing about neural networks is that we have a lot of infrastructure for certain operations. So the idea of using this SDP solver is let's try to reduce the operations for solving the SDP to something we already know works very fast for neural networks, which is forward and backward passes. And the key idea is that we can use first order methods to achieve this. And this can be integrated into modern deep learning frameworks. And by doing that, we found that the solver, just by simply using first order methods, can scale up to 20,000 nodes and 2 million parameters, which is about a 200 times improvement in scalability over previous combinatorial verifiers. And this really allowed us to get certified errors, improved errors on adversarially trained networks on more complex data sets. So to just complete this timeline, we had this question of what happens to adversarial training, which was kind of something that people found was empirically successful. We still didn't know how to evaluate that. And SDP relaxation seems promising because of using quadratic constraints. So in our paper, we actually show some kind of theory why it's so much stronger than all previous methods and what kind of barriers it can obtain, or it can get over. And off-the-shelf solvers still don't scale very well, but the nice thing is that we can build our own SDP solver and use the fact that we have some deep learning frameworks, and that allows us to scale up quite a bit more. And so this kind of scaling that we did was pretty vanilla in the sense that we just ran first order methods. And so there's a lot of scope to do something more complex and really push the boundaries on what kind of verification we can do for arbitrary networks like adversarial trading. So I'm going to talk I know I'm probably short on time, so I'll talk very briefly about the path 2, which I started thinking about a little later in my PhD, was like, maybe we do need to at some point embrace the messiness of the real world, right? So maybe this kind of abstraction, so we saw already, even with the abstraction, things are hard, but also if the techniques are so tied to particular specifications, there's no way that it can kind of work in the real world without embracing some messiness. So maybe we need to think a little bit from that perspective as well. So if we didn't know anything about what to be robust to, and you just had this abstract notion of yes, be robust to the real world shifts, if you ask someone what you would do, the kind of answer that comes up is use more data, right? So the more data you see, the more you've seen of the world, and so probably you're kind of robust to these underspecified shifts. And so the question that we started thinking about is a good pre-trained model. So at the same time, people OpenAI and Google and Facebook started releasing these huge models trained on literally everything they could find on the internet. And so that's a natural question of, does that improve robustness? Is a good pre-trained model, which is a large model trained on lots of data, is that all we need for trying to be robust? And so the answer we found was that yes, they do improve robustness because more data in general means you've seen more of the world, even when there are these kind of underspecified shifts. But really, how you use a pre-trained model is also important. So it's not just about using more data, but there's a lot of interesting questions in about how do you use models that are trained on more data to try to preserve their robustness. So people are not very familiar with this pre-training pipeline. So this is kind of what the idea is. So you take a model that is trained on a lot of data. So you can have some kind of an input that leads to some features. And you use these features or this pre-trained model for some other task. So let's say you're doing satellite remote sensing. So this is an example of some underspecified shift. Let's say you could collect data from, say, North America, where it's easy to get labels. And you want to work well on some out of distribution points, let's say in another continent. Now, what you can do is we might not have data about Africa. We had no idea to say how North America and Africa's data are related. But maybe because you've trained on data, this pre-trained model is trained on everything, this model knows something about these different geographies, and we kind of want to preserve that and use that to get downstream robustness. So the two popular ways that people have for using these pre-trained models is one is fine-tuning, where you just have a random head and then you kind of use your features as an initialization and backprop through everything. So you just kind of do gradient descent with this nice initialization from a pre-trained model. And the other idea is don't change the features, keep the features as it is, and then only change the linear head. So usually people do fine tuning if they can, because that strictly kind of feels like it makes it more specific to your task, it improves performance. And that's what people in practice do if they can do fine tuning. But when we look at robustness, we find something pretty interesting. So when we looked at trying to get good robustness to kind of, these realistic shifts like geography or subpopulation or style, what we found when we compared these two methods is that the in-distribution, that is just the accuracy, does improve if you do fine-tuning, which is the common wisdom, but the robustness goes down when you do fine-tuning compared to linear probing, because like linear probing intuitively is kind of preserving a lot of the features. So you're actually preserving something that you've learned from your original task where you've seen everything in the world. You kind of want to preserve that when you use it, your model downstream. That's the only way you'll actually get robustness. This is just a sneak peek of our result. We also have some method to combine the best of both and stuff. But this is something we found interesting, that it's like not really just about using more data, the way we use it, and we need to figure out how do we preserve some notions of robustness when you train on more data, when you actually fine tune or use it for a particular task. So this is, I think, another kind of interesting avenue to think about robustness, because maybe a lot of the shifts that we have are actually going to be underspecified, but when you just train on a lot of data, there is already some information in that kind of pre-training stage that can be used when we try to use them for particular tasks. So then I want to summarize that robustness is a hard endeavor, even with a well-defined specification, and that's kind of what I realized. Like when I started my PhD, I thought this would be a summer project, but turns out it's not. And this is narrow, but at least allows us for precise guarantees. We know we're making progress, and these kind of abstractions could serve as useful building blocks. At the same time, there are real world shifts that are messy, but more data serves as a promising avenue. And there are a lot of questions here as to how to use the more data, what's the right evaluation, what's the right benchmark. And I think the right answer is to kind of make progress on both these fronts, and it's going to be some kind of a hybrid of both these approaches that would finally lead us to a system that we're happy to use in the real world. Then I want to thank my collaborators and Google and OpenPhil for supporting a lot of this work.
Thank you, Aditi, for the great talk. So it's very inspiring. It covers a lot of things in this field. So we'll have a little bit time for a quick question from the audience before we start the panel session. Any quick questions from the audience? So one thing I want to ask is, you mentioned you can scale up the SDP-based relaxation by tenfold or more using the forward and backward operations on GPUs. I'm wondering if that can be extended to a more general solver that also works for some other SDP problems that can potentially be accelerated on GPUs.
Yeah, I think that's true. I mean, there's nothing special about this particular SDP as such. I think the idea is just that if your SDP involves, like whatever verification problem you're using involves operations like that, like matrix multiplies that can be done efficiently. If you just reduce everything to that, then you can use the solver. So for example, if you have a sparse matrix multiply operation, like it's kind of just reducing to something like that. So yes, like.
Yeah, cool.
Yeah.
Okay. I think because of time, we have to finish the QA session and start the panel sessions from now. Okay, now our talks in the morning session are over, and today we are happy to have 6 panel speakers who are experts in the field of robust and trustworthy machine learning. So let me first introduce all the panel speakers. So Matthias Hein is a Bosch endowed professor at the University of Tübingen. His main research interests are to make machine learning systems robust, safe, explainable, and to provide theoretical guarantees for machine learning, in particular deep learning. He is an Alice Fellow and has awarded the German Raghunathan Award, a ERC starting grant, and several Best Paper awards. Hsieh is an assistant professor in UCLA Computer Science Department. His work mainly focuses on improving the efficiency and robustness of machine learning systems, and he has contributed to several widely used machine learning packages. He's a recipient of NSF Career Award, Samsung AI Researcher of the Year, and the Google Research Scholar Award, and also several Best Paper awards. Taylor Johnson is an associate professor of computer science at Vanderbilt University. Professor Johnson's research group, the verification and the validation for intelligent and trustworthy autonomy lab, recently has been focused on verification of autonomous cyber physical systems supported by projects from AFOSR, DARPA, NSF, and ONR. Aditi Raghunathan just gave us a talk, and she is currently the postdoc at UC Berkeley and is an incoming assistant professor at CMU. She recently received her PhD from Stanford University, advised by Priscilla. She's interested in building robust machine learning systems guaranteed and trustworthy for real-world deployment. She is a recipient of the Google PhD Fellowship in Machine Learning and the Open Philanthropy AI Fellowship. Wan-Yi is the lead research scientist at Bosch AI Center, Bosch Center for AI. She has worked extensively in robust multimodal models for autonomous vehicles, including video and LiDAR data, crowdsourced AI system, anomaly detection, and forensics. At Bosch, she is a co-pilot of the DARPA project on guaranteeing AI robustness against deception, which aims to identify system vulnerabilities, characterize properties that will enhance system robustness, and encourage the creation of effective defense. Finally, Florian Tramèr is a PhD student in computer science at Stanford University, advised by Dan Bona. For the coming year, he'll be a visiting researcher at Google Brain. His current research interests lie in computer security, machine learning, and cryptography. In his current work, he currently studies the worst case behavior of deep learning systems from a adversarial perspective to understand and mitigate long-term threats to safety and privacy of users. To maximize the aggregate time of invited speakers, so we are happy to invite Aditi to moderate the panel discussion for us. So if anyone has interesting questions and wants to hear the opinions from the experts, please type your questions into the chat box, and Aditi will monitor it and select some most interesting questions for further discussion. Because we only have limited time, don't be disappointed if your question is not selected. Now I will give my mic to Aditi, and Aditi will lead the discussions for the panel discussion.
Okay, thanks, Juan, and thanks to all the panelists. I'm really excited to chat. So I was looking at sort of the questions that we had collected and just thinking about it. It feels like one question that keeps coming up is what should we work on when we do robust machine learning, right? So I think that's something that everyone thinks about once in a while. And just for the sake of keeping the panel exciting, I thought I'd invite each of the panelists to share like one question that they think is the most thing that we should be working on right now in terms of robust machine learning, like from their perspective, like what are they most excited? It doesn't have to be like the problem that solves everything, but what you think is a problem that actually would help us make reasonable progress. Should we go in the order that Juan called out people? So I guess Matthias first.
Yeah, thanks, Aditi. Yeah, well, I think, I mean, for me, the most interesting thing, even though it's actually quite old already, is actually the adversarial robustness against natural transformations, so that we basically, instead of going to the LP model, specifying natural transformations. For example, also in more complex domains like MRI imaging, that you go through the imaging pipeline basically and specify adversarial robustness through the imaging pipeline, and therefore also can capture more complex noise distributions.
Oh, thank you. Next we have Cho-Jui.
Yeah, hi. So I think I quite agree with Matthias. So I think the most challenging thing is we already have very good, like a reasonable method for simple models like LP no perturbation and for robustness, but how to apply to real world applications. So in order to bridge this gap, you need to consider like how to model your perturbation set is most important, and how to think about what you want to verify or what's the concept you want to be robust. So I think that's the most important thing in the field. Yeah.
Thank you. Wang-Yi?
Hi. For me, for the adversarial robustness we think we're most excited about defense, especially certifiable defense against physically realizable attack like patch attack or different object in the scene, and especially for models that's not just single modality. Because, for example, like autonomous driving system, they never rely just one camera. At least there will be multiple camera or sometimes plus other sensors. So that would be most applicable to closer to a real scenario.
Yeah, makes sense. Taylor?
Hello, thanks. Can you hear me okay?
Yeah.
Great. Yeah, I think I agree. I'm going to put on my formal methods hat and say the most interesting thing to me, and maybe one of the things that's not being worked on that much, is actually how do we specify correctness? And I think there's a variety of reasons we're not working on that so much, but actually, what does correctness mean? And I think that can be interpreted in maybe in two different ways. One would be in a very domain specific way and working with domain experts. So for example, medical imaging analysis people. And another would be in system level specification. So I think some of those have been kind of mentioned, but my perspective is maybe from the formal method side, maybe a little different, actually saying what correctness means here and really focusing on that because that's hard, let alone just analyzing different types of specifications, actually coming up with what classes of specifications and behaviors make sense.
Yeah. Thank you. Florian?
Yeah, so I'll approach this, I guess, from a more computer security perspective. And there, I think this might sound a little surprising, but I think to me, one of the open questions there is it actually possible to attack a real machine learning model? In that I think we've done so much work on sort of showing that machine learning models are fundamentally sort of brittle, but there's actually been very little sort of core computer security work here of sort of taking an actual system, like, I don't know, YouTube trying to take down videos that it doesn't want on its platform, and like showing that this is actually a system that can be attacked with the type of techniques that we've been studying so far. And it's not at all clear to me that this is actually possible, or at least that it's as simple as we sometimes make it out to be. And I think we could learn a lot about the real security of machine learning systems by studying some of these questions in a sort of ethical and white hat style.
Yeah, cool. Yeah, okay. Thanks, everyone. So it seems like two threads that kind of, like everyone agrees that we need to think more like what is the real problem? Like, we could maybe show a lot of these failure modes and toy situations, but like maybe those are not the things we actually sort of care about. I feel like that's kind of the high level thing that everyone's saying. And that's something that I remember I also observed, like, when I was making my job talk and I tried to find real world failures, I felt like there's surprisingly few. And I was also kind of thinking about why is that the case? Is it because ML is not really deployed and all this? I'm tackling a problem that's a little bit futuristic in the sense that we're going towards full automation and we're not yet there? Or is it just that some of these things incentives are not aligned? Like maybe no one's really trying to break these systems. They have other things to do. Like it's like not as useful to them, or like, maybe there are technical challenges. That was sort of one comment that maybe we can dig into a little bit more based on the experiences of different panelists, like, what they think is like the reason we don't have a good sense of like, what are the real problems to solve. And the second question that, I've been thinking about myself too is it like, given that it's so domain specific to, okay, one is it actually like very domain specific to think about how do we model these shifts, or do we expect some kind of generalist techniques that are going to come out of modeling real world shifts? Like, so should we aim to dig into one particular application and solve a real problem, or should we aim to develop general techniques as kind of like CS researchers or something? And if it is like each of the two, like I was wondering if you had some experiences or guidance on how we could try to approach one of these, either pick a problem, pick a domain and solve it, or kind of what's the right level of generalism we should be aiming for, and like what's too ambitious, but what is actually achievable. So So maybe I can kind of go in the order. So you can comment on either of these questions, either the real world kind of nature, like what's the gap, or like kind of how your approach to making things more realistic is. So maybe Matthias?
Yeah, I think one problem is that it's a bit unclear what actually a reliable ML system is and what kind of properties it needs to have. I think this is at the moment quite unclear. And I think, I mean, a reliable system, and this is, I mean, underestimated at the moment, is that it has to come with its own specification. So basically, specification means that we know where we can actually apply this system, under which conditions. And this is something, yeah, where we are, I think, just at the beginning, or the community actually does not really do much on this. And okay, our take on this is that we want to build really everywhere reliable system. I mean, we are far away from this goal, but we basically have to acknowledge that at runtime, and unless we can control the system very much, we will not be able to control on which inputs we make predictions. So we have to basically, therefore, the system itself has to basically define what are correct inputs, so to say, in order that we can build actually a reliable system. So this is one important part, I think.
Yeah, that's a great point. So I guess it's kind of similar to what people think about like out of distribution detection or like confidence and things like that. Like you kind of want your model to know what it knows, or at least like kind of abstain from answering in points that it doesn't know. And one thing that this reminds me of is things that the fairness community has sort of tried to push in the kind of these model cards or model sheets and data sheets and things like that, where they're kind of trying to document where the training data comes from and what could be, or like, how the model performs on different groups and stuff. And I think we don't have, like, we don't know yet, like what's the right way to do that for like security or, in the robustness kind of perspective. So I think that's definitely something that's interesting. Cho?
Yeah, so I think like another gap. So taking myself as example, so recently we're facing some real problem. Like we want to have some visual recognition system, but it's robust to weather perturbations. And in this case, it's really hard to model it as adversarial robustness problem because you don't know what will be the what kind of perturbation you're going to face. So I think this also one important. There are two important things here. I think one is we may not. So the adversarial robustness is only one small component in the system, and there are many other components. Like when your attack really out of your defense mechanism, then your system need to warning the user, or it has to detect like out of distribution. So for example, you probably need to think how to combine the adversarial robustness and like out of distribution detection, because I don't think it's possible for a single model to handle everything and any possible input in the world. Yeah, and another thing is in practice, there's interaction between. So it's not like a simple, like what we do in a paper, you have an image and you perturb by a user. There could be interactions between users and the system. And the system may also use other mechanisms to know whether this is true or fake. Like when you interact with the physical world. So it's, we haven't seen much work trying to do like a defense in the physical world. So I think it's an interesting thing to do. Yeah.
Yeah, sounds like Florian's claiming there's not attacks on real world itself. So first we need to do that before defense. And I think it's a good point about the multimodal aspects, like, just like there's like going to be a lot of sensors or like a lot of parallel, things that are going on. And like, can we break through all of those things together?
Yeah.
Cool, thank you. Wang-Yi? I guess you mentioned physically realizable attacks. Maybe you can share a little bit more details on kind of what is the domain that you are most excited about and what your experience has been.
Yeah, the reason we are interested in physically realizable attack is because if you would to compromise the system, say autonomous driving system, to the point right in front, right after the sensor and before feeding into the ML system, you might as well change it to anything. right? And at that point, your system has already been compromised. I agree with Cho-Jui that this is a whole system and there are a lot of steps of defenses. So it is hard to just rely on a machine learning system to be robust. And
so, okay. Yeah, so I'm wondering, so if to work on robustness, keeping that caveat in mind, like how should we approach this? Like how do we, should we work with people who work on these actual systems? But that seems hard, like from academia, because we don't have access to, self-driving car system. So so I'm just like, I'm actually just like looking for advice myself to like, how do I, make progress being an ML?
Yeah, I think in industry, even for government, for who are looking for real guarantee in the field, they are only looking for like physically reliable ones, and also not just say patch you can, and they are looking for the reliable ones that can suppress normal object. For example, for object detection system, is there a patch or object to be put in the scene that can suppress the detection of surrounding object? Because if you want to put something, for example, a fake stop sign, you might as well just put a fake stop sign that looks like a stop sign, and instead of trying to get access to the model or just do a black box estimate of how some random pattern and put it in the scene. So that's one thing about it. And yeah, of course, multimodality is certainly in consideration, but I think for academia, the limitation is there are not so much public annotated data for multimodality studies. So yeah.
Yeah, cool, thank you. Taylor?
Yeah, I mean, I think I agree with everything that's been said. I mean, maybe an additional domain and trying to look at things. I think one thing we've tried to do to help make a little bit of progress are additional examples and benchmarks, particularly things outside of the imaging domain. I mean, we've organized this neural network verification competition for a couple of years now, but almost all of the things people are evaluating on are coming from the image and computer vision domain. So I think really looking at systems and seeing where people are trying to apply ML, because it's not just vision, it's all sorts of problems. I mean, I have my CP, my cyber-physical systems hat on now, so I'm thinking like a car or something, right? It's not just vision, a lot of it is that, but there's other ways that machine learning methods are being applied, and I think that would be one area I think we could try to make some progress on, particularly, because sizes can be a bit smaller. If you look at ACAS-XU, that's been highly impactful in this domain for benchmarking purpose, as well as because it's a non-image example. And I think that's kind of expected. So I think there's others that would make sense that would show up for other purposes, and things like even a non-autonomous car, right? There's all sorts of prognostic systems that are data-driven, and other kinds of components where all of these concerns are also going to come into play.
Yeah, fair. Yeah, I think even, just like between vision and NLP, where like in terms of the ML side, like both have a lot of similar benchmarks and everything, but in terms of robustness, it seems like there's disproportionately more attention to vision because it's just more convenient. Yeah. Florian?
Yeah, I think there's not much more to add to what people have already said here. I guess here again, I would say that looking at, I think it is important, not just important, that it's mandatory to look at specific systems to really make progress on some of these questions, because even the definition of what should be counted as a model failure or as an adversarial action is going to be completely dependent on context, and it's something, yeah, that I think we haven't really seen so far, but that will be really cool to explore, is if there are certain settings where people want to apply machine learning, where there are sort of other aspects of the system that can be leveraged to get increased robustness to natural shifts or to adversarial shifts in ways that might go beyond sort of just making a classifier more smooth or slightly more generalizable.
Yeah. Like, I was just, since you spoke about like, you know, how it's difficult to actually attack a real model or something, do you have like some experience working with the system to kind of say a little bit more of like, just go into a little bit more details, like where some of the techniques that we have right now just are, we just need to go beyond those. And it's not just a question of like, you know, modifying them a little bit.
Yeah, so I think on the attack side, for instance, so if you're now really thinking of sort of an adversary that's trying to attack a system, it's like a lot of the work, like the vast majority of the work over the past few years is really focused on sort of white box settings where we know all the things about the model because people in security will tell you that everything else is security by obscurity and we don't, and that's not something that's good. But if you look at what happens in the world, that's actually like, no one's ever going to give you access to a machine learning model. And then you're going to say, well, we have black box attacks, but no one's going to give you like a nice sort of query API either. What they're going to do is they're going to let you query the system like 2-3 times, and then you're going to submit something that's flagged as like bad. They're going to delete your account. And so it's kind of like, from an adversarial perspective, it seems like if you look at the kind of real attacks on systems today, it's sort of like people evading, you know, like hate speech detectors by adding like a couple of smiley faces at the end of their messages. So it's sort of very, very crude, sort of ad hoc attacks that have nothing in common with the kind of attacks that we've seen in the academic research. Which doesn't mean necessarily that you couldn't adapt these attack techniques in a way to make them work against real systems. But I think doing this work would actually be very, very valuable towards maybe also finding design decisions that real systems can use to resist some of these more sophisticated attacks.
Yeah. Yeah, thanks for sharing. I just wanted to remind that people in the audience could post questions. I don't see anything here. Juan, let me know if I'm missing any messages, but like in case no one sent anything, please feel free to send messages to about questions I could ask to the panelists. Okay, so yeah, I think it seems like almost like, you know, everyone kind of agrees and has shared like really interesting ideas or perspectives on how to, you know, kind of bridge the gap between these really nice abstract things that we study in academia, or like, you know, and actually what happens in the real world, and especially looking at other applications and domains. So maybe just to like switch gears a little bit. So one thing, so I'm, I guess, you know, coming much more from a machine learning background than like a lot of the other panelists here. So I was just wondering, from a machine learning sense, like for example, you know, you having a better architecture or a better inductive bias and more data and all of that, like, you know, kind of, how do we think of what kind of progress do we need there that could actually help with security? Or is it something like they're kind of independent in that the security aspects are really about the different systems and, you know, like, yeah, where's the data coming from, who are the adversaries and all of that, and the machine learning progress is somewhat independent. So yeah, like for example, I guess, you know, more concrete question is, if you were to tell a machine learning person who didn't care about security at all, but like wanted to improve the model in some way, like what would be something that as a security researcher you would want? I guess I'll just leave it open, like whichever panelist wants to share their thoughts.
So maybe I can just comment, because I think if we want to build really reliable, trustworthy ML systems, we have to also go beyond our usual, I publish one newspaper on one specific paper, right? Because we have to really build these systems, right? And building these systems means that they have all these properties, right? They are robust, they are explainable, they are fair, whatever, they have out of distribution detection performance, they correctly flag their own confidence in the decisions. And we have not such systems. And the community has also no bias towards building these systems because there's no incentive, right? Apart from, I mean, as a research community. And I think there are interesting research questions which will pop up. And I think we as a community have to work that this becomes actually possible to work on such things.
Yeah, that's true. That's a really important point. I think at least it seems like there's a lot of efforts to make more realistic robustness or distribution shift benchmarks. But I think the key thing that they're missing is like they're still like thinking of it as just a data set and something like, you know, like really like where's the data coming from, how is it used, and who's, you know, going to update the model, and all of that is something that we don't have a way to experiment with. Yeah.
I think there, at least it's a little bit my impression that there's maybe a bias in parts of the machine learning community also against trying to study some of these things from a very, very sort of abstract toy setting where, well, you'll never be able to sort of the first time come up with something that actually works. And so then usually the complaints are like, oh, you have to evaluate things on real data sets with real models. And I think, of course, that's very, very valuable, but I think there's room for the complete opposite of sort of trying maybe some very simple things in settings that we understand very, very well, where we can formally define what robustness means or what guarantees we might want. And we might come up with interesting ideas there. And I think this is kind of an area that's somewhat underexplored at the moment, or where I remember there actually being quite a few papers a bit of this type maybe 4 years ago or so, and that this kind of all died out, where people started working a lot more on empirical robustness problems. And yeah, I think some kind of counterbalancing on these topics might help.
Yeah, that's fair. I remember like someone in the vision group community was like, I don't trust papers which only evaluate on MNIST, right? Like, so I think there's definitely some kind of and then in like the theory side, people are like, oh, this is, you've just, you know, hacked hyperparameters in the data set. Like, I don't trust unless you can prove something. And I feel like, yeah, it's unclear, like, you know, yeah, should be a better dialogue.
I think we have to be honest with what we're doing. I think a lot of this sort of sentiment of like, I don't trust papers that only evaluate on MNIST also kind of came from a lot of papers claiming that they've solved the problem and only evaluating on MNIST, which I think is also not the right way to do things.
Yeah, absolutely.
Yeah, I think we definitely need both, right? I mean, I absolutely agree. We need both, but I don't know. I mean, we have also to say that the community, I mean, 1 or 2 years ago, when a paper was coming out, you had absolutely no idea if the experimental results were basically bogus or if this would be the new grant, whatever idea, right? So it was really in a terrible shape, I would say. And so at least now we are slightly better already.
Yeah. Yeah, and I think like a lot of these, you know, questions are probably like not as much as robustness, but it's to do with ML in general. And I think these, you know, questions come up in like a lot of different other contexts as well. Because I guess we have one question from the audience, which is very different from the stuff that we've discussed so far, which is how much of the progress has been made to draw from insights from neuroscience to address, you know, issues like robustness in CNNs. And I guess that's kind of building off of like, should we be thinking about radically new architectures and things like that, and kind of, you know, what has happened in that space? Because I do remember there's a lot of discussion in the early years about whether humans have adversarial examples or not, and like what we can say. And so I was, you know, I guess the person's wondering whether there's anything interesting that's come out of that investigation. Because I had one comment that I think people are trying to, you know, at least like I've seen a few papers where looking at biologically inspired or like biologically plausible learning mechanisms. Like, so there's a lot of evidence to say that gradient-based techniques are not what happened in the brain. And so they're like different learning things. And so people are trying to like use different ideas to learn, you know, networks, and like they're nowhere as good as doing SGD on a data set. But like I think there's some, or like they claim that there's some promise in these methods that even if they're not as accurate, they're somehow more robust to at least some of these changes. So maybe there's something there, but it feels like really hard to scale those up to a setting, and that, you know, that we can actually test that they're more robust. But I've seen some papers saying something like that.
I mean, I can jump in a little, I guess. I don't know anything about neuroscience, so I'll start with that. But I mean, I think they're different, right? But I do think obviously there are things like ambiguous images. You know, there's a few famous ones of these, right? Like the young lady and older lady type of image, or the like rabbit and duck type image, you know, depending on what perspective you take to look at it. Not exactly, you know, falling into the definition of, you know, the LP norm type adversarial robustness, but obviously they are something perhaps to be thinking about, and that I think people are considering a little bit of. I mean, other scenarios, you know, and driving and whatnot, things with reflections, water on the ground. I mean, there's a lot of challenging scenarios, many of which are going to be highly domain dependent. So anyway, my initial thoughts. So I think we do struggle with identifying certain things. I think the way they show up, though, is of course drastically different than how they're showing up currently in the machine learning domain.
Yeah.
Yeah.
Sorry, go on, Wang-Yi.
Sorry. So we happen to work together with some neuroscience just past summer, but we are not. There were very few work about bridging the gap between like CNNs or and neuroscience, but they've been looking into augmentation and neuroscience-based augmentation instead of network structure. And there are just a couple of handful of papers showing that some of these augmentation that's similar to how vision cortex work could also be more robust as well to either natural distortion or adversarial distortions.
Oh, cool. Yeah, that seems interesting.
Yeah. So I'm not familiar with neuroscience, but some like general comments. So I used to talk with someone, and I think they also have like a universal attack to human brain. Like you can see some two image, but they look different from computer, but they look the same for the human beings. So I think that shows the human perception is still very different from what CNN is doing, and there's a gap between those, and how to tackle this will be important. Yeah. And regarding different architecture, I think one thing currently we're lacking is when we have very different architecture, how do we evaluate the robustness? And so I want to take so recently there's like a transformer-based architecture for computer vision, and we found with this like new architecture and activation, it becomes very hard to know whether the robustness evaluation is reliable, and I don't think there's any good method to verify those neural networks. So I think the current research may be too focused on like ReLU-based convolutional neural network, and maybe we need to think about more generally if there are different kind of architecture or activation, how can we handle those in terms of both attack and verification? Yeah.
Yeah, that's fair. So I guess we have about like 3 minutes before we wrap up. So I just wanted to check if the panelists had any kind of other comments to make, could be unrelated to the discussion or otherwise. If not, then maybe I can like kind of ask this like final question, which I've also been wondering about. Like when would we be happy to use a machine learning system in the real world, right? Like, you know, what are we building towards? Like, what is a goal that we'll know we reached, right? So I think that's or like even, you know, we can think of this even in a system sense, right? Like, so of course, like, you know, people are deploying a system, you'll find some flaws and then you'll go fix it, and that's fine. Like if that process incrementally converges towards the right solution, maybe that's also something I'm happy with, because like I'm not going to use the system immediately. I'm going to test it out and like have some fail safes in place, and then eventually it's going to get perfect and I would use it. So I was just generally wondering, like, kind of what would be an ideal system, that what's the goal that we should be going towards? Maybe we can go in the order. Matthias?
Well, I think that comes back to that the system that we need basically, yeah, specifications, right? So that either these specifications can be that we say, okay, we have trained it on this data, and therefore basically you should also use it on similar data, because we have no idea how it will behave on something which is out of domain.
Right.
Or as I said before, that at least you have this kind of out of distribution detection to make sure that you're not making predictions on some things where you should not make any predictions. So, but it's really a tricky thing. I mean, we are starting here at the moment also some projects in this direction in the medical domain, and the medical domain is really super safety critical. And as I said, therefore, as a community, I think we really need a more holistic point of view on this whole problem. And I have not a good answer when I would be myself happy to use a certain ML system, then rather than saying that I would like to test it myself as much as possible.
Yeah, exactly. So that's something that I was struggling with. You said all this, it's challenging, but like someone asked me like, okay, so when would you be happy with it? And I'm like, I actually don't know. So yeah. Cool. Cho, do you have some thoughts on this?
Yeah, so I think that so there are many different kind of systems, and maybe different system will require different levels of robustness or security. Like I work closely with people working in the search system, like in Amazon and Google, and they don't really so because one of my research focus on robustness, but usually they don't really care about the robustness of in their search system, because there are so many other issues they need to handle. And so they are, but they really care about the out of distribution and explainability of their prediction. So but I think for a system more like a real-time system, like self-driving cars, so probably robustness will be more important. So I just mean there are different levels of robustness. So I think you need to think about when you deploy the system, what's the situation you are going to face, and then decide what level of robustness you need to have. Yeah.
Sorry, who's that? Wang-Yi?
Yeah, so I mean, different application has different requirement, right? Like Matthias said, if it's medical, it has to be very safe. But also, medical scenario is this environment is very controlled, so you would have less out of distribution worry. And say autonomous driving, then there's nothing better than field testing, which is also beyond the hands of us machine learning researchers. So it only all we can do is test as much as possible, and that requires a variety of data, right? You can go try to crawl all the YouTube videos and see if you can correctly identify them or not. So yeah, so this is a hard question. It's very application dependent.
Yeah. Taylor?
Yeah, it's a hard question. I think the reality, though, is that we aren't going to get to make this choice of when we will be satisfied, with the status of robustness, verification, security of these systems, because they're coming anyway. So, I mean, I think the actual answer is one that we could maybe have some level of influence over in terms of regulatory aspects. But I think the real answer is it's coming anyway. And if we can help shift the attitude a little bit to think about these things, that's probably a good thing. But I think the reality is, even in domains where stuff is certified, like medical devices, I'm going to put a link in the chat in a minute once I find it. But But you know, these devices are already coming that have machine learning components in them that are approved. And you know, we see what's happening with autonomous driving. So I think the answer is actually, we're not going to get to choose that. And it's going to happen anyway. So hopefully we can help shift the culture some.
Yeah, fair. Cool. Yeah, thanks, Taylor. Florian?
Yeah, again, sort of approaching this from the security perspective, I think it's a really hard question, because we tend, at least people in security tend to very often sort of think of security as kind of a black and white thing, like either something is secure or it isn't. And sort of under that metric, we've made like zero progress on machine learning robustness over the past 5 years. And again, that's maybe why looking at sort of real systems and how people tend to evaluate those real systems could help, because of course in practice, that's not how people think about security. And it might just be that, that evaluating these things or answering these questions are kind of inherently going to be fuzzy and very context dependent, which might make it challenging, to do academic research on some of these questions. But right now, it seems like a lot of these things are still so much in flux and kind of still being developed, and that there is a lot of potential to sort of at least shape the discussion on what the right questions should be. So yeah, I'm not losing hope yet that we can make some reasonable progress on these questions.
True. Okay, so I guess we are kind of out of time. So thanks all the panelists. This was a fun discussion, and I'll hand it back to Juan.
Yeah, it's a very nice discussion, and I want to thank all the speakers, and I want to thank Aditi again for helping us moderate the discussion. So as a summary, so the speakers discussed realistic specifications of robustness and the reliability, such as natural transformations, explainability, and out-of-domain data, which people really care when applying robustness and reliability machine learning model to realistic applications. And people also discussed attacking and also building a real-world machine learning model under the physical realizable attacks. And also people discuss the connections to neuroscience and the new architectures for robust models, and also the need of new verification tools for new architectures. Finally, the speakers had discussions on realistic metrics of evaluating robustness for real-world machine learning model systems. Those are really great topics, and hope that can inspire researchers who attended this workshop, and to have some new research focus on those exciting areas. And I think that's all of the morning session, and we'll have a break until 1 p.m. Pacific time to start the afternoon session. And if you are interested to see the details of the talks, you can visit our website on this link. Thank you for participating in our workshop, and see you after 20 minutes.
Okay, let's start. Okay, welcome back, everyone. And I'm Kaidi. It's a great pleasure for me to host our afternoon session. So the agenda here is quite similar to our morning session. So we will first have a keynote talk, and then coming up with 5 invited talks, and finally end with a panel discussion. Okay, so let's move to the first keynote talk from Dr. Zico Kolter.
All right.
And,
oh, sorry, go on.
I'll introduce first. So Zico is an associate professor in the computer science department at Carnegie Mellon University. He also serves as chief scientist of AI research for the Bosch Center for AI, working in the Pittsburgh office. And Zico's work focuses on machine learning, optimization, and control. Specifically, his work aims at making deep learning algorithms safer, more robust, and more explainable. And Zico's recent work includes training probably robust deep learning systems and using more complex optimization solvers within the loop of deep architectures. Zico is also interested in several application domains, with a particular focus on applications in smart energy and sustainability domains. And today, he will give a presentation entitled Robustness Beyond the Worst or the Average Case. Let's welcome Zico.
All right, thank you very much. Sorry for jumping the gun there a bit.
Okay, and you can share screen once you're outside.
Yeah, let me do that. Okay. Stop other screen sharing. All right. Sounds good. Share my desktop. And okay. All right. Can everyone see the right screen there? Is the right one showing?
Perfect.
Not presenter view or anything? All right. Let me get to the normal dance of rearranging my my Zoom windows. All right. So I'm really thrilled to be here. Thanks, Huan, for inviting me. Or I guess thank all the organizers for inviting me. Juan just sent me the email. Through no machinations of his own, I'm happy to talk about work that Juan's doing. So he has a dual goal in in inviting me here. Though I should also credit other people who are here too. So Leslie. So this is work I should mention beforehand. I didn't have a note on this. This is work that's appearing this year in NeurIPS, and it was led by Leslie Rice in my group, as well as with also in collaboration with Anna Baer and Huan. And this work deals with kind of a new direction, or what I hope is a new direction in robustness, which is thinking about robustness beyond the way we typically think about it, which is worst case robustness or sometimes average case robustness, but thinking about sort of what lies in the middle of these two extremes. So I'll talk about what I mean by that in a moment. But first, I want to give all the credit to Leslie, Anna, and Huan, who did most of the work here. All right. And actually, I think I mentioned before that this work is appearing in NeurIPS this year. It's actually not yet on archive, unfortunately, but it'll be posted soon. So apologies for giving a talk before I can refer to an actual paper, but hopefully this will be a fun teaser for the actual paper coming out in a few days. Nothing motivates preparation of a paper more than a camera ready deadline and a talk you have to give on the subject. All right, so let me start by talking about what we mean by robustness. Robustness is a very loaded term. Oh, I should also mention before I get in, please do interrupt and ask questions in the chat before we go. I'm happy to sort of intersperse questions and presentation as we go. If we don't finish all the slides, it's completely fine. I'd rather have a conversation. So by all means, ask questions as we go. All right, so I think I'm good. Why can't I? Okay, there we go. So the term robustness, I would say, is actually a very loaded term. We all, or at least a lot of us, work in robustness. We build adversarially robust models. We try to build defenses against adversarial attacks, stuff like this. But despite this, what we actually mean by robustness is often imprecise, or at least what's the common nomenclature about robustness is often imprecise. So what I typically mean when I say robustness, when I talk about robust loss, is I mean some notion of the performance of a machine learning system under worst case perturbations, right? And this is also known as adversarial robustness or worst case robustness, et cetera. But the basic idea, and let me actually get out my little marker here. I'm going to need it elsewhere too. We typically mean that we're going to take some perturbation that we allow to vary arbitrarily in some set. Oftentimes, this is just as simple as a ball around a given point. And we're going to look at the worst case loss of some example, not just on the given points, not just for the panda that we all know, but for the panda plus any amount of noise within some ball, which in the worst case is not a panda, it's a gibbon or something like this. However, people also mean other things by robustness, right? When we talk about other types of robustness, people sort of often sneak this in, but actually it's also very common to talk about things like average case, or what we sometimes also called natural robustness, which is essentially the same basic idea, except you're replacing the maximization here with an expectation, right? So you think, instead of thinking about sort of the worst case of your perturbation in some ball, you think about the perturbation sampled from some distribution now. And I'm kind of overloading notation here. You'll forgive me. I'm overloading a bit of notation. So now here, delta refers to like some sort of distribution over possible perturbations. And average case or natural robustness often refers to the expected loss under these perturbations. Okay, and this is actually often not kind of quantified as such. It's technically not really robustness. So in sort of the classical kind of sense of robust optimization, right? This is not robust. This is sort of, you know, this is stochastic optimization, not robust optimization. But they're very related, these two fields, right? And people often sort of actually mean this thing here when they talk about robustness. For example, the common corruptions sort of data set, or I guess not data set, but the common corruptions perturbations, which are very common as sort of a method of evaluating robustness of classifiers. They typically apply random or randomized perturbations to images. So you don't just learn, you know, how to exactly sort of remove certain patterns. You have to have some sort of randomness, but they typically, you know, they look at things like snow or frost or fog or noise explicitly, or some of them are deterministic, but a lot of them are noisy too. And the idea here is that these noise patterns are not sampled adversarially, they're sampled randomly, right? But we still refer to this as kind of the robustness of the algorithm with respect to you know, over some perturbation set. And I would actually argue this is a less formal definition of robustness. Robustness to me really means kind of worst case performance. That's the classical kind of robust optimization sense of the term. But I'm willing to kind of give that battle up and think of, okay, you know, people mean both of these things. We talk about robustness. So what this talk is about, this is a pretty big difference here, right? A tiny bit of robust, you know, adversarial noise can lead to a very, very big change in classification. Whereas classifiers are more, but not always fully, robust to some amount of adversarial, or sorry, of natural perturbation. And actually, in some sense, one way to think about randomized smoothing is actually using sort of natural robustness to craft an adversarial robustness of an ensemble. So there are already sorts of connections between these two things, and this is actually a very rich field. But what this talk is about this kind of gap between these two, because those are very different things. And I want to consider at a high level, what lies in between these two extremes. Is there some sort of natural interpolation between these two, I would argue, very different degrees of robustness that we have? And what we're actually just going to do right now is talk about defining one of those, or one sort of way of interpolating between them, and then talk about a way of actually computing these metrics between worst case robustness and what I'll call average case robustness. And I think there's a ton more work to be done, and I'll end up in a little bit making some comments on that. But we're just gonna, I want to offer kind of a first glimpse into what might serve as an interpolation between these two things. Okay, so that's the agenda for today, and the rest there's, I mean, there's actually a lot of math on further slides. I was looking at my presentation after I prepared it and realized how math heavy it is. But forgive me, we have some time, so stop and ask questions. So I don't get through all the math, it's certainly fine. Okay, so first of all, let me define what I mean by something in between adversarial and or worst case and average case robustness. First of all, I don't just mean like, this, 1 minus lambda of this plus lambda of that, right? We're not talking about something simple like that. We're talking about something that more fundamentally is satisfying as some middle ground between these two. Fortunately, I think there's a very nice, there's actually a very nice notion here, which has to do with functional norms with respect to a density. Okay, so now we're going to dive into the math a little bit, but this is pretty easy. I'll dive into some sort of a little bit heavier math in a second because I find it actually really beautiful in this case. But let's define some math here, even at the start. So I'm going to define a Q norm of a function. So I have some function f. I'm going to define its Q norm with respect to a density mu, and this density here mu is actually going to capture the threat model. So for example, for an L infinity ball, this density here could just be a uniform distribution over, say, the unit ball or the epsilon ball, right? So maybe a uniform density over that space. And actually, in our case, we allow for unbounded densities. In general, you can't have that with adversarial robustness, because that would allow for an unbounded perturbation. But this can be some density that defines our expected set of allowable perturbations. And if you don't want to have a density over that set, you can just make it a uniform. You have some finite support and have your density be the uniform distribution over that support. So the Q norm of a function with respect to this density is just the expected value of the function. Oops, this should be flipped here. This should be the function. I already see a typo on the second slide, so it's not, that maybe bodes well. the expected value of the function raised to the cubed power, all taken to the 1 over cubed power. So this is actually just the normal extension of a vector norm to a function, where the function is then weighted by a certain density. So I have it right here. So here I have the Q outside the absolute value properly. But it's basically the integral over all deltas, the density of delta times the absolute value of the function raised to the cubed power. And this whole thing taken to the 1 over cubed power. Again, this looks a bit complex, but this is really actually just thinking of functions, doing the normal sort of functional analysis thing of thinking of functions, just big vectors. This is just the normal sort of the normal LP or LQ norms applied to functions instead. All right, now here's of course the punchline. It's so if we take any smooth loss now, as you probably know, for a vector, right? The L infinity norm is equal to the maximum element of that vector, and the L1 norm is equal to the sum of the absolute values of that element. Or if you have a density here, then it would actually be equal to the average value of the elements. And because of this, we actually have this very nice notion here that essentially the L infinity norm of the loss function, and I mean a functional norm now with respect to the perturbation, right? So this is nothing to do with the LP balls, really like that. I mean the actual functional L infinity norm ends up being a maximum, i.e. the L infinity functional norm ends up being adversarial robustness or adversarial kind of loss. And the L1 norm of this ends up being expected loss. So we now have a very nice sort of framework for categorizing, and I'm being a little bit informal here to be clear. So for the full sort of functional analysis kind of thing, you need to have some definitions of continuity and stuff like this. And there are some scaling terms here. Maybe like you might want to scale by the density. I'm kind of often assuming this is a uniform density, but ignore all that. This is the basic idea, right? Is that the L infinity norm, the functional L infinity norm of the loss, is the adversarial loss, and the L1 norm is the expected average case loss. So I think this is a really nice framework for thinking about adversarial robustness and average case robustness, right? It puts them both on some sort of spectrum of extremes. In other words, sort of, they're all LQ, functional LQ norms, where Q equals 1 is equal to average case robustness, Q equals infinity is equal to worst case robustness. And the question is, what does it mean to talk about what we're going to call intermediate Q robustness. Right? That's robustness that lives in between worst case and average case, and I think a very natural manner. So what do these things kind of mean? What does it mean to talk about intermediate Q robustness? So at the high level, that's sort of all it is, right? It's a middle ground between worst case and average case robustness. What I mean by that is it puts more weight on worse examples, right? So if you're sort of familiar with vector norms, right, you know that if you talk about like the Q3, I'm not going to use P here because P is too overloaded. People talk about LP balls and robustness. We're also going to talk about P as being a probability. So it ended up actually being so cumbersome to talk about here of using P everywhere. So I'll use Q. But oops, and I even did it there. I even put intermediate P. So it should be intermediate Q robustness. So it should be Q. Intermediate Q robustness. It's a middle ground between worst case and average case, right? It puts more weight on worst examples, right? So you know, if you take a vector norm, the L3 norm or the L10 norm, right? This would look more and more like the max that you get at L infinity, but it's not, right? But because it's not the worst case perturbation. What it actually is it's something that puts more weight on the worst case, on things that you have large loss, but doesn't put complete weight on the single one worst example in your entire set as its adversarial robustness, right? It still is sort of some notion of an integral, of a sort of a distribution over your possible perturbations, and it takes this into account when computing the actual robustness measure. I should also mention this has nothing to do with sort of this LP balls, as we typically talk about with threat models. In a threat model, you sort of specify, that's just specifying what that distribution is. And that distribution in this intermediate Q robustness could be either L infinity, the L infinity ball, a uniform distribution over it, say, but it could also be like random scalings and crops and flips of the image. Like that's all fine too. It can be any distribution that you can define over your image. You can, for all of those, talk about sort of the worst case or the average case. And now we can talk also meaningfully about like the intermediate case here for any threat model you want. And again, maybe another way of putting this is it still penalizes the worst case, right? Because you still are taking the worst case to the Q. But it's not dominated by what we think of as kind of like the measure zero adversarial attacks, right? So when you think of adversarial attacks, if you think of it as a distribution, adversarial attacks kind of lie on like a measure zero set, right? Because you're sort of finding the exact points that are really worst for the classifier, no matter if that's like this, huge chasm that this spike you'll never really find in practice. You always put all your weight there. And the other thing I want to mention, this is not sort of inherently better or worse than existing robust methods. So we're not really going to compare to other methods here. What we're going to talk about here is really a different notion of what it means to be robust. And we'll talk about sort of the trade-offs, because there are trade-offs, right? If I train for one of these intermediate Q robustness measures, then I'll do better on that measure, maybe also better on adversarial robustness or average case robustness, but I'm optimizing a different objective. And I think it's an objective that it's harder to sort of explain intuitively, certainly, but I think it might be in some sense what we actually are after, because oftentimes we make this complaint, right? That worst case robustness is too worst case and average case robustness is not worst case enough. Well, now we have this intermediate element that we can sort of use for this purpose. Now, the other thing I'll add is that this also, another way to think about this, if you incorporate this into training, this also offers kind of an interpolation between data augmentation and adversarial training. So when we think about data augmentation, we think about randomly sampling perturbations of our data to augment it for training. Whereas adversarial training finds the worst case perturbation and kind of augments the data with that, right? And they have very different purposes, right? Data augmentation often helps our clean performance a lot. Adversarial training does not, it often hurts our worst case performance for the benefit of now doing better at test time on the worst case. But they have but this is now precisely, if you incorporate this during training, this is precisely kind of this middle ground between data augmentation and adversarial training. It's a procedure for spanning that kind of gap. And those are actually very, very far apart typically, right? Those typically have very, very different purposes, or how we think of them as having very different purposes. Okay, so hopefully with these things, I mean, and again, this is actually this is sort of a very initial notion. We're just starting to play around with it, I think. But hopefully like this at least gets you curious about this and maybe thinking that, hey, this might be an interesting kind of mechanism to tie together different notions of robustness. Which raises another question now, which is, okay, so maybe you sort of buy that this is an interesting notion of robustness. How do we actually go about computing this? How do we compute, you know, intermediate Q robustness, right? L or Q. I don't want to use LQ because that always sounds too much like the threat models we're going to use. But the intermediate, you know, Q robustness for our loss function. So the first thing I'll mention is we could use a simple Monte Carlo estimator, right? That's actually really simple to do. So one thing we could do, if we want to compute an estimate of this quantity, the LQ, L superscript Q, which is shorthand for our metric that we care about here, is we could just sample a bunch of samples from our distribution, and then just compute the empirical LQ norm of those samples, of the loss of those samples, right? That's sort of the easy thing to do. So I think I'm missing I'm missing a 1 over m here. I should be here. Love the mouse drawings, I'm sure. But the first time I'm giving these slides, there's going to be typos in session. Okay, so we could do that, but this is a really bad idea, right? Because as you would imagine, right, this is never going to find those rare events that we care about. So the whole point of adversarial robustness, right, is that it really does look for worst case examples, right? It follows the gradient of your loss to actually find worst case examples. This method here it completely ignores the gradients, right? And so it's going to be a horrible method. I mean, it's like like the simplest possible 0th order estimator of adversarial robustness. You just sample a bunch of points randomly within your ball, and then, you know, if you're looking for like the adversarial robustness, so for the Q equals infinity case here, that would just then return the worst of those, right? It's a horrible idea. That's no way to sort of definitely no way to sort of find actual adversarial examples in practice. Now I should mention there's a whole bunch of ways we could do it. So you see there's any number of methods we could use to actually compute the intermediate Q, you know, to do sort of like the sampling of rare events to compute an estimate of this quantity. But I want to focus on one particular way of doing it, which I think is really, really cool. And it's essentially looking at a Monte Carlo estimation task using MCMC. So I'm going to spend some time on this because I think it's really neat. Actually, the next slide will be the real sort of mathy one, but sort of go from there, or maybe two from now. So what we're going to do is something kind of strange. We're going to think about this quantity that we're trying to integrate, essentially, right? So we're trying to compute the integral of this quantity, and then we'll take the qth root of that, or the 1 over qth root of that. Wait, no, the qth root, right, to the power of 1 over q. So we're going to think of a density which is equal to this thing. Okay, so remember, we're trying to, sort of going back a few slides, we're trying to compute this integral here, you know, over the loss. And the way we're going to do that is I'm just going to define some density to be equal to that thing, an unnormalized density, right? I think this is not integrate to 1. I'm gonna define our density to be equal to just this thing. Okay, and now the problem of computing our robustness metric for any Q is just the problem, or computing the robustness metric is just the problem of computing the Qth root of the partition function of this density here, right? So if you think of this as an unnormalized density, what we've done by casting it this way is framed the problem of computing our intermediate Q robustness metric as one of computing the partition function of this unnormalized density. All right, so great. I've replaced one really hard problem, which is computing a high dimensional integral, with another really hard problem, which is computing the partition function of a distribution, which of course are exactly equivalent. So I haven't really done very much yet. Just sort of said it in theory. So the problem, right, as I mentioned, is that computing the partition function is hard too, but we nicely now have a very large number of tools at our disposal. In particular, one of these tools is something called path sampling. I was not familiar with path sampling until we all started working on this project. But it's really a beautiful approach, and it simplifies really nicely in this case, to the point where I kind of want to have a few slides on it just because I think it is so pretty here. And essentially what it does is it transforms the problem of estimating the partition function into one of sampling from the unnormalized density. And of course, this is also hard, right? So all these things in probability are hard. But somehow this task here, sampling from an unnormalized density, this is actually in some sense a better studied problem. And in particular, methods like MCMC methods are very sort of well understood and very well tested for these kind of things. And as we'll see, there's some really interesting connections here between these and our approach. Sorry, there's interesting between these and sort of standard approaches for adversarial robustness, like just PGD based attacks and stuff like this. But there are, of course, many other approaches, and I actually suspect that if this ever catches on, the first thing people will do is find better estimators for what we're trying to compute than what we've done here. But nonetheless, I think this is actually a really cool kind of estimator that we can form for these sorts of things, and I want to take a little time to describe it. All right, so now you'll sort of permit me maybe 5 minutes to talk about path sampling. The math is kind of cool enough, and I think interesting enough. Maybe it's all known. I'm sure this is probably all known by people in some branches of Bayesian statistics, but I haven't seen this before. So I thought it was very interesting, and I think particularly in the case of this robustness metric, it simplifies in ways that are really interesting to make a really sort of simple and elegant estimator for this function that I think has all sorts of applications. Okay, so what path sampling is a method that computes integrals like you've seen by basically iteratively sampling from more and more kind of annealed forms of the distribution. So this is not like that this is a fairly standard kind of way of thinking, right? You start off with like a uniform distribution of your whole space, and you gradually become more and more peaked in your distribution. You sort of do an MCMC step that kind of gets you more, or so like a Monte Carlo step that gets you more and more toward the peaks as you increase like the annealing factor. And that's sort of how this thing works in practice. Is that you sort of anneal the distribution starting from one that's not very peaked, or basically from Q equals 0, which everything is just uniform, to a version that's very peaked. And the idea that we're going to do is we're going to consider an annealed distribution. So we're going to consider this annealed distribution with its annealing parameter t, and t is the thing that it's just like Q, but it's going to vary between we're going to vary it between 0 and our final Q that we want. Okay, so we define our normalized density as just this thing with t. We define the partition function similarly as z of t is this sort of thing, and we define the true density as the normalized version of our density. So everything is simple so far, and now's the slide full of tricks that it's going to be impossible to sort of I'm maybe being very unwise to put these on a slide, but I think it's cool enough that I kind of wanted to. Okay, so there's a bunch of tricks that sort of are associated with path sampling, and they basically work like the following. So first of all, there's this sort of standard likelihood ratio trick you can do, which basically looks at it's like the same thing that like if you've ever seen reinforce in reinforcement learning, it basically is the same thing. It converts a derivative of some complex kind of integral to an expectation of some computable derivative. Right. So I won't go into why this is true. This is sort of like, you know, 3 lines of pretty simple kind of integrals. You swap integration and differentiation and stuff like that. And you use the fact that, you know, the derivative of a log term is just 1 over that. It's just derivative of the inside term divided by the outside term, right? And so you can just play around a little bit, and what you get is that the derivative with respect to t of the log of the partition function is equal to some expectation here. And the nice thing is that in the case of intermediate P robustness, this is the derivative of the log of our unnormalized density with respect to t. Well, going back a slide, so remember this is the log of this unnormalized density. Well, going back a slide, the unnormalized density is just the loss to the t. So if we take the derivative of this thing, the log of this thing with respect to t, we just get the log of this, right? So that sort of simplifies, and you just get the log of this thing. So that's nice. Now we can actually, in order to compute the one thing that we want, we're going to take this term, this derivative term, and we're going to integrate it from t equals 0 to t equals q. Right? So we're basically going to take this derivative and use the fact that the final thing we care about, or the log of the final thing we care about, is the value at q. And so it's going to integrate this inside thing over that range. And when you do that, you know, again, swapping kind of integration and expectation, or, you know, using the definition of integration expectation, what you find is that the whole thing you care about is actually just a bunch of expectations. It's an expectation of t drawn uniformly from 0 to q, but you actually end up sort of sampling that uniformly to integrate from, or to anneal from 0 to q. Then delta samples from this annealed distribution, and then the log of some term there. And finally, in the last step, this is, I promised the last time I'll deal with too much math here. If you do Monte Carlo integration to generate samples from this thing, and then sorry, not Monte Carlo, if you do like MCMC sampling to generate samples from this distribution here, then it turns out that you can compute the exact sort of quantity you care about by just actually generating a bunch of samples from this exact form here. And then taking their geometric mean. So like the fact that there's a log term here essentially makes, and you want the, you want the exponential of this thing. You swap logs and sums and exponentials, and you end up getting the geometric mean of the loss terms. So I think that's just to me super interesting. That like I don't know why I haven't seen this before. But it seems like a really sort of nice result that basically in this particular case of this particular integral we're trying to compute, you simplify to having the metric you care about is just a geometric mean of a bunch of different losses. And so that seems really interesting. Okay, so now popping back up, ignoring past sampling for a bit. Generating, okay, so you know this all looks lovely, but I'm sort of ignoring one big point here, which is that in order to compute these things, you still have to sample from the unnormalized distribution, right? You're still talking about generating samples from this distribution you can't sample from, or you can't generate samples from loss to the q of something or loss to the t of something. That's the density you can't sample from. So what you can do though is you can use MCMC methods to approximate samples from this. And the cool thing about this, I think is really interesting here, is that if you use a gradient-based MCMC technique, which is what you want to do, because you don't want to just generate random samples, take random steps, unless you have to. But what you really want to do is use the gradient information, just like we do in adversarial attacks. What it turns out is that the updates you make with Hamiltonian Monte Carlo end up looking a lot like scaled PGD attacks. So you're basically taking updates, you're making updates in the gradient with respect to your parameters, your perturbation of not actually the loss, but the log of the loss, which is again going to like scale the loss by its, the gradient of that thing is going to be basically a gradient of the loss scaled by the loss. It's kind of interesting. I mean, we tend to scale losses anyway when we take like normalized PGD steps. And so there seems to be really interesting connections here between running Hamiltonian Monte Carlo on this particular distribution and actually running PGD attacks. Now, to be very clear, I mean, you don't do as well at just attacking it as a PGD attack. That's hopefully not surprising to anyone. You're adding randomness. You're doing like reflections on the boundary instead of projections to the boundary. Otherwise, you'd have too much of probably mass on the boundary, and you don't want that. You want it to be in the interior of the ball. So there's lots of things that are sort of finicky to get it working right, but it does work. So let me now show you like a mass of numbers that sort of I will then explain. I will explain them. I always tell my students never to show something like this. Whenever you have a mass of numbers, you want to show the a bar chart that does it instead. But I just didn't get it ready in time, so you're going to see a mass of numbers, and I'll try to explain what they actually mean. Okay, so let's look at this column here. So this column here is different training methods. This is an MNIST classifier with L infinity perturbations of 0.3 in the L, so sort of normal kind of threat model, trained, with a bunch of methods. So this column here is different training methods. We can train it with standard methods. And I'm sorry, it's again old notation here. These P's should all be Q's, so that's the degree of robustness we're talking about here. So this is standard training. This is random sampling with Q equals 1. So that's sort of random, just random sampling. Then you can also do sort of the simple Monte Carlo estimate that scales the things and takes the empirical LQ or LQ norm, but doesn't actually do a good job of sampling that. Or you can use the Hamiltonian Monte Carlo method to sample these things. Okay, and so these are the different training methods that we have on the y-axis here. And finally, we can also train it, of course, with PGD 50. You can train MNIST that way too. And then what you have on the horizontal axis here are different evaluation methods. So we can also use different methods to evaluate how robust the model is under these different robustness metrics. So we can either use random sampling with some number of total samples, or we can use Hamiltonian Monte Carlo with the same number of total samples, but Hamiltonian Monte Carlo like divides them up into like samples and then leapfrog steps and stuff like this too. I forget what they're actually all called, but with the same number of samples in Hamiltonian Monte Carlo, but again, using the gradient information to get a sense of what the real robustness is. So here's how to sort of read this. If I take a standardly trained model and I evaluate it with sort of normal loss, I get this as my loss. And this is cross entropy loss. Remember, we're talking about the smooth loss function here, not the 0-1 error, but the actual smooth loss function. Now, if I start evaluating just with random sampling other amounts of robustness, I see that as I increase my P or my Q in this, what I'm calling Q, the loss increases, right? As you get worse, more and more sort of closer to worst case robustness, things get bigger. But random sampling is really bad at sort of finding the real value. And then I guess if I run PGD, I get some very high loss here, right? But this is actually quite bad at finding these things. And what we find is that not unsurprisingly, if we're able to use gradient information in Hamiltonian Monte Carlo, we get a much better estimate of the sort of actual intermediate Q robustness here. It's hard to know what the actual right answer is here. I mean, we can't get these integrals analytically, but this seems to be much closer to the actual worst case robustness that we're talking about here, or getting toward the worst case robustness, because evidence for the fact that we have much higher losses here, right? So we know the worst case is here, and we would expect that as P goes to infinity, we would approach that. But actually, P sort of increases like logarithmically. Like you actually have to get very, very high to have worst case, but it is increasing kind of nicely. And then similarly, when we train, so this is, we can use training methods where we also have training. I'll get the question. I see there's a question there. I'll get to it in a second. If we do different training methods, what we see is that maybe non-surprisingly, as we do different training, our estimates of the corresponding LQ robustness also go down. So if I train for Q equals 1000 and evaluate on that, I get a much lower loss than if I do something else. And actually, if I train adversarially, I give an even lower loss at the not in MNIST, unfortunately, but we have some results on CFAR too. And at the expense of some clean accuracy, you get much lower robust loss. But what we see is that also not just for evaluation, but also for training, these losses get much better, or these get to be better estimates, and they are better controlled. So if you just train based upon random sampling, it does not do as well as training based upon the Monte Carlo methods. Yeah, so this is quite a scribble of a slide here, but if you'll apologize, hopefully it conveys the rough message. It was a question though.
Hey, yes. So if I understand correctly, so you're estimating the same thing using two different methods.
Yes. So like this column and this column are the same. They are. I mean, obviously Q equals 1 and PGD 100. Those are different. Those are actually different, metrics of robustness. But this column and this columm are the same. One's just generated with random sampling, the simple Monte Carlo estimate, and one's generated with the HMC. So the basic idea is like this one here is a much better estimate of the actual quantity than this one is.
Yes, and is it fair to assume that, for example, if you increase the number of samples in random sampling, you'll get a better estimate, like what?
Yeah, but it essentially will take basically forever, right? Because you're trying to cover an exponentially sized ball with just random samples, and you can't do that, right? You need some gradient information to actually find anything. In fact, actually, let me go to the next slide to show you this, the actual plot here. So this is actually showing the number of iterations. So that's the number of samples, right? And how the estimates start to converge over a number of iterations. So we don't actually know in some sense the true LQ robustness, right? But we probably have pretty reason to believe that at least for these simple sort of problems, the HMC estimator is pretty good, right? And in fact, it seems to sort of be leveling out, which is a good sign that it's, actually, I take that back. It's not necessarily a sign of anything. The unfortunate part about probability is you can never tell. But for Q equals 1, right? So if you're just doing random sample, basically, if you're just trying to ask for the L1 norm, or the L1 functional norm, it doesn't matter. You can just use random sampling. But if you have one of these higher intermediate Qs, which is what you care about, right? So the time where you really inject a bit of this other case, then what you find is that it really is important to use these HMC estimators in order to get a good estimate of these things. And again, this is sort of very preliminary in a lot of senses, and that it's just sort of proposing a new metric of robustness and proposing a way of evaluating it, and showing that it can be useful in some cases, I think, to consider these things, but there's a ton more work to be done. In fact, let me actually just finish up by saying a few more things. So the same thing actually so the thing I want to emphasize is this is not just limited to norm ball threat models. You can also apply to threat models that take into account things like crop, horizontal scale, and flipping, etc. This is what's typically used, for say data augmentation, stuff like this. And you have a similar story holds here, where you basically want to you want to use these HMC methods, especially when you have higher values of your intermediate Q function. Okay, so I'm out of time, and I want to have some time to finish up now and take a few more questions maybe. What I've shown so far is really just in some sense an initial stab at thinking of the world of robustness between worst and average case. I think that we often think about worst case robustness as just the robustness. That's what robustness is. That's certainly how I think about it for a while, but that's not really what people actually often want from robustness, right? It's like these performance in these measure zero sets maybe isn't really that important. And At the same time, you probably also don't want to consider just sort of the average case, right? Just, you know, some distribution, what if distribution is wrong? What if, the whole point of robustness is you somehow want to account for the, you know, these worst case effects. And so I think it's really valuable to think about what falls in between these two extremes. You know, what we've presented in this work and what will be coming out soon in the papers is this you know, one attempt to deal with what falls in between these two extremes, and one way of estimating that, and then, you know, incorporating it into training, into evaluation, etc. And really, what I hope to do here is at least, you know, get some people thinking about these new possible directions in robustness, and what we could do sort of to go from here. So with that, say thank you to everyone for joining, and I'm happy to answer any questions. I would normally say that the paper is on my website, but it's not yet. So will be, well, it is listed actually, but I think it's it doesn't exist yet in actual final form. So we'll soon.
Hey, Zico, I have a question if you have.
Yeah, absolutely.
Thanks for the talk, by the way. So this is kind of reminiscent of the tilted ERM. I don't know if you have that work.
Sure.
It's one of Virginia's, right? It's, you know, it has this nice smooth interpolation process between worst case and average case.
Mm-hmm.
When you like interpolate here, do you also see like a smooth interpolation between, let's say, like the performance drop off, as you know, as you make a more robust model, the folklore says that you're gonna have to pay some clean accuracy.
Yes, you do. I'm trying to see. I mean, you know, it's unfortunately this is a bad example to show it because MNIST everything does fine, so everything works fine on MNIST. There's no accuracy penalty you pay for doing robust training on MNIST. But yes, when you train you CFAR into the ones, yes, you absolutely do. One interesting thing though, which I think is really cool, is it isn't maybe as bad as you would think though, because we know that as you move to Q, you know, from Q equals 0, which is like, guess what would that be? That would be, well, Koza doesn't really have a great meaning here, but ignore that. As basically you sort of step up from Q equals, you know, Q equals, basically, as you step from just using the pure data points themselves to Q equals 1, we know we actually see a huge performance boost, right? And we know that because data augmentation, i.e. random insertion of perturbations in some model, works better than nothing at all. So that's sort of interesting, right? There's actually at training time is a performance boost from Q equals 1. I believe, we have not seen it yet. I'll be fully honest. I believe there are probably cases where you would get a similar boost from small q. So from q equals 2 or q equals 3 or something. Once you start going to the point where you're approaching adversarial loss, you're definitely going to get a decrease, because we know as q goes to infinity, you get worse performance. But I think there is actually room for benefiting at training time from this intermediate regime. And I think it's really worth thinking about.
Right, thanks. Yeah, I'll keep an eye out for the paper, and maybe there's some better like CFARish experiments.
Great,
give some insight there.
Yeah, they're still small scale. To be clear, we're doing this in small scale, and it doesn't improve clean performance yet on CFAR, but it does. But you are able to estimate sort of these differences. Yeah. Maksym.
Okay. Hey. Yeah, so basically, thanks a lot for a very interesting framing of the robustness problem. So, okay, so my question is about, okay, so why not using the loss interpolation, like basically like you mentioned, right? So basically lambda times expectation plus 1 minus lambda, then you just interpolate that. So is there some, I don't know, conceptual advantages?
Okay, sure. So the way you can kind of think about this is, I mean, okay, so why do I think that that's worse as an interpolation, right? So Q equals 1 looks at the lost landscape over your ball and just says like, okay, I'm just going to take that lost landscape and I'm going to average over that whole lost landscape, and that's my loss, right? That's Q equals 1. Q equals infinity says I'm going to find the single worst point in my lost landscape and go there. And I don't think a nice interpolation is to just sort of have a mixture between a delta function and a nice smooth distribution. I think what you want in an interpolation is you want something that smoothly interpolates between the two distributions themselves, right? That sort of becomes, shifts the loss from, or the distribution from just the loss itself to slowly the peaks that end up being a single peak at the maximum. I don't think that it's very sort of unsatisfying to have a mixture distribution that sort of just says, we're going to slowly fade out this nice, smooth thing and just replace it with a single point. It doesn't capture multimodal behavior. It doesn't capture all these things that you think you want in a nice interpolation. So I think, modulo the fact that it's harder to compute, I think this is a much nicer estimator of loss of robust loss that we should be focusing on. And I think whether or not we really can focus on it depends on whether or not we can sort of quantify it accurately. But this is a philosophical question, right? I just to me, when we talk about interpolating two sort of distributions, I think of one that sort of shifts one function to the other function, not one that just sort of fades out one function, like a mixture that's like you flip a coin that sometimes one function, sometimes the other function, right? That seems very unsatisfying to me.
Okay, thanks a lot.
Okay, so is there any questions from audience? We still have time for maybe 2 more questions.
Maksym, is another question, or is that your old hand?
Yeah. It's a new one. Right. It's kind of follow up on the previous one actually, right? So, what would be the performance metric that you are optimizing in this case, right? So, okay, so you showed this kind of table with different, different values of the loss, right? So, like, is it something like, yeah.
Sorry, sorry, actually go on. Sorry, I was interrupted. I jumped right in. What's the loss metric we're optimizing is your question?
Yeah, like what is the performance metric? Like, is it some balance between accuracy and robustness, and how do you
no. So the loss metric is always just the intermediate Q estimate of the loss of the robust loss. So for these things here, right? So when I train with HMC p equals 10, we compute the actual estimate of this loss function, and then we optimize that. And the nice thing, by the way, is like, there's a really easy form for this, right? It's just the geometric mean of losses. So you can backprop this really easily, right? You can actually do a really nice job of optimizing this if you want to, because you just generate some samples. We know that our estimate we're trying to minimize is the geometric mean of this thing. So we just minimize the geometric mean of losses. It's a really sort of nice way of converting between kind of this is another thing that's really elegant, right? So the fact that path sampling gives you this really simple form at the end, which I know there's a bunch of logical leaps here, and I don't expect anyone to sort of follow with all of that. But the final statement is our final loss is just a geometric mean of losses evaluated at a bunch of samples of perturbations. So when we optimize them, actually, this is optimizing in the case of this HMC method. All we're doing is we're trying to optimize this function here, right? We're trying to optimize this LQ robustness, but what we do in practice is that we just backprop through this thing, right? And that's very nice. That's sort of very easy to do, and really kind of works quite in a quite straightforward manner. So that's what we're optimizing in these things. We're trying to optimize this metric. I mean, again, this is defining a different metric, right? So it's saying like the metric we have is different, and we want to optimize that and then evaluate it as well as we can.
I see. But out of all the models that you, let's say, presented in the table, like, is there some way to say which one is the best, like the most desirable model?
So again, I mean, so I guess here you could sort of probably say that the best is the PGD model here, because PGD on MNIST does really well. It doesn't really sacrifice any standard error, and it has lower error on all of these other metrics too, right? So like the p equals, so I would actually say very clearly the best model is the PGD model. On other data sets, right, this is an inherent trade-off that you can't balance, right? So PGD will be better at worst case performance, but worse at standard performance, and these intermediate ones will be better at their intermediate level of P and worse at other ones. Now, you might ask, like, well, why is the one that optimizes P equals 3000 worse than PGD on that? And the answer is that PGD because this is an imperfect estimator, you know, PGD in optimizing the worst case on MNIST is actually able to basically sort of, you know, run the table essentially, right? It's just really, really good. I probably shouldn't have included MNIST here, but it's just the most exhaustive set of experiments we have. So in this one, actually, is pretty clear that PGD is the best one. But for other settings, there definitely are settings where you get worse performance on I mean, even here, right? Like, I don't want to interpret numbers as meaning too much in this, but you know, if I well, actually, let me go back. You know, if I train for, actually, no, I'm gonna ignore this because this is all just sort of random noise at this point, and like in this one, these are all essentially equivalent. The thing I will say is that for other data sets, of course, there are more obvious trade-offs involved, where when you optimize for one of these metrics, you do better on that metric, but worse on other metrics. And it's just one more metric. You can't really compare the two because it depends which metric you care about. Here you can say pretty uniformly that the robust model is the best. That's not true for other ones. But the point is, like, it's not as if we would just then take our trained models and compare their clean versus robust performance. The point is that's an incomplete set of metrics. You actually want to compare their intermediate Q robustness as well, to understand how they do on that metric that you're optimizing for.
Okay, thanks a lot.
All right, well, I think it's 5 o'clock, so I will turn it over to Greg if he's here.
Okay.
Thanks very much, everyone.
Thank you, Zico. Thank you for this insightful presentation. And that's definitely pointed out a new direction for the community. And let's move to next talk. Okay, so welcome Greg Young. So Greg Young is a researcher at Microsoft Research AI in Redmond, Washington. And he joined MSR after he obtained a bachelor's in mathematics and a master's degrees in computer science from Harvard University, respectively, advised by Chen and Alexander Rush. He won the Hopes Prize at Harvard for best undergraduate thesis, as well as honorable mention for the AMS-MAA-SIAM Morgan Prize, the highest honor in the world for an undergraduate in mathematics. Okay, and let's welcome Greg Young.
Thanks, Kaidi, and thanks all the organizers for inviting me to speak here. And thanks again, Zico, for a nice talk. So I'm going to jump right into it. So I'm presenting the work randomized smoothing of all shapes and sizes, which was done in collaboration with Tony Duan, Edward Hu, Hadi Suman, Leah Reichenstein, and Jerry Lee, based on work from last year. So everybody, knows about adversarial examples. He adds some unnoticeable noise and he changed the label of an optimizer on an image. And people have come up with different ways of countering this. One way is empirical defenses, where you evaluate on the best empirical attacks, and you hope that this works on future attacks and stays effective. And methods are usually based on adversarial training. And then there's another class of certified defenses where we want specific guarantees under specific threat models that our defense work. And as we've seen recently, methods based on randomized smoothing essentially are LP adversaries repeatless and infinity. And other defenses fail to scale to ImageNet. Now, let me just briefly review randomized smoothing, but probably many of you already know and are familiar with what it is. So the core idea is that even if a classifier is not smooth itself, we can always smooth the classifier by convolution with input noise, with random input noise. So, operationally, when you do inference, what you're doing is, you have a neural network F, and you're interested in predicting on an image like a cat image X, and you would sample, say, 100 noise, ID noise from some distribution like Gaussian, for example. And here we're denoting that as delta I. And then we're adding the noise to the image and passing the 100 X plus noise to through the neural network and get 100 different predictions of the classes. And then finally, we take the majority vote, right? So if like 70 votes of the 100 votes cat, then we're gonna output cat. And mathematically, what this is doing is just measuring the measure of the region of the cat decision region under the measure of the distribution of delta, right? And for certification, to guarantee that we are robust, we just say that the larger the winning majority vote, the more robust it is to the perturbations of X. And more precisely, there are these functions you can calculate, which takes the normalized majority vote count, right, from like 0.5 to 1, and then gives you a certified radius from that number, right? Okay, so hopefully everybody's already familiar with this. Is a good enough review of randomized smoothing. And there are some basic questions regarding randomized smoothing, as early works focus on simple distributions such as Gaussians or Laplace distributions. So for example, it's natural to ask, how do we certify general smoothing distributions against general LP adversaries? What's the optimal smoothing distribution for an LP adversary? And what are the fundamental limits of randomized smoothing for LP robustness? Okay, so I will go through each of these questions, offer some answers, but I'm gonna focus mostly on the second and the third questions. But let me first tell you about some new techniques that we've developed for certifying general noising distributions. And this will be necessary for our general explorations of the later questions, where we test a lot of different distributions. So again, I'm gonna very briefly go through this, and because at the core, this is also very mathematical, so I'm gonna be skipping most of the math and just focus on the high-level insights. So we contribute two different methods for certifying general distributions. The first method is the level set method. So again, I'm going to use language that probably only makes sense to the people who have thought about this before, so I don't have to delve into details. But the level set method is based on a clever integration of Neyman-Pearson sets, which are like sets that optimize a certain, like the robust certificate, using level sets of smoothing or the smoothing distribution. So essentially, we look at like a Gaussian or something, and then we slice the distribution horizontally, and then we integrate the level sets in a particular way so that we get the Neyman-Pearson measure. So the advantage of this method is that it's exact but numeric, and yields a table of robust radii that you can use to do lookup when you get the majority vote counts. So that's one method. And then another method is called differential method, where we compute the largest possible infinitesimal increase in the measure of Bassett, where Bassett means like the region of the wrong class. And we compute this largest possible infinitesimal in this measure due to an infinitesimal adversarial perturbation, right? So like in general, for randomized smoothing certification, of course, we're not interested in just infinitesimal increases, but we want to also like understand what's the largest possible increase for some fixed L2 norm 1, right, perturbation. But the idea here is that it's easier to understand what happens if you have infinitesimal adversarial perturbation, and then to get a bound on a fixed size perturbation, you just integrate this infinitesimal increase over this range. So the disadvantage of this is that it's inexact compared to level set method, but the advantage of that is it yields symbolic expressions of robust radii, which is easy to implement, easy to verify the implementation, and is quick. And it turns out in high dimensions, it's really pretty close to the true robust radius. Okay, so again, I'm really very quickly going over this, but people can definitely ask for details or go look at the paper. And I'm going to summarize this part by just like looking at summarizing the distributions that we cover with these two methods. So here the picture is arranged in terms of bubbles. Each bubble is kind of like a distribution, a family of distributions. And with each family, we also denote the LP adversary that we target, right? So for each bubble, we provide adversarial robust certificates for that distribution against that adversary. So for example, we have the common Laplace uniform Gaussian that everybody knows, but we also have more exotic ones where we have like exponential to negative some power of x, p norm to some p power, and these distributions are ID log concave distributions. We give L1 adversary certificates. These three bubbles correspond to different shapes of their level sets. So cubical means that the level sets have cubical shapes. Spherical means that the level sets have spherical shapes. And cross polytope means, of course, that the level sets are cross polytopes. And we also explore a lot of different tail, how the distribution's tail, how heavy it is as it goes to infinity. So we have, for example, polynomial tails, and we also have exponential tails. And then we also have some exotic ones like ID log convex distributions instead of log concave. Okay, so this is, again, just a very quick overview of the plethora of distributions we cover in here. And this will be important later on when we like exhaustively, theoretically and empirically explore the effect of distributions. Okay, so this is what I really want to focus on here. The question is, given an LP adversary, what's the optimal distribution for smoothing? And to get at this answer, it's really helpful to start with a uniform distribution over a convex body S of volume 1, right? So then the distribution is just, the probability is 1 at every point on S. Okay, so when we have an adversarial perturbation, say V, what that's going to do is it's going to shift the distribution by V, right? And if you have a bad set U, again, a bad set just means like the wrong classification, the region corresponding to the wrong class. Then the measure of U is going to, of course, change when you shift S by V, right? In particular, the measure against this uniform distribution is just the volume of S intersect U, or S plus V intersect U in this case. And in particular, as an example, if, as in this picture, the volume of U intersect S is less than 1/2, but the volume S plus V intersect U is greater than 1/2, then your label has flipped, right? Because originally you would predict, let's say the white region is cat and the black region is dog, but then after shifting, you would predict dog because the measure of U now is larger than 1/2. Okay, hopefully this makes sense. Any questions? Also, I can't really see any hand going up, so just feel free to shout anything out. Okay. All right, so to be robust means that you want to make sure the volume gain by U when you shift S is as small as possible. So we need to figure out how much volume is gained by a shift by V. And the easiest way to understand this, to visualize this, is you rotate this picture so that the horizontal axis corresponds to the V direction. Then the volume gained by U is just like this region here, right? Like S plus V minus S. And if you just like visually collapse this to the left, you get a shape like this, where like the shape has the same volume as this shaded region, which is a volume added gained by shift by V. And if you think about it, if V is very, very small, then this volume is approximately equal to the 2 norm of V times the volume of projection of S in the direction V, which is like this line segment, the length of this line segment in this example, right? So like, in other words, like the volume of this is approximately just the base times the height, right? And one way to visualize this more, or to understand, to grok this more, is that you can think of volume of this pi vs, the projection of S in the direction V, as what an observer sees if this observer is looking at S from direction V. Right, so you're looking at this. This is like what part of S is actually blocking your view. Okay. Any questions here? Great. So again, to be more robust to perturbations means we want less volume gain when we shift by V, right? So to be optimally robust to all perturbations V from a set B, like say an LP ball, means that S should look small from all directions of V inside of B. And if you want to put yourself in the shoes of S, this means that you want to like look slim, from all directions V inside of B. So you want to be Instagram ready in all directions in B. And this means that S must minimize some sort of surface tension defined by B. So, so if you want to put yourself in the shoes of S, you want to minimize your fashing in front of Instagram. And this means that S is the Wolf crystal with respect to B. Okay, so what is a Wolf crystal? By the way, this is kind of a non-trivial connection here, but let's look at Wolf crystal here. So this is the formal definition. So Wolf crystal with respect to a set B is defined as a unit ball of some norm dual to this other norm, and this other norm is defined kind of as like the expected correlation of the vector X with random vectors from B, from this set B. Okay, so this probably doesn't really mean anything to you at this moment, but let me first remark that this came from a century ago from physics, where people wanted to understand minimal surfaces. So essentially, like just as the round soap bubble minimizes surface tension for a given volume, the Wolf crystal also minimizes certain similar surface energies that arise when the crystal interfaces with another material. So soap bubble is like a typical example when the B is like the unit ball, L2 ball, but there are also other kinds. So for example, here are the relevant Wolf crystals for our adversarial robustness setting. So when B is the L1 ball, right? Your adversary is an L1 adversary. The Wolf crystal is a cube. And for L2, it's an L2 ball, kind of like by symmetry. And for infinity, it's not the L1 ball. It's like some more complicated shape, which is a zonotope in general, but there's not really a simple description of this in high dimensions. But in 3 dimensions, it looks like this. And the point I want to get across is that there's an optimality theorem with regard to Wolf crystal. So among all distributions with reasonable density functions, those with Wolf crystal level sets have best certified robustness against LP adversary, where the Wolf crystal is defined with respect to the LP ball. Okay, so this is the point I want to express. This is kind of the punchline of this section. Any questions about this? So next, we're going to talk about some empirical results, but I want to just pause to see if anybody are confused. Okay. Now, this theory is actually quite useful. It's not just idle chit chat. So, for example, compared to what people thought previously, where like for L1 adversary, Laplace was thought to be the best distribution, or of that shape to be the best distribution. We actually found cubic, where here in this example to be the uniform distribution, ID uniform distribution to be optimal for the L1 adversary. And here we're showing kind of the standard like radius, robust radius versus certified accuracy plot, where so you have Gaussian, which does the worst, Laplace does better, and uniform does the best. And here, like the gap is almost like 10 points at various places. So this is where like the Wolf crystal theory has the largest payoff. Now, for spherical distribution and for L2 adversary, you think that spherical distributions are the best, and that's indeed the case. And you don't need to really intuit this using the Wolf crystal theory. Now, for L infinity, there's a non-trivial prediction, but unfortunately for empirical evaluation, Wolf crystal with respect to L infinity norm is very complicated to sample and to compute in high dimensions. But for our purposes, this Wolf crystal is actually close to sphere in suitable senses in high dimensions. So correspondingly, we find spherical distributions also beat out other common distributions for L infinity adversary. So again, this verifies the theory, though unfortunately doesn't really give us any new numbers compared to what we had before. And recall all the distributions, the new certificates we obtained in our paper, and then people have wondered whether like how fat the tail, or like whether singularity at the origin matters. But what we found is that for the most part, the level set shape is the most important thing, and you can vary the tail. Like for example, here we're taking exponential to the L1 norm for different powers of the L1 norm, and for the most part, like the radii are about the same. But let me remark that there's a recent result by Levine and Fazy, which I think is pretty interesting. So far, we just considered additive noise, but they improved on our L1 results by considering non-additive noise, whose distribution does not have density, which is, and the noise is on a kind of a random quantization noise. And this bypasses the Wolf crystal theorem, because that theorem, one is about additive noise, and the other is about distribution of density. So it seems that from their paper, the gain mostly comes from the ease of training with their proposed smoothing distribution, rather than like better robustness given a majority vote count. Okay, so finally, let me quickly go over the fundamental limits of randomized smoothing, which is, even given Levine and Fazy's result, it doesn't bypass this limit. So far, the certification procedures we have talked about only uses the majority vote count, but it turns out this runs into fundamental limitations when the input dimension or number of images, number of image pixels, for example, is large. And this is the limitation whether the smoothing distribution is additive or not. So to frame it in the general way, consider a very general notion of smoothing scheme, which is a mapping of data point x to a distribution q of x. A q of x can be anything, right? So like so far we consider only additive schemes where q of x is like a shift of some q by x to center the x, right? But you can also consider non-additive schemes like Levine and Fazy did. And it turns out there's an inherent trade-off between two objectives. One is adversarial robustness, right? Where we want the majority vote to stay invariant within a large region of input x. And the second is classification accuracy, where we don't want qx to be too similar for different x, or else the smooth classifiers will be almost a constant function, right? So I mean, this is not a new trade-off, of course. Just like every time we do PhD and other stuff, there's always a trade-off of this. But here, like the key thing is that the trade-off is it gets worse and worse as your input dimension gets higher and higher, and this is like a rigorous no-go result. So this no-go theorem says that if a smoothing scheme emits non-trivially accurate smooth classifiers, then using only majority vote count, you cannot certify robust radius of essentially this thing, which is a scaling of input dimension as power of -1/2 + 1 over p against an LP adversary, where d is the input dimension. All right, so concretely, what this means is that for L1 and L2 adversaries, you can only certify radius of size constant. And for infinity adversary, you can only certify radius of size 1 over square root of d. So for example, like as your image size gets larger and larger, we go to 4K, we go to 8K videos and stuff like that. Like the amount of perturbations of each pixel for infinity must be smaller as the image size become larger and larger. Of course, like at some point it goes below 1 over 255 and it's completely useless. And again, like this theorem applies to anything that uses only the majority vote count, and this essentially applies to all currently known smoothing schemes in literature, added or not, except for, as far as I know, DJ's 2019 paper has a full information algorithm, and there's a more recent Mohapatra has a higher order technique for trying to bypass this thing. But so far, I think scaling is issue, or like the effectiveness of the method is an issue. Okay, so again, this applies to almost anything, and I haven't seen like convincing results that can bypass this barrier. Okay, so that's all my presentation. So let me conclude. So I asked 3 questions at the beginning. How do we certify general smoothing distributions against general LP adversaries? Here we contributed 2 methods, level set and differential methods, where I was very, very brief about what they entail. Second question, what's the optimal smoothing distribution for an LP adversary? And here the proposed answer is the Wolf crystal level set distributions. But you can be creative, and you can try like singular distributions or non-additive distributions that can bypass this particular optimality. And finally, what are the fundamental limits of randomized smoothing for LP robustness? And here is a lot harder to bypass. And here the answer is that if you use majority count only, we cannot certify robust radius of more than essentially d to the -1/2 + 1 over p power. Right. So for L infinity, we do not expect something more than 1 over square root of d. Okay. Thank you. That's my presentation.
Okay. Thank you, Greg. Thank you for your presentation. So I think we only have time for 1 quick question. So is there any question from audience? Okay. So if not, I have a quick question. So is the method able to like cover the perturbation beyond the LP known perturbation?
Do you have an example?
Like the transformation of the image.
Like rotations, the image?
Rotation or brightness change, something like that.
Yeah, so not directly, but for example, for Wasserstein, there's a reduction to, at least Wasserstein on L1, there's a reduction to L1 robustness in a different space. And on a different space, you can use our method.
Okay, thank you.
Mm-hmm.
Then, okay, then let's move to the next talk from Yizheng Chen. And Yizheng Chen is a postdoctoral scholar at University of California, Berkeley. Her work focuses on robust machine learning algorithms for security applications. Previously, she was a postdoc at Columbia University. She received her PhD in computer science from Georgia Institute of Technology, and she is a recipient of the Anita Borg Memory Scholarship. Okay, let's welcome Yizheng Chen. And Yizheng, you can share screen once you are outside.
Thank you for the introduction. Let me figure out how to share the screen. Okay. All right, I'll get started then. So I'm going to talk about our paper, Learning Security Classifiers with Verified Global Robustness Properties. This is joint work with my co-authors Shiqi, Yue, Xiaojing, Suman, and David. So this is a collaboration between Columbia University, Indiana University Bloomington, and the UC Berkeley. So security classifiers have been increasingly adopted by production industry to detect malware, advanced persistent threats, online fraud. All those internet giant companies and antivirus companies, they're using security classifiers to solve real world security problems. So what can go wrong there? For example, if we look at the application of using machine learning classifier to detect fake Twitter accounts, we may use features such as.
Oh, it's okay.
Okay, I'll continue.
Yes, please.
All right, so we may use features such as the length of username, the length of profile description, number of tweets, and following and follower counts. And this can be really good, like achieving really good accuracy to detect malicious Twitter users who spread malicious content on Twitter. However, if attacker just make a small change to the attributes of the account, such as increasing the number of followers by 1, this can evade the classifier. So what existing defenses can do is to ensure that similar inputs have the same malicious prediction. For example, in this case of malicious Twitter accounts, if attacker changes number of followers into a small range, like between 7 and 13, the classifier will still predict the perturbed Twitter account as malicious. So a lot of existing defenses, including adversarial training, certifiably robust training, and randomized smoothing can provide such robustness. So this is typically defined as local robustness, which makes the robustness guarantee for some inputs, but not all inputs. The problem with this is that for some other inputs, there is no robustness guarantee. Now, if the attacker makes a new malicious user, evil user 2, the classifier may still be able to predict correctly to make it as a malicious prediction. However, the attacker can predict the new input slightly, increase the follower count by 1, and then this will be predicted as benign. Now we go back to the same evasion problem again. So we were wondering in our work that can we train classifiers that are robust for all inputs? This is the definition of global robustness, which is a strictly stronger definition than local robustness. So in this paper, we propose new methods and algorithms to train verifiably robust security classifiers. Instead of providing guarantee for local robustness, we provide guarantee for global robustness. And currently, the standard of the art is to define robustness using a small LP norm ball. So we were wondering, do we mean robustness in the same sense? Does it apply to attackers that target security classifiers? So we looked into the threat models of how attackers may be able to evade different kinds of security classifiers. Specifically here, I'm showing an example of a malicious Twitter account user. Here I highlighted 2 attributes that are features, the profile description and number of followers. And we looked into how an attacker might modify those features to evade the classifier. So first we can see that the attacker can arbitrarily change the length of profile description. However, for the second feature, the attacker needs to spend money to increase the number of followers. So it is.
Sorry, Jen, sorry for interruption. So it looks like your slide is stuck at the page 6. Oh, now it's go to page 8.
Oh, okay. Okay, I think this may work now.
Yes, it works very well right now. Okay, thank you.
Okay, no problem. So the attacker makes different kinds of changes to these two features. And we notice that very often the attacker makes different kinds of large perturbations instead of smaller perturbations captured by LP norms. And these perturbations are still constrained in some ways. For example, by the economic cost of perturbing the features. Therefore, we conclude that we need new notions of robustness to capture the threat model of different attackers who try to evade security classifiers. So we propose several new global robustness properties. In particular, we formalize the threat models as the properties that we aim to achieve when we train security classifiers. In total, we have proposed 6 new properties. We have proposed 6 properties, and 5 of them are new properties. Here I will walk through one specific example of how we came to define this property called high confidence property. As we have just described in the threat model, the attacker can arbitrarily change the length of profile description. So we think that it doesn't make sense if the attacker can simply evade the classifier by changing this one simple attribute. We don't want the perturbations over this feature to cause a malicious prediction to become benign. In particular, we don't want any prediction that is already high confident to be changed to benign by this perturbation. So the property can be written as the following. If any data point is classified as malicious with 0.99 confidence, changing the profile description should not make it predicted as benign. Now, this can be generalized to any confidence level other than 0.99. And also, this can be generalized to any other low-cost feature other than the profile description. So in the general case, this will be the definition of the high confidence property. And we can write up a mathematical formula to define the property. And this will be one of the properties we're interested in training the classifier to achieve. So the previous example shows how we may use domain knowledge to define and specify the property. And in addition to that, we have also used economic cost measurement study to analyze attacker's threat model and specify the properties. So here is an example of how we specify the monotonicity property for the Twitter account classifier. So we wanted to measure what is the relationship between price of fake accounts used to spread malicious content versus the number of followers for this account. And we have crawled over 6,000 for sale posts from underground markets. Attackers usually buy those fake accounts and then set up this operation to spread malicious links and malicious content on Twitter. As we can see from the measurement result, the price of account increases as the number of followers increases. What this tells us is that in the threat model, for the attacker, it is expensive to increase the number of followers and relatively cheap to decrease the number of followers. So if the attacker conducts a cheap operation, such as decreasing the number of followers, we don't want the classifier to be trivially evaded again. So we specify this property that the output of the classifier F is monotonically increasing as the number of followers decreases. If the output of the classifier is higher, it means that the input data is classified as more malicious. So in order to evade, the attacker will have to spend more money to purchase more number of followers for the account. And this is the desirable result that we want to raise the bar for attackers to evade the model. So the detailed definitions of our other properties are described in the paper. And here I'll go through some of the intuitions we had when we define some other properties. For the redundancy property, we specify that the attacker has to modify different groups of low-cost features in order to successfully evade the classifier. This means that if for any input data that is already predicted as malicious, and if we have the high-cost feature and any one of the low-cost feature group, then we know it will still be classified as malicious. In other words, this makes different groups of low-cost features redundant of each other. We've also specified the stability property in the way that stable features should not affect the classifier output too much. And we've generalized that to a small neighborhood property. So this is different than the LP norm small neighborhood because we've defined a new distance metric. The new distance metric will capture the fact that attacker changes different security features by different amount, even after we normalize the features. So the details of the definition can be found in the paper. So after we have defined the global robustness properties, we want to train classifiers to achieve that. So to do that, we actually looked into a new type of discrete model. We call that the logic ensemble model. Because the model is discrete, that enables the verification of global robustness properties. And then we design and implement a new training algorithm for the model to achieve those verified global robustness properties. The logic ensemble is an ensemble of logic rules. So here I'm showing a simple example consisting of 3 rules for username length and number of followers features. If the username length is greater than 5, the first rule outputs -1. And depends on whether the number of followers is smaller than 100 or greater than or equal to 100. The second and third rule outputs 2 different values. And the output of the classifier is computed as the following. We first take all the rules that are true and take these outputs and then sum up the outputs. So it is a sum ensemble. For example, if we know the username length is 1 and number of followers is 50, only the second rule is true, and the other 2 rules will not have outputs to the sum. And so this gives the classifier output 2. Because the classifier is discrete, we can use an integer linear program verifier to verify the global robustness properties. And we have then designed and implemented a new training algorithm to achieve those properties. The goal of the training algorithm is, given a set of global robustness properties, we want to train a classifier with good accuracy that satisfies all the properties. Our key idea used when we designed this training algorithm is to use counterexample guided inductive synthesis, or CGIS. CGIS works as the following. So we need 2 components in overall. One is the verifier and the other is the synthesizer. So the verifier checks whether a candidate classifier satisfies the property. If it doesn't, it generates a counterexample, and the synthesizer will attempt to fix that. If there's no counterexample, according to the verifier, then the classifier is verified to satisfy the property. Here, the counterexample means an input that violates the property. Now, given this counterexample, the synthesizer can train a classifier such that this input no longer violates the property. Since classifier makes similar mistakes, satisfying the property for one input usually applies to multiple inputs too. And therefore, we're not only slowly trying to eliminate one counterexample at a time, but every time we're eliminating multiple counterexamples. And based on that, the synthesizer can propose a new candidate classifier for the verifier to check whether the new classifier satisfies the property. This process goes on until we stop on one of either 2 cases. Now, the first case is shown on the left side. When the verifier can say that at a certain point in time, the new candidate classifier satisfies the property, and then we have succeeded at finding a solution. Or on the right side, if somehow the synthesizer says we cannot generate any new candidate classifiers, because somehow we cannot eliminate multiple counterexamples at the same time. So this will result in a failure. So we actually cannot guarantee that the process gives you a successful result, but we do guarantee that the process terminates. And actually, empirically, we can find classifiers that satisfy all specified properties. This is true for all the experiments we run to train hundreds of models over different kinds of data sets. Now, I'll give you some intuition of how we implemented the synthesizer. We can think of a classifier under any hypothesis class as a set of all possible weights that we can assign to the classifier. So some of those weights may actually give us a solution to satisfy all the verified global robustness properties we want, as well as give us a good accuracy. So in the training process, our goal is to find the solution of the combination of those weights. So what the training does is to enforce constraints over the classifier's weights. Each constraint will eliminate some counterexamples. And over time, we accumulate those constraints to make progress towards satisfying the verified global robustness properties. At the same time, we want to minimize the classification error, so we can also maintain a good performance when we try to satisfy the properties. The detailed implementation of our synthesizer uses continuous logic networks. The details of this can be found in the iClear paper, where they first introduced continuous logic networks. But on a high level, we smooth the discrete structure of the rules and then do projected gradient descent for the training. So we also implemented a boosting technique to increase the accuracy and capacity of the model. So overall, the boosting works as the following. So we first generate a subclassifier F1, and this goes through the CGIS loop of verifier and synthesizer until the subclassifier F1 satisfies the properties we want. Then we will boost the classifier and add a subclassifier F2 and go through the loop and do the same thing again. So this repeats until we finished n boosting rounds. So we'll have n subclassifiers. Because our logic ensemble is a sum ensemble, so in this whole process, we can sum up the outputs from all the subclassifiers, and this will be the final classifier to achieve the goal. We have done extensive experiments to evaluate our new training algorithm over 3 public data sets to solve real-world security problems, including detecting cryptojacking, Twitter spam accounts, and Twitter spam URLs. Here, I am showing some of the key results when we train the verifiably robust models for Twitter spam account classifier. We compared our robust logic ensemble model against 4 baselines. 2 of them are regular training. They are XGBoost and regular neural network training. And the third one is generalized unconstrained monotonic neural network, which can enforce monotonicity property for neural networks. The fourth one is DL2. DL2 is a training technique that can allow neural networks to satisfy logical constraints for most of the training samples. So what we found is none of the state-of-the-art methods can achieve all 5 properties. Here, the question mark means that for the DL2 train network, we haven't found a counterexample using gradient-based attacks. However, we also haven't been able to verify this property just for a small neighborhood. On the other hand, we are the first to train a verifiably robust classifier with all 5 properties. Our training algorithm has modest impact on performance. So we have only 5.4% decrease in true positive rate and 0.1% increase in false positive rate. To conclude this talk, we argue that security classifiers need new notions of global robustness properties. And when we design the training algorithm, our key insight is that we can apply counterexample guided inductive synthesis to train verified global robustness properties. And lastly, we are the first to train classifiers that satisfy 5 new properties for real-world security applications. So our code will be available soon at this GitHub link. And now I'm happy to take any questions.
Okay, so is there any question from audience first? So if no, I have a quick question. So for the intuition of using a verifier and a synthesizer, so is that a similar idea to the GAN?
I wouldn't say it's similar to GAN, but this is this has been proposed for program synthesis. For example, you can do a checker and a synthesizer to synthesize static analysis rules. And the more complicated version will be you can actually synthesize real world code for developers. So this whole paradigm has been proposed in the program synthesis research.
Okay, thank you. Thanks for Yizheng, and I will move to another presentation. Okay. And Dr. Chen is an assistant professor in the Department of Computer Science and Engineering at University of Nebraska-Lincoln. He earned his PhD degree in computer science at Vanderbilt University in 2020. And his research interests are reachability analysis of robustness certification of deep neural networks, formal verification of autonomous cyber physical systems with learning-enabled components, safe and robust training for deep neural networks, real-time verification, and safe motion planning for distributed learning-enabled CPS. And he will give presentation titled Robustness Verification for Semantic Segmentation Networks using Relaxed Reachability. Okay, and welcome, Dr. Chen.
Thank you for, can you hear me?
Yes, I can.
Yeah, thank you for the introduction. I'm going to share, you see my screen, right?
Yes.
Okay, so today I'm going to talk about robustness verification of semantic segmentation networks using the concept called relaxed reachability. And this is the joint work between the University of Nebraska-Lincoln, Vanderbilt University, and Stony Brook University. So semantic segmentation networks usually used in perceptions in autonomous driving cars. And mathematically, a semantic segmentation network is a nonlinear mapping function that maps a multi-channel input image to a target class or label. Like other deep neural networks, semantic segmentation networks are also vulnerable to adversarial attack when slightly changing the input image can completely fool a very well-trained semantic segmentation network. So to use semantic segmentation network in safety critical applications like autonomous driving car, we need to have the methods that can formally verify or certify the robustness of semantic segmentation network. And this is the main motivation of this research. So how we measure the robustness of semantic segmentation network? Before we discussing this, I emphasize that a pixel is considered robust under adversarial attack if its classified label is unchanged under the attack. And as shown in the figures, as shown in the slides, under adversarial attack, a pixel class might be changed. Therefore, the first thing we need to worry is that we want to answer how many percentage of the pixels are robust under an attack. And secondly, we want to know that if how sensitive the network is under the attack. For example, if I attack 1 pixel, how many pixels might be affected? And the last questions we want to answer is that the accuracy of the semantic segmentation network is usually defined using the intersection of a union indicator. So, or shortly IOU. So in terms of robustness, what is the robust IOU of a network under an attack? So this slide shows the main idea of our approach that use reachability analysis to verify the robustness of a semantic segmentation network. So our approach have three main steps. First, from an input image X and the bounded nodes, we construct an input set that contains all possible adversarial images. And we represent this set using a data structure called image star. And then we propagate this image star input set through the network to construct a segmentation reachable set RF that contains all possible classes for all pixels in the adversarial image. And finally, we compare the segmentation's reachable set with the ground truth non-attack segmentation image to find out which pixels are robust, non-robust, or unknown under the attack. So we have introduced the core steps in our approach. Let's consider the first step. So we can construct the input set containing all possible adversarial images under a specific attack by using image star data structure. So an image star is a tuple containing a center image C, a basic image, a set of basic images V, and a set of predicate variables on far, and a constraint on predicate variable P on far, and the lower bound and upper bound vectors of these variables. And any image in an image star is a linear combination of the center and the basic images. And the figure in this slide is a small example of a 4x4 image whose one pixel in the orange color is attacked by a bounded distance between -2 and 2. So we can represent all possible adversarial images created by this attack by an image star as shown in the figure. So using image star data structure, we can perform the reachability analysis of downsampling layers such as convolutional, average pooling, mass pooling, fully connected layers. And the details of this approach can be found in our previous work published in CAP last year. So to analyze the robustness of semantic segmentation network, we need to perform the reachability analysis of upsampling layers such as transpose or related convolution layers. And fortunately, we can also do it very efficiently using image star because the image star data structure is closed under offline operations as proved in our previous work. So given an image star input set theta, the reachable set of a transpose or related convolutional layers is a new image star in which the new center and new basic images can be computed very quickly by applying the transpose convolution or related convolution operations on the center and the basic images of the input set. So the constraints on the predicate variables do not change in the reachability analysis. So after downsampling or upsampling layer, we usually use a nonlinear activation functions like a ReLU or TangH. And in this result, we focus on ReLU activation function, the more popular activation function used in deep neural networks. And we emphasize that our approach can also handle all the types of activation functions like sattling, liquid ReLU, TangH, or 6-more as well. And in our previous work, we have showed that we can compute the exact reachable set of ReLU layers using a sequence of step ReLU operations. However, the number of image stars in the exact analysis grows exponentially and thus cannot be used to analyze the robustness of a semantic segmentation network as we have a very high dimensional output space, like thousands of outputs. So the feasible solution to analyze the robustness for semantic segmentation networks is using an over-approximate reachability. And the idea is we can replace the step ReLU operations by an over-approximate step ReLU. And we relax the output of a ReLU function applied to each neuron by a triangle as shown in the figure. And we want also to we want to emphasize that we can also use over-approximation rules using zonal top or the new abstract domain methods proposed recently. And we can see that our methods use a less conservative over approximation rules compared with the Zhang and the new abstract domain methods. And to construct the over approximate reachable set, we need to use the lower bound Li, upper bound Ui of the input Xi of each neuron. So in our approach, we can find the optimal bounds of this input by solving linear optimizations. And we can also estimate these bounds quickly by using only the lower bound and upper bound vectors of the predicate variables. And in the Zonotop and the new abstract domain method, these bounds can be estimated quickly without solving any LPs. And therefore, these methods are very fast for large networks. However, they come with the cost of the conservativeness in the constructed reachable set. So this slide presents a small example of computing an over-approximate reachable set of a ReLU layer given an input is a 2x2 image star. So to apply the triangle over-approximation rule, so in previous slides, for each neuron, we need to find the range of each neuron. So using only the lower bound and upper bound vectors of the predicate variables, we can quickly estimate the ranges of 4 neurons. And using the estimated ranges, we can quickly neglect the neuron N21 and N22 in the analysis. Because N21 is always smaller than 0, so its output is reset to 0 when we apply the ReLU activation function on this neuron. And similarly, the N22 is always larger than 0. Therefore, the output of this neuron is equal to the input. So we only need to focus on N11 and N12. And the ranges of these neurons can be found exactly by solving 4 LBs. The question is, if I only want to use only 2 LBs in the analysis, which will save you like 50% of the total optimization times, which LBs should be selected to solve? And this is the key idea of our relaxed reachability methods that allows users to choose different levels of relaxation to reduce the verification time and construct a good enough reachable set for verification. So to answer the previous questions, we can use different heuristics to choose the LP to solve and construct the over approximate reachable set based on the combination of the estimated ranges and the exact ranges. So in this research, we propose 4 heuristics to choose LP to solve. The first one is the random methods, which randomly choose the LBs in the LB pool to solve. And the second one is the area-based methods, which optimize the ranges of the neurons with potentially largest a triangle over approximation area. And the third one is the range-based methods, which optimize the ranges of neurons that are with the potential widest ranges. And the last one is the bound-based range, bound-based methods, which optimize the ranges of neurons with potentially largest absolute lower or upper bounds. So this slide shows you the LBs that will be chosen by different relaxation strategies. Based on the estimated ranges, we can compute the area of the over approximation at neuron N11, which is smaller than the one at the neuron N12. Therefore, using the area-based heuristics, we will choose the neuron N12 to optimize the range. And after optimizing the N12 range, we have reduced the over approximation errors by delta S equal to 0.25. So when we use the range-based heuristics, because the estimated range of the neuron N11 is wider than the range of N12, therefore, in this case, we will choose the neuron N11 to optimize the range. And in this case, we also reduce the over approximation errors by delta S equal to 0.25. So when we use the bound-based heuristics, we will choose to minimize the upper bounds of 2 neurons because they have the largest absolute values. And in this case, we reduce the over approximation errors by delta S equal to 0.5. So we can see that different heuristics might produce different over approximation errors. And we will see in the evaluation that which heuristic is the best. So the last layer we need to consider is the pixel classification layer, which is responsible for classifying an image into a class. So if we have L classes, the input to the pixel classification layers is an image with L channels. And let's consider a pixel Xij's and its value across L channels. The channels that have the maximum value, for example, K, will be the class assigned to the pixel. And in the reachability analysis, the input to the pixel classification layer is an image star with L channels. And depending on the value of the predicate variables, each pixel in this image star can be assigned to more than one classes. In this case, we say the class of this pixel is uncertain or unknown. And to compute the pixel class reachable set, we need to find all possible classes of all pixels in the image star. And to do that, we need to find all cross channels mask point candidates of the image star. And the question is, how can we do it efficiently? Because we're gonna have thousands of pixels in the image star with L channels for each. So at a specific pixel, if we want to check the channel P value is a cross channel mask point candidate, we need to check if there exists a vector of predicate variables such that the value of the pixel at the channel P is larger than all other channels values, which is equivalent to solving a feasibility problem in linear programming. And therefore, to find all cross channels mask point candidates of an image star, we need to solve many feasibility problems, which is impractical for our application here. So can we find mask point candidate quicker? Yes. Again, we can use estimated range to quickly estimate the classes of all pixels in the image star. For example, as shown in this figure, if we know that the lower bound of the pixel in the first channel is always larger than the upper bounds of the pixel in the other channel, then the class of these pixels should be 1, right? So to evaluate our methods, we train a set of 6 semantic segmentation network with different architectures on the MNIST dataset and the M2NIST dataset. And we use different layers for downsampling and upsampling. For example, for downsampling, we use convolution and average pooling, or convolution and mask pooling. And for upsampling, we use transpose convolution and related convolution. So we experienced that different choices of downsampling and upsampling layers lead to different accuracy in training. So for adversarial attack, we consider the brightening or darkening attack, which is very common in autonomous driving, where you have shadow that darkens some pixel of the camera image. And the idea behind the darkening attack is that when the value of a pixel is larger than the threshold, it will be darkened. So to evaluate the sensitivity of the networks under the attack, we limit the number of attack pixels in the image by n marks here. So this slide shows the average robustness value, sensitivity, and IOU of MNIST networks with different size of the attack and number of attack pixels. And the average values are computed on a set of 20 images. And from the figures, we can see that the mask pooling network N2 is less robust and more sensitive to the attack than the average pooling network N1, because it have lower average robustness value and IOU, and it also have higher average robustness sensitivity compared to N1. And we can also see that the related convolution networks N3 is less robust and more sensitive to the attack than the transpose convolution network N1. And this slide shows a very interesting and surprising results on the accuracy and the robustness of M2NIST networks. So we remind that the related convolution networks N6 have 24 layers, which is larger than the transpose convolution networks N5 that have only 22 layers. However, in terms of accuracy, the smaller networks N5 is more accurate than the larger one, N6. And in addition, the smaller network is also more robust and less sensitive to the attack than the larger network N6. And interestingly, a more accurate network is not necessarily more robust. So we can see this when we compare the network N5 and N4. So N5 is more accurate than N4. It's much more accurate than 4 because its IOU is 0.65 compared with 0.60. The IOUs for N5 is 0.75 compared with 0.62 of N4. However, surprisingly, N4 is more robust and less sensitive to the attack than N5, as shown in the figure. And from the reachability time graph, we can see that in these networks, the reachability time of the ReLU layers do not dominate the total reachability time. Therefore, in this case, applying the relaxed reachability does not have much in reducing the total verification time. So this table shows the verification time improvement of the MNIST networks using relaxed reachability. And we can see that for N1 and N3 using convolution and average pooling for downsampling, we use relaxed reachability methods. We can see reduce significantly the total verification time and up to 99% when the input size is large. However, this is not the case for the mass pooling network. And two, the reason is that the relaxed reachability introduce more predicate variables. And when it's come to the mass pooling layers, it takes more time to find the mass bond candidates for the local regions and cause the increase in the reachability time for this layer. And to overcome this, we need to have the relaxed reachability methods for mass pooling layer in the future. So in conclusion, we have proposed a relaxed reachability approach for three metrics to analyze the robustness of a semantic segmentation network. And we have learned that to train a robust and verification-friendly semantic segmentation network, the user should use a convolution and average pooling for downsampling and transport convolution for upsampling. And lastly, the user should minimize the number of ReLU layers when they train the network. And our experience showed that the relaxed reachability is extremely useful when the reachability time of the ReLU layers dominates the total verification time. And the area-based relaxation strategy is the best compared with the other. And in the future, we will investigate the relaxed reachability for mass pooling layer and unmass pooling layer. And that concludes my talk today. And I'm happy to answer any questions. Thank you.
Thank you. So is there any questions? Okay, then thank you, Dr. Chen. And I'm also pretty agree with you that the max pooling layer will hurt the verified accuracy. And usually it is not necessary. It is not a necessary component in the neural network and can be replaced by with unweighted pooling. We also found that during our experiments.
Yeah, so actually this research is, the idea of this research come from the WRS autonomy project. And then they have a very large semantic segmentation network to detect the pi for the water vehicle, right? And then they have like unmasked pooling layer and masked pooling layer. And then when we try to verify that, we realize that we should not have that type of like neural networks because it's gonna hurt verification a lot. Yes. You can see that, you know, the masked pooling layer is always the hard one. Yeah.
Exactly. Okay, thank you.
Thank you.
And next presentation is from Heidi. And Heidi is a second-year PhD student at MIT, advised by Alexander Mandry. And he's broadly interested in deep learning, and his goal is to make it safe, robust, and reliable. Before MIT, Heidi spent 2 years at Microsoft Research as an AI resident, then as a research engineer, where he worked on various aspects of adversarial robustness. And Heidi holds a master's in robotics from Carnegie Mellon and a Bachelor of Science in Mathematics and a Bachelor of Engineering in Mechanical Engineering from the American University of Beirut. Okay, let's welcome Heidi.
Thank you very much for the introduction. And thank you for organizing this great workshop and for inviting me to this workshop. Okay, let me share my screen, my slides. All right, so today we're going to talk about certified defenses, and specifically certified defenses for adversarial patches. And this is a recent work for in our group, and it's in collaboration with Sashi Zhang, Eric Wang, and Alexander Madri from our group at MIT. Okay, so as he introduced me, I'm Hadi Salman from a PhD student at MIT. All right, let's start. So let's start with the fact that we all know about, which is that our machine learning models are brittle, in the sense that even small imperceptible perturbations, these inputs, can drastically change the output of these models, and we all know this phenomenon as adversarial examples. Okay, a very important thing to discuss or to be aware of when we discuss about adversarial examples is these set of perturbations that we allow our adversaries to perturb within. Which usually have or a popular choice for such set is those LP normed balls. For example, people try to synthesize adversarial examples that adversarial perturbations that are norm bounded within some L2 or infinity ball, and build also defenses against such attacks. But the thing with these LP normed balls is that although they give us some proxy of how robust our models are, they are far away from like what we would expect to happen in the real world. So a more interesting or a more realistic type of attacks are patch attacks. Okay, where an adversary, as we all know, can perturb a specific region, contiguous region of an image in order to flip the predictions of a classifier on that image. And the nice thing about patch attacks is that they can manifest in many different forms in the real world, such as 3D adversarial objects, or even adversarial eyeglasses, or adversarial t-shirts and shirts. And what this demonstrates is that all of the adversarial patches are actually physically realizable and pose a real threat for on our machine learning models in the real world. So a main question here is, how can we defend against such attacks? Okay. So a common way or a popular way to defend against adversarial examples in general has been adversarial training, where we train on worst case examples by solving some minimax problem. Okay, so we are all familiar with this. And this has been shown to work really well in practice and has been also made relatively fast. But the problem with this approach is that we get no guarantees at all. So we have no idea if in the future there's some strong attack that we don't know about yet, if this attack will break our model or not. So we really do not get any guarantees that our models are robust. And to solve that, in the past few years, there has been a lot of work on certified defenses, which are methods that come or give us robustness guarantees. And these range from exact verification methods to relaxed certification methods, all the way to smoothing-based defenses, and many, many more. Okay. So in this talk, we're going to focus about this last class of defenses, which is smoothing-based defenses. And I'll talk more about this class soon in my talk. But before going there, let's just take a look on the state of certified defenses to get a sense of how well they perform in practice. Okay. So here's a table which reports the standard accuracy and the certified accuracies against adversarial patch attacks at various sizes, on various sizes of the patch attack. A standard non-robust resonant 50 would get around 76% standard accuracy and almost no or not at all certified accuracy because it wasn't trained actually to be certifiably robust. Okay, now if we look at a recent method, which is basically de-randomized smoothing by Levine and Faizi, we notice that we can actually get non-trivial accuracies on ImageNet, certified accuracies against patch attack on ImageNet. But the thing is that we get this significant drop in standard accuracy, which is a common thing that we usually get actually with any defense that we build for adversarial examples. So the question here is this trade-off really just a reality that we need to just accept and live with, or can we do more? So every time we build a certified defense, whether it was against adversarial examples, adversarial patchers, or something or something else, do we just have to accept this reality that this we will build this defense, we have to accept that we will get drop in standard accuracy? And this is the main focus of our talk, to answer whether this question is correct or not. And to do that, we redirect our focus from presenting a new certification method or certified defense to rethinking the architectures that we actually use in our defenses. And the main finding of our work is that VITs are better for patch defenses. Okay, and I'll walk you through how we reached this conclusion. Okay, there are many different certified defenses, and in our talk and this talk, I'm just going to focus on this de-randomized smoothing method, which I'm going to introduce very soon, and demonstrate how VITs can actually perform much better on such method. Okay. All right, so let's take a quick look about on de-randomized smoothing and how it works. So de-randomized smoothing is a defense that basically aggregates the predictions over many different ablated versions of an input. So basically, we have an input, we replicate this input and mask most of it, except for a small part of this input. In this case, a small column in this image, but it can be really any small shape. And we get predictions for each of these ablated images, and then we basically take the majority vote of these predictions to get the prediction of this defense. Okay, and the hope here is that by aggregating these predictions over many different ablated versions of the input, that any potential adversary won't be able to affect all of these inputs at the same time. So in case there's an adversary, he or she might be able to just affect or attack some of these variations or ablations of the image, and therefore won't be able to affect the total majority vote, and therefore won't be able to affect our predictions. Okay, so to make this more concrete, let's look at the full pipeline of de-randomized smoothing. So it looks something like this. So we have an input image, and we basically generate a number of ablations for this image. Then we pass them through some classifier, okay? And we record the classes for each of them, okay? Sorry, we record basically the occurrence of each class, the number of occurrences of each class. And we basically return the class that occurs the most, okay? Okay, I'm not sure, sorry, hold on just one second. Okay, so we return the class that occurs the most, and by looking at the top occurring class and the second top occurring class, we can actually certify the robustness of this model at this image. So if this gap between the top occurring class and the second top occurring class is greater than some margin, we can actually show that the model is robust. Okay. If we look closely at this pipeline, something really crucial or a key part of this de-randomized smoothing pipeline is the fact that this classifier has to work well under image ablations or under substantial masks of the image. So imagine this base classifier does not work well or does not classify these image ablations very well. We really won't be able to get the majority vote to be the correct class, because basically most of the predictions would be wrong, or if not all the predictions would be wrong, because the classifier is bad at classifying those image ablations. And even if the majority vote is correct, this gap between the top occurring class and the second top occurring class might not be large enough to actually certify anything at all. Okay, so essentially to improve the performance of such a pipeline or such a certification method, it all boils down to improving the performance of this classifier on these masked images or ablations. So now, that's what we will focus on right now. Okay, so how can we actually get good performance on ablated images? And it really all boils down to what models we are using. It's really all determined by the actual model that we are using, or the actual classifier that we are using, right? And the go-to architecture or model for computer vision applications and for many of the certified defenses currently are these, convolutional neural networks, which we all know about, okay? Which use some convolutional layers to process images across many layers. Sounds good. But the problem or the thing with convolutional neural networks is that they cannot share information globally. They just share information locally because they're using those convolutional filters, and therefore intuitively speaking, they won't be able to focus on important regions in the image and just ignore unimportant regions. And in the context of our problem, it might actually be very difficult for CNNs to just ignore the masked regions and just focus on unmasked or unablated regions. And this raises the questions of whether these architectures are actually suitable or the right architecture for our task, which is predicting under image ablations. And to answer this question, we consider an alternative architecture to CNNs. Basically, we consider the well-known vision transformers, which have shown a lot of advantages over CNNs in the recent years. And in fact, it turns out that vision transformers are better suited than CNNs on predicting image ablations, as we will show very, very soon. And the reason for that is the way vision transformers work by basically tokenizing generating a set of tokens for each image and passing these tokens through a set or a series of self-attention modules, and these modules or self-attention modules naturally support sharing information globally, which allows the VIT to focus on important regions in the image and just ignore unimportant regions. And in the context of our problem, this allows the VIT to just focus on unmasked images and just focus on unmasked images and just totally ignore the masked or ablated parts of the image. Okay? So this is the intuition behind this, but does this work in practice? And to answer this question, we conducted this simple experiment. We basically evaluated the performance of a number or several VIT architectures on ablated versions of ImageNet. So we bring ImageNet, we just ablate most of it, or for each image we ablate most of it randomly, and then we evaluated these images using 3 different VITs, and we compared the performance to comparable sized CNNs, namely 3 different resonets. Okay, and indeed it turns out that the transformer is much better at classifying ablated images or image ablations compared to CNNs. Okay, so this is great. So, and our intuition is verified in practice. VITs are better at solving the task of classifying image ablations. And what this suggests is that now if we actually plug our VIT in this de-randomized smoothing pipeline, we should get better certification, because now the VITs are much better at detecting or at classifying these image ablations. So is that really the case? Do we actually get certification improvements? And the answer turns out to be yes. By simply plugging a VIT into this pipeline, we can actually boost the certified accuracies on ImageNet by a lot, by a substantial margin. And not only that, we can even get standard accuracies that are much higher than before, and that are comparable to standard non-robust models, such as a standard ResNet 50, for example. So this is really nice. Like, we just simply swap 2 architectures, and now we get much better certification performance and much higher standard accuracy. But this is not the full story. In fact, if we use VITs, we can unlock additional benefits. Specifically, the nature a VIT works, the nature of VITs allows us to simply drop masked tokens, because VITs basically tokenize an image or generate converts the image into a set of tokens and passes these tokens into a series of self-attention modules. So we can simply just not pass the fully masked tokens. We can just simply drop these tokens. And the reason why one would do that is that by doing this, or by dropping masked tokens, we can speed up the inference of these VITs by a lot on masked images. And this is really important for certification, because certification basically requires us to do inference many, many times over ablated versions of the input. Okay, so by speeding the inference of a VIT on ablated images, we essentially will speed the certification using the randomized smoothing. Okay, to get a sense of how much speed up we get, for example, a VIT base, which is comparable in size to a wide ResNet 101, is 20 times faster on masked images or ablated images. So in practice, usually VITs and CNNs run about maybe the same speed because they both operate on the full image. But now, because in our use case, most of the image is ablated, we can simply drop that. So VITs can actually benefit from that, to just ignore the masked part of the image and focus on the unmasked part, and this speeds up inference time. and thus speeds up also certification by a lot by if we just place this, masked token dropping in this pipeline. So by simply, masking the tokens and then dropping the masking the image and then dropping the masked tokens, we are able to speed up certification by a lot. Specifically, a previous, the original de-randomized smoothing gets around, processes around 1,000 images in like 150 seconds. We are able to drop that by, drop it to like 58 seconds only, and by further optimizations as well, we can drop it to like 3 seconds for 1,000 images, which is really great. Like it's really very, very close to what a standard ResNet 50 would achieve. It's still a little bit slower, but it's much better than before. So this is really nice. By just using VITs instead of CNNs, we are actually able to achieve not only substantial improvements in certified accuracies, but also standard accuracies and speeds comparable to standard non-robust ResNet 50s, for example. And the reason this is really, really interesting is that this is probably the first time we might be able to like not severely suffer from a robustness trade-off or a robustness penalty. So there seems to be a hope that we can still, build some certified defenses for adversarial patches and get models that are really a viable alternative to our standard models that we use in the real world. So there's still hope. So this wraps up what I wanted to go over in this talk. And the takeaways are that VITs turns out to be really great at classifying masked images. And this works really well with de-randomized smoothing because the de-randomized smoothing hinges on the ability of a classifier to classify ablated images. And by basically using VITs in de-randomized smoothing, and modifying a little bit the architecture of the VIT to be able to drop tokens, we get those smooth VITs, which achieve much better certification performance than before, along with competitive clean accuracies and orders of magnitude faster than previous certification using de-randomized smoothing. Here's a link to our paper, our code, and our blog post. And thank you very much for attending the talk. I'm very happy to answer any questions. Thanks.
Thank you, Heidi. So any questions from audience? Okay, if not, I have a quick question. So does your method is sensitive to the size of the objects of input? Because if the size of the input the size of the object is small, then it looks like because the method depends on the margin between the top one label, top one class and the top two class during the majority voting, right? So if the object is so small, maybe there are many prediction will vote to some noisy data maybe.
So so de-randomized smoothing is not our method. It's Levin's and Faizi, just like to clarify. But no, actually it doesn't. I mean, it might. It actually works on small size images. So here I just like showed ImageNet results. But we have in the paper, CFAR10 results. So it actually works as well. It works as fine for CFAR10, and previous works have actually shown to make it work on Amnist and CFAR10 actually.
Yes.
So it works. But you're right. Like if we have like if we have images that the signal or the information is only captured in one small region, then yes, you're right. Exactly. Such methods would fail. For example, imagine you have a self-driving scenario where there's a small stop sign that we have to detect. Really, this will probably appear in only one of the ablations. So this makes I think this method will fail in such scenarios. Yeah.
Okay. Thank you.
Any more questions?
Okay. So if there's no question, we'll move to the next talk.
Sounds good. If you have any more questions later on, just reach out. I'm more than happy to discuss them.
Thank you.
And thanks for inviting me. Thanks.
Okay, so let me introduce Wenbo Guo. So Mo Guo is a PhD candidate of the College of IST at Penn State. He obtained his master's degree from Shanghai Jiao Tong University in 2017. His research focuses on deep learning and computer security. His work includes improving the robustness, transparency, and safety of deep learning systems, and developing novel deep learning models for security applications. He's a recipient of the IBM PhD Fellowship, Facebook Baidu PhD Fellowship finalist, and the ACM CCS Outstanding Paper Award. He also won the 2018 CAAD Winning Award at DFCON USA. Okay, welcome Wenbo Guo.
Yeah, thanks, Kaidi, for the introduction. Yeah, let me share my screen here. Okay. Okay, so I'm able to see my screen, the slide.
Yes, looks good.
Okay, yeah. Okay, so I'm very happy to be here to discuss, introduce our recent work about explaining and remediating deep reinforcement policies. So this talk is based on our NeurIPS work. The title is here. Shout out to my collaborators. Okay, so over the past few years, we have witnessed great success of deep learning in many fields, such as CV, NLP, and also in computer security. Recently, researchers proposed deep reinforcement learning, which utilize deep neural network as a policy in reinforcement learning. This new technology has shown extraordinary performance on many decision-making tasks. But agent trained with DRL also dominated different type of games, ranging from simulation game to real-world games. I think one of the most famous example would be a Go game where DRL policy is a world-class professional Go players. But behind the above success is a harsh reality that DRL is still not explainable. Specifically, as we can see, at each time step, a DRL agent or DRL agent's policy take as input the current observation and output the corresponding action. Because of the black box nature of neural networks, we are not able to read why the agent makes the current action. Going beyond individual actions, individual steps, the agent usually takes a sequence of action based on its policy and collect a certain amount of reward. Still, it's kind of hard for us to reason the correlation between these time steps, and we can either reason like why does the current policy take the current action to win or lose the corresponding game. Existing DRL technique, explanation technique, usually focus on answering the first question, that is explaining individual actions. As demonstrated in the figure here, usually this method explains the current action by highlighting the important subregion within the current observation that leading to the corresponding action. Although drawing some useful insight into how the agent make individual moves, this method cannot explain the overall policy learned by the agent. So in this work, we propose a novel explanation method that try to answer the second problem. That is, we want to provide insight into the policy learned by the agent. So specifically, given a trajectory of our target agent, we want to highlight the time steps that contribute most to the agents or to the trajectory's current result. In the rest of this talk, I will first summarize existing interpretation technique for DRL policies, and then I will introduce our proposed method, followed by the evaluation and application. Finally, I will conclude this talk. As mentioned above, existing DRL explanation technique usually focus or mainly focus on pinpoint important features within the current observation. This actually equivalent to simply explain to explaining a deep neural network. So this work utilize the following existing deep learning explanation method to draw insights into a DRL policy. Different from this works, in our paper, we propose a method to pinpoint the most important time steps within the game trajectory. Here, we assume the access only to the target policy network and the corresponding environment. At a high level, our method first collects the trajectory and the corresponding reward of a target agent. Here, each trajectory, as shown here, is represented by a sequential data point, where each element, the xt, is a state action of the target agent at the time step t. And the response of the current of this sample x is just the reward of the corresponding trajectory. Using this data set, we could fit a self-explainable model and then draw the important time step from this self-explainable model. We design our self-explainable model with the form simply say g of f of x. So here f is the feature extractor which takes as input the original trajectory and output a hidden representation of the trajectory with the same length, but with only like one dimension at each time step. We design our feature extractor as a deep additive Gaussian process model because this model could capture the correlations between and within the game trajectories. After obtaining the hidden representation, the fx, we then input it into our predictor and gets the final predicted reward of the corresponding trajectory. We use the Bayesian regression model as a predictor because it enables posterior inference, but more importantly, also enables the identification of important time steps within the input trajectory. Although this formula here represent our proposed explanation model. To enable efficient learning and inference, we play around the inducing point trick and design a customized learning method based on variational learning. More technical details of the model and the learning process can be found in our paper. In this slide, I will demonstrate the workflow of our proposed explanation system edge. Given a trajectory, edge first input it into a recurrent night encoder and gets a sequence of embedding where each element is the embedding of each time step in the input trajectory. And then we edge input the embedding of the last time step into a shadow MLP encoder and gets the episode embedding, the embedding of the whole episode. After concatenating the time step embedding and episode embedding, edge then input it into an active Gaussian process model and gets the hidden representation of the whole trajectory we mentioned above. Finally, it inputs the hidden representation of the trajectory into our final prediction model and gets a predicted reward. So here, the time step importance can be inferred or extracted from the mixing weight of our prediction model. We evaluate our method on 3 selected games, one from Atari game and 2 others from musical games, and compare it with 4 baselines. 2 of the baselines, they follow the methodology of approximating or fitting the trajectory with a vanilla neural network, and then apply a post-training explanation to draw the important time steps. The other 2 baselines are basically well-known or existing self-explainable model. And we compare our method with these 4 baselines from 4 different perspectives. Due to time limit in this talk, I will only focus on the explanation fidelity. To evaluate the fidelity of the explanation drawn by different methods, we follow idea to do the evaluation. Basically, we just replay the game episode. But when we replay when during the replaying, we replace the action at important time step with some random actions. Our intuition is that if the identified steps are truly important ones, modify the action at these steps will trigger a large change on the final reward. So following this idea, we then design our evaluation metric and conduct the fidelity evaluation. The results are shown in this figure. A lower metric value indicating a higher explanation fidelity. As we can see from this figure, our method, the purple bar, the edge, should obtain the highest fidelity on all of these 3 selected games, which verify the fidelity of our method. After verifying the explanation fidelity, we then further explore how to utilize the explanation to do different things. As the first explanation, as the first application, we explore how to launch adversarial attacks based on our explanation result. Our intuition is that In the winning trajectories, usually agent wins because it makes some correct moves on several important time steps. So if we modify or change the action in this at this important time steps, probably we could mislead the agent to instead losing the game. Following this intuition, we design our action manipulation attack method. More specifically, we first utilize each explanation method to explain a set of winning trajectory of the target agent, and then identify the top 30 commonly most important time steps across all the trajectory. And then we launch our attack at those identified steps by replacing the original agent given by its policy with some like a random action, randomly chosen from the whole action space. In this table, we show the attack result built on each different explanation method. As we can see from this table, all the explanation method was able to generate an attack that reduce the winning rate of the target agent. But we can also see that our explanation, the attack generated from our explanation, shows the strongest exploitability. With the success of the attack, we think this application reversely, and we then hypothesize that if we replace the wrong move made by the agent in the losing games, probably we could reclaim the winning of those games. And guided by this hypothesis, we design a policy remediation method. Specifically, we first identify the top 5 steps from the losing trajectory that cause the failure of our target agent. Then to patch these failures, we construct a remediation policy in the form of a lookup table. More specifically, to construct this lookup table, we simply replace the action at those important time steps with some random actions, because we do not have like a oracle or ground truth. If you have like oracle, you can replace the actions given by the oracle. And then we record the state action that actually lead the game, lead the agent to winning the game instead of originally like lose the game. By doing this way, we could collect a lookup table with a set of states at action pair. When playing the agent in the corresponding environment, if the current states match those states in the lookup table, we can take action given by table. Otherwise, we take action based on the original policy of the agent. The result here shows the improvement in the winning rate by like patching the policy error following our proposed method. As we can see from this table, basically our method edge, since edge can give the can achieve the highest explanation fidelity, it also enable the highest improvement in the agent's winning rate. Finally, we use our method to explain a victim policy and explore how to robustify this victim policy based on the explanation. Given a target victim policy, we first fix it and train an adversarial policy against this victim using the PPO algorithm. We then use our method edge to explain the trajectory of the victim policy playing against its corresponding adversary. The figure on the left-hand side shows an explanation of the winning trajectory of the victim agent. And the figure on the right-hand side shows the explanation of the losing trajectory. As we can first observe from both trajectories, we can see that the adversarial agent, the green one, in both trajectories, they establish a weird behavior that is falling into the ground. But in the winning and losing trajectory, the victim have different reaction to the adversary's weird behavior. Specifically, in the winning trajectory, the victim agent, the red agent, was able to ignore the weird behavior of adversary and directly running towards the finish line. However, in the losing trajectory, probably the victim agent was tricked by the adversary policy, adversarial actions, and just directly fall into the ground and thus lose the game. As we can also show from the explanation bars here, edge draw different explanation from these two trajectories. In the losing trajectory, as we can see here, edge assign a very important or high weights of the time steps that's pre-training to the weird behavior of the adversarial agent. However, in the winning trajectory, I just assign a very low weight to the correspond to this time steps. This difference in the explanation actually indicates that in the winning trajectory, the victim just simply ignore the weird behavior of adversarial agent. So guided by this finding, we propose a defense that simply blind the victim observation on the adversarial. So basically, we just force the victim to do not focus or do not look at the behavior of adversarial, just running in the environment. And as we can see from the result here, this defense strategy actually works, and our explanation edge could enable the highest winning rate improvement of our target victim agent. To conclude this work, first, the deep reinforcement learning suffers the lack of transparency issue at two different levels. And we show that a DRL policy can be explained by modeling its trajectory with a self-explainable model. Finally, we also demonstrate that explanation of DRL could be utilized to launching adversarial attack, patching policy errors, and defending against the adversarial attack. Thank you very much for your attention. We also publish our code. It can be found in this repository.
Okay, thank you, Wan-Yi.
Yeah.
Is there any questions? So because I am not the expert in the explainable AI, so maybe I have a simple question. So how to evaluate the explainability of a neural network, especially within the quantitative results? Because that's kind of abstract, right?
Yeah, that's a good question. So in our I think at high level, regardless of explainable deep neural network or DRL, basically the key idea of evaluating the explanation result is, say you have input, you identify some important feature within that input. We want to know whether these important features are truly important ones, or say the non-important ones that identified by your algorithm. The way to do this is just delete those features or replace those features with some random values. And then we observe the changes in the prediction result. If the prediction result change a lot, we will say, okay, these features are important. Otherwise, we will say, okay, these are not important features. Yeah, that's the basic idea.
Thank you.
Yeah, no problem. Yeah, thanks.
Okay, and finally, we will go to our last round. This is the afternoon panel discussion. And I will first introduce the 6 speakers we invited. And Stanley is an assistant professor in computer science at Stony Brook University, investigating the verification, autonomy, cyber-physical systems, and neural networks. He strives to develop practical formal methods that are both scalable and useful, which demands developing new theory, programming efficient tools, and building experimental systems. And Yizheng Chen is a postdoctoral scholar at UC Berkeley. Her work focuses on robust machine learning algorithms for security applications. Previously, she was a postdoc at Columbia University. She received her PhD in computer science from Georgia Institute of Technology. She is also the recipient of the Anita Borg Memorial Scholarship. Nicholas Carlini is a research scientist at Google Brain, working at the intersection of machine learning and computer security. His most recent line of work studies properties of neural networks from an adversarial perspective. And Changliu is an assistant professor in the Robotics Institute School of Computer Science at CMU, where she leads the Intelligent Control Lab. Her research interests lie in the design and verification on intelligent systems with applications to transportation and manufacturing. She published the book, Designing Robot Behavior in Human-Robot Interactions with CRC Prize in 2019. And she is the recipient of the 2019 Eminent Research Award. And David Wagner is professor of computer science at UC Berkeley. He's known for discovering security vulnerabilities in neural networks. 800.11 wireless networks, electronic voting systems, and other widely deployed systems. He currently studies the security of machine learning. And Eric Wong is the postdoctoral researcher in the Computer Science and Artificial Intelligence Laboratory at MIT. His work focuses on the foundations of robust systems, building an elements of machine learning and optimization to diagnose, understand, and develop reliable systems of real-world settings. He is a 2020 CBL scholar and received an honorable mention for his thesis on the robustness of deep neural networks to adversarial examples at CMU. Okay, and I will also appreciate Yizheng Chen that she will help moderate this panel discussion. And I will turn over to Yizheng, and thank you.
So I'm gonna go over some questions that the organizers thought that would be interesting to discuss. The first one is the following. The definition of safety, reliability, and robustness can be quite different in each field. Many existing works focus on simple mathematical models, such as LP norm perturbations. However, the specifications for safety and robustness used in practice can be much more complicated. So what do you think is the specification that is most important for the domain you're familiar with? For example, in robotics, cyber physical systems, computer security, etc. Would someone like to comment on the robotics first?
Yeah, maybe I can comment on the robotics. So I mainly work on human-robot interactions and robot safety. And in this domain, I think the most important property is the input-output stability and also input-output safety, especially when a robot needs to work with human. So given one example about those kind of properties, suppose there's a human in the environment, then the output of the robot should not get closer to the robot if the robot is already very close, in close contact with the human. Yeah, and this can be mathematically written as a input-output constraint on the robot control policies. And the limitation of current specification is that a lot of verification approach requires those constraints to be kind of linear constraints, kind of polyhedral constraints. Yeah, but in reality, we need to relax that assumption to tolerate more non-convex constraints. Cool, that's the robotics perspective.
I can comment a little bit too. How's the sound quality, by the way? Can you guys hear me? Okay, great. So so I work in cyber physical systems a lot, and so the types of models we consider you'll have differential equations describing how the physical system is changing over time, and then if you have maybe something learned with reinforcement learning or some neural network controller that's interacting with the physical system, you could imagine the properties you would want to prove would be that maybe let's say overall time the system stays safe. And so this wouldn't be an input-output property of the neural network. It would be something that combines multiple executions of the neural network and maybe some of the differential equations themselves. So including differential equations and multiple executions of a controller would be a useful property to have, but that's of course much more difficult than an LP norm property or something like that.
Thank you. I think that's very interesting. So can you characterize multiple execution of the neural networks as like some temporal property?
You could think of it. So you could imagine specifications like that. I'm thinking even simpler, just like a safety specification is enough. So I think like most of us know like the ACAS XU benchmarks, and those properties are like open loop properties. But the property you care about is you avoid collisions in the closed loop. That's what I'm thinking of. So then you could have some safety distance with two aircraft and say from any initial starting position, the aircraft will stay 500 feet away. So then you have maybe some physical model, you have a
maybe Dubin's aircraft model describing how the system changes under each of the output commands. And then maybe you have some period of execution, right? That's probably the easiest way to think of every second. Let's say the neural networks execute and you follow the command. Or maybe you could think of, if you want to get closer to reality, like you'll have you won't have exact timing information. You'll execute sometime within the next second. So you have some maybe maximum. You have some frequency execute at, right? So like real-time systems typically have like a worst case execution time, and you have periodicity, right? Those are simple real-time schedulers are like that. And so if you're not, it depends how the sampling is done, but the easiest way to implement it, you would just, sample at some point within the frequency. But then, checking all the possibilities is kind of much trickier. So, but, even simpler than that, just have discrete time when you have safety properties like that. And the temporal specification is just always you avoid an unsafe state.
Well, I think the temporal properties can be generalized to other applications as well. Like robots are moving over time. There are videos of robots moving, and then if you think about videos, these are just frames of different images over time. Perhaps in security, you would have incoming stream of data over time as well, when you are doing some sort of detection tasks. So what do other people think about these?
I'll let other people speak.
Yeah, since you mentioned security, I think trying to answer this, like exactly what setting you care about for security, I think is a good question. I think obviously if you can do LP attacks, then you can do lots of other attacks that are strictly more permissive. But in security, often all you care about is getting the machine to make some error. You don't necessarily need it to be an imperceptibly modified error. So let's think maybe the easiest example that people have been talking about for maybe the longest is malware detection, right? If you want to detect if a program is malicious or benign, I don't need to construct a program that is epsilon different from some other program but is classified as benign. I can come up with any new program I want in the world, and as long as it has the malicious behavior and it evades detection, then I'm happy. And this is a much harder problem. Now, from the attack perspective, if I can do an LP malware sample, then obviously I can do the unconstrained problem. But what I truly care about at the end of the day in security lots of the time is an unconstrained. The adversary can do almost anything. They just need to find some error. But solving this is really, really hard. And I guess it's part of the reason why we've been considering LP attacks for a while. But at some point we're going to need to start figuring out a way to address the more general problem.
I can add a little on the security side. Whenever you have any kind of a intrusion detection system or detecting security breaches, there's always the question in the security world of evasion. Can attackers modify their behavior so they won't be detected, and how easy or hard is that? So I don't know exactly what the right property is, but possibly one way to think about that is cost. It's often possible, given enough effort, to evade detection, but how much would that cost an attacker, or how much effort would it take? And so one theory is you don't have to have the perfect system. You don't have to outrun the bear. You just have to outrun other people. You just have to make it so that it's less attractive for them to attack you than to attack others in the world. So possibly a property that's ill-formulated and I don't know how to formalize has to do with what the cost or the effort required to evade the machine learning model is.
So then is LP norm, even for images, is LP norm good enough? Like, is there any other specifications? Eric, what do you think?
Yeah, so I guess like from a more general like machine learning perspective, Really, when you think about what is most important, it's not necessarily one specific specification that is most important, but rather they perhaps like a class of specifications that is important. And I think what is probably most important going forward is sort of being able to have a flexible way of doing the specification. So having a specification that is flexible that allows you to adapt it to whatever it is that you need to do, rather than focusing solely on a single particular type of specification. So like, for example, you can look at the LP norm as, in some sense, it is capturing anything that exists within the LP norm, right? And it is one such class of specification, but it's, of course, it doesn't contain everything for images. And I'm sure if you ask most, people attacking these vision systems, the LP norm is generally not something that people use to break, real world machine learning systems, right? And then so sort of what I would say, from my opinion, is the most important thing is having a more flexible class of a more flexible class of threat models or ways to specify what is the thing that we want to actually defend against.
Yeah, so I'm looking at the next question. It says that for different applications, the perturbations for features may be dependent on different dimensions and even maybe dependent on the data, which can be an obstacle when applying robust machine learning techniques. Is there a way to help practitioners find an appropriate threat model for their data? So threat models in real applications can be very complicated. I guess if it says if you care about a different class of specification, how do you find the specification?
So I guess I can comment briefly about this because I guess this is sort of related to some work that I had done in the last year, which was that sort of if you want to sort of characterize what it is you need to be robust to, there's, I guess, sort of maybe two kind of ways you can go about doing this. The first is you try to, you take out your pen and paper and you try to like write down mathematically, what is it exactly that I'm trying to be robust to? And this can work for some things, right? But, as like maybe the question kind of suggested, not everything can be sort of written down in a set of mathematical equations. But if you can, then that's sort of maybe the best thing that you can do. Now, sort of a different way in which you can do this is, if for example, the threat model maybe depends on the data itself, right? Then what you could do is some work that we had done before, which is to learn what the threat model is. So it's to have a model which represents the threat model that you're trying to be robust against. Now, and then we call this like a learned perturbation set or a learned threat model. Of course, this induces another machine learning model, right? Which then requires that we have to make sure we are really careful about what does this set contain and what does this set not contain, and what exactly is it that we can guarantee with this set, because it is a learned model, but it does give you a lot more expressivity in what you can capture and a lot of flexibility, because in that sense you can learn a model from data which is not really constrained by necessarily a mathematical set of equations.
I think this is very related to another question that the organizers had written down for us. And I think that maybe give us some more concrete discussion about how to generate specifications. So this question says, neural networks are often used in applications where the desired operation is vague. In these domains, it is difficult to formally state if the intermediate output of the network is correct or not. For example, specs like all images with cars should be classified correctly, or the current autonomous car command is fast and safe. all of these sound great in English, but translate poorly to mathematics. So instead of handwritten formal specifications, can we consider specifications that are also vague, created by machine learning methods? And I do have some comments about this, that I'm wondering whether it's possible to have templates of specifications and learn how to fill up those holes in the template. Or, so I've read that when people do formal verification of code, there's a Using Security 2008 paper that they automatically infer specification from code. So their assumption is that developers write checks of things like access control or rate outbound checks, where most of those checks are written correctly. So they can try to figure out from the data where what is the most reasonable specification that people usually want to do. So that's the natural behavior without attacks. And once they figure out the specification, they try to use that to check the rest of the code where the specification is not written. I don't know if this kind of template or learning from data can generalize to other kinds of applications, like images or robots or other security applications or cyber physical systems. So what do you guys think?
Maybe I can comment a little bit on the robot side. I think the template idea is great. So for example, if we want to learn the safety specifications for the robot to safely operate or collaborate with a human, in a lot of cases, we are not sure about what is the safety threshold for the human, then we can probably learn those safety thresholds by generating some template operations for the robots. So then the robot can gather information. I think that's a very clever way when we have relatively low dimensional space, but it seems like images are too high dimensional, and we lack some fundamental understanding about the underlying structure of images. So I feel like it's more challenging for those high dimensional spaces than those low dimensional spaces where we know how to describe. Yeah, so that's my view.
And adding on to that, in the limit, this becomes a problem of attacking the specification, right? Where you can verify that your program satisfies some property, and from the security side, you're going to just say, okay, that's great, you have the specification, I'm just going to do something different. Which, I mean, consider, let's say, crypto, right? When systems that use crypto fail, it's almost never the case that the crypto fails. AES is essentially perfect. There was a time when AES block ciphers were bad, but we figured that out. Now when systems that use crypto fail, it fails at the boundary between the crypto and the system. And asking for a specification, I feel is asking for us to come up with a way to put a boundary between the machine learning and the system that uses the machine learning. And currently, I think, we have all kinds of problems with making it satisfy specification in the first place. But even if we could do that, it seems likely to me that it will still have all kinds of security challenges, because you will say something like, all scenes that have cars in them have this property. But now the question is there a car there? What does exactly it mean for the car to be there? Do you have to use a machine learning model to detect if a car is there? Now can I attack that machine learning model to say, nope, no cars here, so the spec doesn't have to hold true? I think it's definitely an important problem, but it just seems like this is the next area where things are going to go wrong once you actually want to deploy these in practice.
I think there's a fascinating challenge with using learned models as your objective or your property, your goal. So let's say that I want to train a robot to do cartwheels. It's probably pretty hard to write down a loss function or objective function by hand that characterizes how good a cartwheel, how good a action that was, how cartwheel-like it was. So you could imagine a really natural thing to do is to train a model to recognize, did that sequence of actions look like a cartwheel? And then ask humans to rate different sequences and learn a model. And then when you have the model, use that as your loss function and train a network to learn to cause actions that the cartwheel detector thinks was a good cartwheel. And if you're lucky, maybe that works, but I think there's a risk there, which is that when you train the model, the optimizer might, instead of learning how to do a cartwheel, might learn how to take an action that is an adversarial example for the cartwheel detector model. To take an action that fools the cartwheel detector, that the cartwheel detector thinks is a cartwheel, but no human would say is a cartwheel. And I think that could quite easily happen by driving that action sequence into some portion of the space that your human labelers haven't looked at. Because your human labelers haven't looked at, there's no training data for your cartwheel detector, and what the cartwheel detector does is arbitrary. And in that region of the space, it might just by chance happen to say, that's an awesome cartwheel, dude, I love it. And so then your optimizer might cause your robot to learn to do those crazy things that aren't actually cartwheels, but your model thought were. And so I think it's a great challenge for the field to figure out how to solve that problem, like maybe how to come up with optimization algorithms that are strong enough to train the model, but not so strong that they construct adversarial examples for your cartwheel detector.
Yeah, these all sort of like hammer on sort of what I had kind of alluded to before, which is that you have to be, if you try to do something with a learned specification, you really have to be clear what it is you're trying to be robust to and how you actually evaluate whether the model, actually contains the things you want to be robust to. And then you're right, it could also very well contain many things that you didn't intend, and then an adversary could potentially take advantage of these things. But yeah, this is like sort of maybe an inherent kind of trade-off that we have to do in order to have something more expressive than what we can write down right now with LP type models.
I'm glad you're bringing that up, because I think one of the fascinating things here is usually we think of adversarial examples as a problem when there's an adversary. But this could pose, if you're using a learned model, this could pose a problem even if there's no adversary in sight, because the way we train neural networks is through optimization, and optimization is itself an adversary. So even if you don't care anything about security or attacks, this gives you a reason why you might care about the robustness of any learned models.
So I think there was a comment also that Yizheng said about how they do like automatic generation of specifications for software. So I've seen techniques that use like invariant generation based on observed data, like preconditions and postconditions of functions. So if you have a Python function and the first variable is always a certain type, you add this as sort of an assertion, right? Something like that. Or if the list always comes in sorted, you add this as a precondition that you can then check at runtime. And so I wonder if you do this at a low level to a neural network, if you'd get anything useful out of it too. Like, are there certain neurons that for all of our training data, the ReLU is always in the positive range or always in the negative range? And then could this be then a condition I add to try to check for this, data that comes in later that's not, not similar at all to the training data I have? Maybe it's not as simple as just looking at a single neuron and a single range. Maybe it's some combination of neurons that you can use to generate these sort of intermediate specifications that you could learn these from data, but a human would never come up with them because it doesn't really make any sense to a human.
People have tried to do exactly this. There are several defenses that do this, and it's possible it could work, but we've broken the ones that try so far.
I see.
So it's so here's the challenge, right? Once you have the model that is looking at the other models, you have the checker is looking at the original model and it's trying to learn what's good and bad. And you have exactly this problem that now you have, this model is learned. This model has adversarial examples. And so now what you do is you generate an input which fools the first one into giving the incorrect error, or in giving error, and then fools the second one by constructing an adversarial example against that other one, so that this property that, so it thinks that there's something that's true. It thinks that it's now looks all good, but it isn't. And so far, at least for the ones that I've seen, it doesn't significantly improve the robustness.
So I guess the hope is really that the checker somehow is more robust than the thing that's being checked, so that it's maybe harder to attack, right?
Yeah, so I haven't, for example, seen an adversarially trained verifier. This is a thing that I don't know why I haven't seen this, but maybe it exists and I just haven't stumbled upon it. But for the papers I've seen, most of them are trained using standard techniques or with some kinds of weak verification or weak adversarial training. I haven't seen like a really strong adversarially trained verifier. Maybe this would help. I guess this is a concrete thing someone could try and do. Yeah, no, I think this is an interesting framing of things. And typically in security, verification is the easier, right? Like, I mean, this is the standard thing that people always say is you don't write the thing to, let's say, parse some complicated structure. You just verify that it was parsed correctly and reject if not. You can imagine a similar kind of check here, but it seems because of the very high dimensions, and like a model has 1 million parameters, 1 million activations, you haven't like made the problem any simpler in your verifier. Your verifier is still looking at 1 million dimensional input and has to decide if things look good or not. So maybe it's not any simpler, but.
In the image classification case, I could imagine it's, it depends on the spec, right? You have this general thing that is image classification, and the spec is all cars get classified correctly. So then the checker just has to check, is it a car, is it not a car? Hopefully that's an easier problem than find the class of the image.
Yeah, definitely. This is, I mean, this is sort of the motivation behind like some of these analysis by synthesis kinds of approaches, which do, like, I'm not going to check if this is a 1, or if I'm going to check which digit this is, I'm going to say, if this was a 1, then it should look like this. And these approaches, at least for simple models, for simple classification tasks, can do quite reasonably. And hopefully we could extend it to complicated things. But yeah, so far it's been tricky, but I don't think it's hopeless.
So I'm more curious about the problem that Nick and David mentioned about, is there a car in the first place? So earlier today, David mentioned a problem with the arrows of detectors for self-driving cars. I don't know if that applies to robots as well. And some of you did not hear the question, so I'm also wondering what everybody thinks about that. So David, are you interested in discussing this question again?
I'd love to hear how other fields ensure safety. How do you verify or evaluate or demonstrate that a system has a very low error rate? 1 in 10 to the 10 or something like that. Is that achievable? Has anyone have any success, and how do you do it?
What was the question? Is that's how can you achieve like a high confidence in autonomous driving?
Well, for autonomous driving, if you want to be safer than humans, you probably need to have a crash that's rarer than 1 in 10 to the 8 crashes per hour driven. So if I now want to claim that my machine learning model is safer than a human, that probably means I need something like to prove an error rate of less than 1 in 10 to the 12, let's say. So how would I normally do that? I'd gain like sample 10 to the 12 images, real world images, and then prove that it's correct on all of them. And that sounds incredibly infeasible. So do any fields have any more efficient way to provide evidence or verify or test that their systems achieve a very low failure rate?
Maybe I can provide one example in robotics that we are using. So we heavily rely on human knowledge to model everything and to quantify the bounds on the available motions of all the participants in the system. For example, all the human motions have limits and all the robot motions have limits. So if the safety header is outside the physical limits, then we don't need to worry about that. And then we can characterize the distribution of the human behavior within the limits. So for a low probability area, if there's some safety hazards, since the probability is low, so that's okay. And we can focus on making sure the system is safe for the high probability area. But that heavily relies on our knowledge or our ability, human designers' ability to model everything. I feel for like a general image or more complicated machine learning problems, the challenge is that we cannot have a good model or mathematical description of the problem, underlying problem. Yeah, that's my take.
The only thing I can think of is like if you have like hardware safety, you can have two pieces of hardware until you understand their error rate, and then you put them together and vote, right? So I don't know if that can be applied to perception or machine learning. You have independent systems with independent failures. That doesn't sound quite right, but.
I can maybe add one example here, which is actually some work that I did with some collaborators at Bosch. And we were doing this like model for like a fuel system in a car. And it didn't need to have 1% error. It just had to perform better than the other machine learning models that they were using. So maybe depending on what it is, like if you're doing like full autonomous driving, you need this 1% error. But for maybe other low level kinds of applications or smaller modules, maybe it's accepted that there is some degree of error and it's actually viable in this kind of set of an error.
I guess maybe the extra challenge for self-driving is there are areas, like there are domains where if you want to check something like, I can reasonably test 2 to the 32 things on my computer if it's a mechanically checkable thing that requires like 1 second per test. But if you have to verify, right, 2 to the 10 to the 10, which is roughly 2 to the 30, like, and each of these requires like asking a human, is there a car here? Is there not a car here? Like this is $1 billion to do, and that seems expensive to verify for a car. So I guess it's not only is it hard to achieve this low error rate, I think it's even hard to test if you have achieved this low error rate, because if you're humans that right, you don't even know if your oracle is going to be reliable at this kind of precision.
So what are the examples where the error rates can be higher? And is that achievable in hardware?
Are you referring to the example that I mentioned earlier?
Yes.
Yeah, so this was an example where they were making a fuel detection, a detector that for the amount of fuel in the engine for their injection system. And they had some machine learning models that already had some level of error, but it was better than like baseline, whatever other baselines that they could come up with. So they were using like Gaussian processes and things like that. And then, but they wanted to put it in a neural network, but because the neural network had a much lower error rate, but the neural network is like, something that I guess is known to be kind of unreliable. And so then having a formal specification on top of the neural network can maybe assuade, people that are worried about how potentially unreliable this could be.
Oh, that's interesting. Thanks.
But like it's like a fuel, the amount of fuel in the engine. It's sort of all the engineers there sort of accepted that there's going to be some amount of error in here, and they want to just like get this as small as possible. But it's not that you need to have a certain threshold in order to actually deploy it.
I guess maybe another example of this is I think modern branch predictors, right? Don't they now start to use some machine learning fancy things to do this, where all you need to do is beat the prior branch predictor. And if you can beat your counting by adding another layer of 10 values or something, then like all your code just got 5% faster, and like everything's fine. It doesn't matter that the total accuracy of a branch predictor is only 80%. Like it doesn't have to be 99.9. Things are better now. I mean, I think there are interesting security questions to ask about trying to ask if you can attack some of these branch predictors, and that's I guess what all of this, in part spectrum meltdown stuff does with training branch predictors. But I don't think I think from just the perspective of there are some things that just don't have security consequences if you make errors, and you just need to beat the previous system, and then you're better. I agree with that. But I feel like I still think the question of there definitely are settings where you can't make mistakes. I feel like those are the ones that are really hard ones that you do need this maybe a 1 in 10 to the 10 kind of thing.
Well, thank you. I think I've learned a lot. That's very interesting. Maybe we have time for discussing one more question. So this question says, so usually we use attacks to do something like vulnerability analysis or finding out what's wrong with the models. And can that be used for good instead? Can we use whatever the adversaries can do for good things rather than simply breaking down systems?
I mean, okay, there's this line of work, right, that shows that adversarially robust models have nicer properties in that they're more aligned with human perception and that you can use them for image synthesis and these kinds of things. This, I guess, is one. I'm not using the attack per se here, but I'm using the result of a better attack. Because now I have a model that's more robust, and the model that's more robust is not just nicer from a security perspective, it also has other nicer properties. I guess this is one example where things are helpful, but here I guess I'm not necessarily using the attack exactly.
Yeah, I guess maybe like a way you can think about how you can use this for good stuff, or maybe not necessarily good, but like not attacking or breaking models, is that you can look at the adversarial attack as just a basic primitive, right? It's a primitive that just gives you a way to do a minimal distortion that changes what the network does, right? And whether you use this for breaking stuff or to do other things is, however you end up using this primitive. And I sort of think, maybe more generally, it's a small change that allows you to change that affect how the model works, is perhaps a potentially powerful way to understand how the networks are actually making their decisions in the first place. So that could be something good that might actually end up coming out of this.
So one idea I had, which is maybe just naive, it was about for like how to train neural networks, right? So my understanding is generally you're doing sort of local gradient descent. You can get caught in local minima. I was wondering if you could use like robustness analysis for training itself, right? So you'd analyze neighborhoods of the weights in different layers, and you try to improve accuracy or something like that. And because you're analyzing the whole norm of weights around it, if there's some sort of local minima that you would normally get stuck in, this would allow you to jump over it. So ideally, this could be a very large norm, right? And then you could really find sort of the global optimal values for all the weights, something like that. And maybe it works better than existing training methods, but it's going to be tough to beat that. But it was an idea.
You could think of two existing defenses as putting attacks to good use. Adversarial training involves applying attacks at training time so that you expose the classifier to the ways it might be attacked. So if you can come up with really effective, fast ways to mount attacks, then you make adversarial training more effective, maybe. And the other is these generative classifiers or analysis by synthesis that Nick alluded to, are effectively mounting an attack. They're looking for find the lowest distortion, the lowest perturbation or distortion to this image that makes the generative model, makes it something that could have been produced by the generative model for a 1. The lowest distortion makes it something that could have been produced by the generative model for a 2, which with the highest likelihood from the generative model. That's probably the true class. So that's also kind of an interesting use of effectively an attack, but now at inference time. So if you can make the attack really effective and efficient, then you've made inference for analysis by synthesis models more efficient, faster.
Yeah, and that related thing in the testing of robot policies is that we can use attacks to accelerate the testing, like generating adversarial environments, challenging environment to make sure that the autonomous vehicle can drive in those challenging environments.
Yeah, I mean, there's this quote that I like about you should care about security even if there's no adversary, because if you can get things to behave even in the worst possible environment, then in any randomized environment, it's going to be strictly easier. Where you have to be careful here, because sometimes you just can't get things to behave in the worst possible environment. But if you can make things if you can align these two, then you can, like, if you can convince me that no adversary can cause my car to crash, even if I don't think there's actually going to be an adversary who's going to want to make my car crash, then I would also be convinced that it's not going to crash, when there's rain on the road and there happens to be glare because something's shining weirdly, then everything would align. But I feel like, at least in this space, the input dimension is so high that optimizing these two objectives are not necessarily pushing the same directions. But conceivably, you might have a smaller problem where you could align these two much more easily.
Yeah, and I think in mathematical sense, using adversarial attacks to accelerate testing is like associated with solving this min-max problem. And if in the general testing, we're essentially solving that mean over all the possible scenarios. Although we get rid of one layer of optimization, but since there are so many scenarios, it's very difficult to solve. But bringing another layer of optimization, then we can solve it more efficiently.
So what about this kind of recent idea of doing watermark? I think it was originated from the children attacks. And then some people are proposing that you can embed some watermark in your model.
For what purpose?
So prevent the model to be stolen. I don't know how well it works.
Sorry, I don't quite understand what's being proposed.
I can maybe comment on something related, but it's not exactly the watermark, which is that there is some work on what is called, I guess, on adversarial examples, which is to basically use an adversarial patch but like, I guess for good reason, to basically help your object detection. And then then this is like in a scenario where you actually have control over the object you're trying to detect, right? And then so then if you put an adversarial patch on your object, which is not actually adversarial, but actually very benign, and it helps you get the right sort of detection, then that's maybe, it's not really a watermark, but like it's kind of similar to, I guess, in some sense.
I think there's one line of defense against copy of a model theft that's inspired by watermarking. So there's this age-old technique from map makers used to use, maybe still use. It's very expensive to go map all the streets around, and it would be easy for some competitor to steal your map and make their own copy. So what map makers supposedly used to do was they would put in a few extra fake streets that didn't really exist. And if they saw a competitor have those fake streets in their map, then they knew that the competitor had stolen from them. All right, so you could imagine training your neural network that same way. I have some really obscure object that's never encountered, in ordinary life, and I train my model so that when it's presented with that object, it classifies it in some very specific way. It classifies that as a ripe banana or like that. So now, if I suspect you might have stolen my model, I present your model with an image of this really obscure object. And if it also says ripe banana, then I should be suspicious that maybe you stole from me. I think it's challenging to make this kind of defense work well, because if you steal my model, you might be able to use it to label a new data set that won't have that obscure object in it, and then train your own model on those labels. So I don't know what the current state of the art is. I think there's been some kind of a arms race back and forth in attacks and defenses of this kind of work, but I think it's intriguing.
Well, is our time up?
Yes, I think so.
Okay.
Okay, I mean the discussion. And I think overall the discussion are great and insightful. And we really appreciate the participation for all speakers. And we'll also release a video recording if you missed any talks, and you can check out the recording online. And if you have any questions, you can also contact our organizers listed here. And we hope people can stay in touch after this workshop, and maybe next time we can meet everyone face to face. Okay, let's thank all speakers again. And this is going to be the end of this workshop. Thank you all.
Thank you.
Thank you.
Thank you.
Bye.
Bye.